Hey everyone, and welcome back to PrepFusion. So today we will begin with the R-PYQ series of electrical machines. So we will solve most of the important like recent PYQs that came in gate from electrical machines. We'll cover the induction motor and like we'll cover the iron part as well. So whichever questions came in iron, we have covered those. So make sure you do those questions as well. If you are a iron aspirants, make sure you follow this video, especially for induction motor and your transformers. So questions have come from electrical machines in iron, so make sure you follow that. And for double E, don't need to say much, you of course have to follow it. So here I have opened this YouTube playlist, so make sure if you have not already covered like the important parts or whatever you want from this playlist, complete electrical machines is covered completely for free on YouTube. So make sure you utilize it, and trust me, whatever I have covered right in this course, you will not even get by paying thousands of rupees. In paid courses, you will not get this. Like people feel like because I'm providing it for free, the quality might be lower. But once you study it, you will realize. Okay, you study at least the first video. In the first video itself, I have explained some things like what does a transformer means, and what happens when we apply DC supply voltage to transformer. All these things happen there. So if you watch, you will realize. Okay, many new things are there. Okay, so that was a bit of information. If you have not studied, please make sure you revise through this playlist or study from this, right? Because in this video I will only solve questions. I will explain theory as well, but not much, very less. Okay, now for the students who have studied machines already, they can revise machines through this revision X notes. Okay, these are revision X notes. So notes for this playlist, right, for this course is already present free on the website. So go into our website. In the first video, if you click the first video of this playlist, you will get complete information, how to download the notes, which link to go, everything is mentioned in the first video. Just click the first video, everything I have like explained in a very easy, simple manner. Okay, you will get the notes, everything for the course. And also if you want to revise, you can revise through the revision X notes. So complete machines short notes is uploaded, and other subjects as well. So you can go into the website or search in YouTube revision X notes. Okay, there a video will come, just watch that video, everything has been explained regarding revision X notes. You go into the website, also you will find the revision X in the free courses section. So from there you can download this revision X notes to revise, right? These are just short notes, PrepFusion short notes, so you can revise through these kind of things. And yeah, that will be very hugely beneficial for your gate preparation. And whatever questions I have solved in this R-PYQ series, right, for electrical machines, you will see I will try to use as little formula as possible. Most things I will try to derive or try to solve by basics. So once you start the video, you will realize. Trust me, you will enjoy it a lot, and a lot of things will be cleared and revised. So let's begin with the first chapter, that is magnetic circuits. Then we'll move on to transformers, then DC machines, and then induction motor, and finally to synchronous machine. Also, please don't forget to like the video. If you do enjoy this series, make sure to like the video and comment down below whatever part you enjoyed. So once you will study, you will see a lot of things, you will realize a lot of mistakes that you are doing. So you will enjoy the video for sure. If you're enjoying, comment down below, like the video, hype the video. So yeah, let's start with our first chapter, that is magnetic circuits. Let's begin with magnetic circuits. So this is the first question. The magnetic circuit shown below has uniform cross-sectional area and air gap of 0.2 centimeter. So if you see, its area is uniform, and it has 0.2 centimeter of air gap. The mean path length is 40 centimeter. So basically 10 centimeter, 10 centimeter, 10 centimeter, and 10 centimeter. Correct. Now assume that the leakage and fringing fluxes are negligible when the core relative permeability is infinite. So mu r is infinite. Okay. The magnetic flux density computed in the air gap. So air gap magnetic flux density. So B gap equals to 1 Tesla. With the same ampere turns, if the relative core permeability mu r is 1000 and it is not in the saturation region, it is in the linear region, the flux density calculated in the air gap would be, what will be the air gap now if the permeability is not infinity, right? So do remember how do we calculate the flux density? So basically, right, if I convert this into magnetic circuit, so it is nothing but a series magnetic circuit, where here I am providing the mmf, right, that is n into I, right? mmf is same, they have told me same ampere turns, right? So if I convert this into magnetic circuit diagram. So here I will have N into I, right? That is my MMF, and I will have two reluctance. One will be the core reluctance, correct? S core. Another one would be the S air gap. Okay, I can write just SG. I can write BG like this. Now the interesting fact is, if my mu r is infinity, remember what was my uh, uh, reluctance formula? It is L upon mu a. Okay, it is L upon mu a, right? That is my reluctance formula. Where A is the area, L is the length basically of the core. So in our case, mu is basically mu r into mu naught, and mu naught is 4 pi into 10 raised to the power of minus 7. Correct? If you remember, it is 4 pi into 10 raised to the power minus 7. And if mu r is infinity, then your reluctance of the core will be 0. If mu r, so I can write this as SC or S core, it does not matter actually. So that will be 0 if mu r is tending to infinity. Okay. So in the first case, it is 0, right? So what is the flux in this circuit? Flux is the same. Okay. What is the flux? So flux would be phi would be equals to, in the case 1, right? Phi 1 would be equals to Ni by the reluctance, because SC is 0, it will be only contributed by G. Okay, that's all. And what is your flux density? Flux density is simply phi 1 by area, that will be your flux density, that is Bg. Okay, so in the first case, this is my Bg, that is equal to 1 Tesla, that is fine. In this, now this A is constant, this area is A is same, it will not change basically, right? In the second case, what is happening is I have a uh, 1000 of relative permeability, right? Relative permeability is not infinite anymore, right? So then my SC will not be, so this is the case 1. So in the case 2, your SC will be L upon 1000 into mu naught into A. Okay, that is what my SC is. So what will be your overall reluctance in the case 2? Now you cannot say that SC is 0. So overall reluctance will be SC plus SG, correct? So that will be equals to, so this is, what is the length? So length would be 10 plus 10 plus 10 plus 9.8, not 10, right? Because 0.2 has been lost in the air gap. So it will be 39.8 centimeter. And don't worry if I'm writing this in centimeter, right? Everything will be cancelled because I'm taking the ratio. Everything will be cancelled. Don't worry about it. So this is 39.8 divided by 10 cube into A into mu naught plus SG. SG is what? It is 0.2 centimeter divided by so what is the relative permeability of air? Relative permeability of air is 1. So this will be A into mu naught, that's all. Okay. So this thing will be constant basically. In the previous case also, SG will be this only. Now what is the flux in this case? Phi 2. Phi 2 would be your overall MMF Ni divided by this reluctance SG plus SC. Okay. So and your air gap flux density would be Ni. So basically phi 2 upon A, correct? So in the second case, so Bg, this is not air, this is Bg2, right? So Bg2 upon Bg1, where Bg1 is given as 1 Tesla, that is equals to phi 2 upon A upon phi 1 upon A, right? So A will be anyways cancelled. Okay. So this will be so Bg1 is 1, right? So your Bg2 will be equals to phi 2 by phi 1, that's all. Now what is your phi 2? Phi 2 is this Ni by Sg plus Sc. So this will be Ni divided by Sg plus Sc divided by Ni divided by Sg only, because in the previous case your mu r was infinity, so Sc was 0. So this will be equals to Sg by Sg plus Sc, or I can say directly my answer would be, if I divide by if I take Sg common, right, that would be equals to 1 divided by 1 plus Sc divided by Sc. Okay, that's all. So what is Sc divided by Sg in the second case, right? This is the core reluctance in the second case. So if I find out the ratio, right, Sc divided by Sg, that will be actually quite high. That is what I am thinking. Okay, this will be quite high. Okay, so yep, let me calculate these values. Okay, so if I find out the ratio, right, of these two, what will be the ratio? So Sc divided by Sg, that will be 39.8, it is in centimeter, divided by 10 cube A mu naught divided by A mu naught. So A mu naught will be cancelled, 10 cube will be still in bottom, so this will be 39, so 0.8 divided by 200. Okay, so almost 0.2 actually. Just let me calculate these values. So 39.8 divided by 200, that is 0.2 almost. So this will be 1 plus this inverse, so 0.83. Okay, so your Bg2 comes out to be 0.834. What are those in two decimal places? Round off to three decimal places, so it will be 0.834 Tesla. This will be your answer for the question. That's all. Like, seems pretty lengthy, but it's not that difficult. It's very simple. So yeah, let's solve the next question. So this is again a very interesting question. Like, magnetic circuits mainly will involve the concept of dot polarity, right? So here the input impedance of Zn we have to calculate, and if the coils have some mutual inductance of 1 Henry, right, in Laplace domain. So remember one thing, right? What does dot represent? Dot represents the polarity, the instantaneous polarity. So if I assume my dot to have positive instantaneous polarity on the left hand side coil, the right hand side coil also will have the same polarity, right, at the dot. Why? Because it depends on the orientation and the flux flow, right, that we have discussed previously in the full course. So we will use that here. We will use that. So I know this is plus, right? So I will not use much stuff here. So what I will do is I will assume some currents. I will assume few currents here. So let's assume that this is the current, this is plus, this is plus. Let's assume this current I2. Let me write it in time domain only. I will convert them in Laplace domain later. This current I1, and it makes sense because if this is plus, right, current direction will be this only, because I have a resistive load, so it will absorb power. So if this is plus, right, current will leave from the positive terminal because it has to absorb power. So this is also plus minus, so the load has to absorb power, hence current direction will be instantaneous, current direction will be this only. And here I have source because I'm providing some. So actually what do I need to calculate? I need to calculate, if I'm providing a voltage V1, I need to calculate V1 by V1 of S by I1 of S in Laplace domain, right? First let me consider the time domain equations, then I will obviously convert them to Laplace domain. That is the point 1. Now point 2 is, if you remember this thing, that if I have two coils, right, and both of them are dot, okay, now interesting thing is happening. If both of them are dot on this side, and this is the current, right? I. So we see current enters the dot of both the coils. That means the mutual inductance between them will be additive in nature. What do I mean by that? So the voltage V1, right? Let's assume that this is coil L1 and this is coil L2, and they have a mutual inductance between them as M, right? It will be L1 into di 1 by dt plus, because both of the currents are entering, plus M into di2 by dt, whatever is the coil whatever is the current in the second coil. In this case they are same, so it does not matter, but this is a basic property. Now if they are series, if their currents are in opposite sense, what do I mean by that? So for one of the coil, current enters, for the other coil, current leaves, then this mutual inductance, right, will be simply subtracted. That's all. It will not be added, it will be subtracted. Here what is happening? In one of the coils, current is entering, in the other coil, current is leaving. So it is subtractive in nature. So let me first write down this equation, right? Let me first write down this equation. So what is my what is my so let's assume this voltage is V2, 8 plus minus V2. So current I2 is what? I2 of t is simply V2 by 5. Okay, that is certain. Also, what is the voltage across the coil? So V2 of t would be equals to L2 into di2 by dt minus, because they are in opposite sense, right? From one of the coil, current enters, from the other coil, current leaves. So it will be minus, right? Minus M di1 by dt. Okay, and okay, how will it help me? So V2 is this, right? V2 is I2 into this, so this will actually help me out. So I2 is V2 by 5, or V2 is I2 into 5. Okay, so V2 I can replace with I2 into 5 equals to L2 is 4 Henry into di2. Remember, all these are function of time, right? These are all instantaneous values, function of time. Di2 by dt minus M. Now M is what? 1 Henry, so it will be 1 into di1 of t by dt. From this I will convert this into Laplace domain. So now I will take the Laplace transform of this whole equation. If I take the Laplace transform, this will be converted into 5 into I2 of s equals to 4 into s I2 of s minus I1 of s, correct, into s obviously. So from this I can get the value of I2 of s. I2 of s would be equals to minus s by 5 minus 4s. Hold on a second. This current is, okay, current is leaving from the coil, right? Actually, according to us, current should enter the coil. That's what we know. Actually, how do I calculate this inductance is, like, if this is dot, right, plus minus, we assume that the current enters the coil, and then we write V equals to L di t by dt. But here we are saying the current is leaving the like positive terminal. So I'm guessing this should be negative somewhere, or okay, let's keep it as it is right now. This is 5. No, I think, yeah, this will be, no, I'm guessing this will be negative actually. Why this will be negative? Because generally what we say is, if the current enters, right, then we say this is plus minus, and then we write this equation V equals to L dit by dt. Now if I reverse this current direction, right, so your I actually becomes minus I. So you replace your I with minus I, so this will become minus di by dt in this case. So there will be a negative sign here. So there will be actually a negative sign. Just be careful. There will be a negative sign here. So what will happen? Negative will be positive. So this will be this all of this will become plus, right, into I1s. So be careful, like this kind of things are a bit tricky. This will come more with practice. You have to practice as much as possible. Just be careful with these things, right? Cool. Now this is fine. Now let's come to the primary side, right? In the primary side, if I uh, write this KVL equation, okay, so minus V1 plus 4 into so all these are in time domain, plus 6. So L di and dt. For this case, it is fine, right? Because current is entering the positive terminal, there is no problem. Here current was leaving, that's why I had to put a negative sign. So few things you have to keep in mind. If current leaves the positive terminal of inductor, there will be, you will have to add a additional negative sign. This part is different, right? Whether it will be the mutual inductors will be additive or subtractive, that is a separate topic. Okay, just be careful regarding these things. Okay, so minus plus then L di 1 by dt 6 into d1 by dt minus it will be subtracted m into di2 by dt, that is 1 into di2 by dt, that will be equals to 0, right? So I will convert this equation into Laplace domain. So this will be v of s will go on that side, will be equals to 4 into I1 of s plus 6 s into I1 of s minus I2 of s. Okay, now I2 of s is this, right? This, so I will replace a minus this, right? So this I can replace, this will be, these things will be same, just I can take I1 of s common, this will come it together, and I2 of s minus of I2 of s is this value, okay, s into, so minus s divided by 5s 4s plus 5, and in brackets I will have I1 of s. So v, so this is actually I have written this as v1, so you can write this as v1 only, because previously I mentioned that v1. So v1 of s upon I1 of s, that is what I'm concerned about, that is equals to my Zin of s, that will be equals to this will be 16s plus 20, right? 16s plus 20 plus 24s square plus 30s minus s divided by 4s plus 5. So your answer would be 23s square plus 46s plus 20 upon 4s plus 5. Pretty interesting question. So what things you have to keep in mind? So this is the one part that you have to keep in mind, right? If the currents are reversed, then the voltage polarity also will be reversed, and the other part is this one, how will the mutual inductance be? So you see, you just check solution of any coaching PYQ book, you'll not understand what they have done, you'll literally not understand it, right? That's why I am here to solve the questions. Literally trust me, you'll go into any publication, you'll not understand the solution there. Let's now solve the next question. So let's solve the next question. So this is the next question where we have a toroid made of CRGO, has an internal diameter, right? That is of 10 centimeter, and outer diameter. So this is the internal dia and outer dia of 14 centimeter, right? So what do we mean by internal and outer dia? So it will be like a hollow kind of cylinder, and this is the internal dia, and this would be the external dia. The thickness of the toroid is 2 centimeter, correct? And the number of turns of the toroid is 200. Now, is the thickness 2 centimeter? Yes, it is. It is correct. Like this information, if they don't even give it, then it is fine, because what is happening is, if you see that this is the dia, right? Dia is 10 centimeter inner and outer is 14. So radius would be, this will be 5 centimeter and outer radius would be 7 centimeter, right? So this thickness is actually 2 centimeter. That is fine. That we already know from the diameters, but they have given this extra information. That is fine. Mu naught I know, mu r I know. They have given me of CRGO. When the current this flows, what is the flux density? So to calculate flux density, what do I need? Flux density is mu naught mu r into h, right? Or you can directly say it is flux density is flux by s. That also is fine. And mu naught mu r I know. What is h? H is equals to h into L, right? Will be equals to L is the mean path, will be equals to N into I, ampere turns, correct? What is L? L is the mean path. Now in a toroid, the flux flows through the core like this, okay? This is the mean path of the flux that flows through the core. Yeah, this is like a cylinder kind of shape, right? So flux flows like this in the center, from the center, right? So what is the length of the path for the flux? It is 2 pi into this imaginary radius, right? So it is basically the circumference of a imaginary circle that is in the middle, right? So what is the mean radius? It is called as the radius of the circle, that is called as the mean radius. What is the mean radius? It is basically the outer radius, that is 7, because the outer diameter is 14, plus the inner radius, that is 5, divided by 2, okay? So it is 6 centimeter, okay? It is 6 centimeter, right? So yeah, the radius is 6 centimeter. So its mean length will be 2 pi into r, that is 2 pi into 6, that is 12 pi. So your h would be equals to N into I. So N is 200, I is 5 into 10 raised to the power minus 3 divided by 12 pi. So this would be 1 divided by 12 pi, that is my h. So your b, remember they have asked in millitesla, okay? Just keep this in mind, they have asked in millitesla. So your b would be mu naught, that is 4 pi into 10 raised to the power minus 7 into mu r is 3000 into 1 by 12 pi, basically. That is this, right? So what will happen is, this will be cancelled with 3, this 3 will be cancelled with 1000. So this will be actually 10 raised to power of minus 4, basically 10 raised to power of minus 4. So we have to report in millitesla. This will be 0.1 millitesla, okay? If I am not mistaken, this should be 0.1. Okay, one small mistake, one very, yeah, not small, very large mistake. This is in centimeter, right? So this length is in centimeter, correct? But we should not report in centimeter, we should report in meters. So this will be 10 raised to the power minus 2, because it is in centimeter. I have converted this into meters. So this will be 10 raised to the power minus 2. Don't make these kind of mistakes, okay? I am also making. Don't make this 10 raised to the power minus 2. So here a 10 raised to the power minus 2 will be there, right? Due to that, this will be 10 raised to the power minus 2 already. So this will be 10 millitesla, not 0.1 millitesla, 10 millitesla, okay? 10 will be your answer for the question. Let's solve the next question, right? So in the next question, a sinusoidal current of this is flowing in the 4 ohm inductor, which is mutually coupled to another 5, sorry, not ohm, 4 Henry, which is coupled to another 5 Henry inductor, whose current is given like this. The coefficient of coupling between the inductors is 0.6. The peak energy stored in the circuit is, what is the peak value of the energy stored in the circuit, okay? So there is this formula for energy stored for uh, two inductor setup. So it is basically half half into L1 into I1 square plus half into L2 into I2 square plus M into I1 I2. Okay, that is the formula basically. So peak, basically I will choose all the peak values. Okay, so if I choose all the peak values, this will be half into L1, that is 4 into I1 square, that is 1 square, plus half into L2. L2 is 4 into I2 square. I2 is 2 square, right? Peak value. Uh, Hold on a second. Oh, okay. So sorry, this is 5, right? 5. The secondary inductor is 5 Henry. Plus M, mutual inductance is, which is mutually coupled, and their coefficient of coupling is 0.6. If their coefficient of coupling is 0.6, what does it mean basically? So coefficient of coupling is basically uh, the mutual inductance upon under root L1 L2. Okay, so M, I don't know, I know coefficient of coupling, so M will be equals to 0.6 into under root L1 L2. So under root L1 L2 will be 4 into 5 basically. So this will be basically, if I solve this, 20 under root into 0.6, which comes out to be 2.683. Okay, so 2.683 into I1 into I2. I1 into I2 will be, this will be 1 into 2 basically. So let's solve this actually. So this will be basically 2 plus 10 plus 2.683 into 2, that is 5.366, right? So this plus 12, that is 17.366. So this formula is actually pretty important. This have this same formula has been used in this gate double E paper, I guess. So 17.366 will be okay. Remember one thing, these are all milliamperes, right? These are all milli. So if I square milli, I will get micro. So that's why the answer will be in microjoules, not in joules. Just be careful, okay? Because these currents are all in milli. Okay. So yeah, that was one thing. So your answer would be 17.366 milli. They have asked us to round off to 2 decimal places. So your answer would be 17.37 microjoule. Okay. So let's solve the next question. So here we have been given the circuit. The source frequency omega is 5000 radian per second. Okay. The mutual inductance between magnetically coupled inductors is 5 millihenry. Okay, the mutual inductance between the magnetically coupled inductors is 5 millihenry, right? So M is 5 millihenry. Okay, with the self inductance L be 125 millihenry, right? Like the L1 is self 125 millihenry and L2 is 1 millihenry. And the Thevenin's impedance ZTH, but they are asking me Thevenin's impedance ZTH between these two terminals, right? So let's check. Let's first write down the reactance values, right? These are all given in inductive inductance and capacitance. So let me write what is X1, right? X1 is the winding inductance, right? It is 120. So it is j omega omega is 5000 into L, that is 125 milli. So this will be J625 ohms. X2 would be J into 5K into 5K into 1 millihenry. So this will be J 5 ohms, and your XM, right? XM would be J into 5K into 5 millihenry again. That is J 25 ohms. Okay, so J 25 ohms. So yeah, now one thing that you have to remember, you have to understand the T model of a transformer. Okay, what is a T model? That includes the mutual inductance. Okay, so the T model of the transformer would be something like this. This 2 ohms will be there, right? They won't matter with the frequency components. Then I will have this inductance, that will be x1 minus xm. Okay, you have to represent, if you want to represent the mutual inductance effect, you have to write this x1 minus xm, and this will be, if I want to write everything in a single circuit, this will be xm, right, and the other side will be x2 minus xm. Okay, this is called as the uh, T model. So that's how we call the T model. Of course, there is the reactive capacitance as well. Don't forget the reactive capacitance. So this you can do only you have been given the values. Okay, what do you call, given the values of uh, the mutual inductance in inductance and the uh, yeah, primary and secondary inductance. Now there is a thing that I'm also confused in this question, that they have not given the turns ratio. How will you refer this particular capacitance on the other side? I don't know. Okay, so what they do in T model is they assume this to be 1:1. If it is 1:1, then all of this works. So simply the capacitance also I can draw here, right? And what will be Xc? Xc would be 1 by j omega 10k into C. C is uh, 50 microfarad. C is 50 microfarad, right? So yeah, this will be equals to, if I calculate this will be 10 cube 1000 upon 50 upon 5. So that is minus J4. Okay, that is the capacitance. Now what will happen here? So what is x2 minus xm? X2 minus xm, this will be equals to plus J20. X1 minus xm will be plus J 600, right? Sorry, x2 minus xm. Okay, this will be actually minus. Sorry. X2 minus xm will be minus J20, right? X2 minus xm will be minus J20, not plus. Xm is 25. Correct. So what will happen? So and this is already equals to J25, right? So if I convert this, uh, if I write the equivalent of this parallel branch, right? So it will be J25 divided by, this is minus J24. So J 25 minus j24 basically, and of course here also I have minus j24. So this will be 1, so this will be minus j600, right? This whole thing can be converted into minus j600, and this is plus j600, so everything is cancelled. So this is zero impedance here, right? So actually your circuit is simplified by a lot. Okay, unfortunately you will have to remember the T model thing. That is all. So this will be 4 ohm, 4 ohm, 2 ohm, right? 4 ohm, 4 ohm, 2 ohm. Okay, now if I solve for this, right? So this will be 24 upon 2 plus 4 and plus 4 ohm. So this will be equals to 8 by 6 plus 4. So 8 by 6, that is 4 divided by 3 plus 4, that is 5.33 ohms. Okay, so your answer would be 5.33 ohms. That's all. Like, only thing that you have to remember is the T model. Let's solve the next question. So two magnetically coupled coils, when connected in series aiding configuration, the total inductance is 500 millihenry. So if they're coupled, right, if they're connected in series aiding, it will be L1 plus L2 plus 2M, that is 500 millihenry. And L1, and if they are connected in series opposite, right, series opposing basically means L1 plus L2 minus 2M, that is equals to 300 millihenry, right? If the self inductance of the both the coils are equal, so L1 equals to L2 is same, so essentially this will be 2L plus 2M equals to 500, that is L plus M would be equals to 250, and here L minus M would be equals to 150, and that this becomes much simpler. So they're asking me the coefficient of coupling. So if I add these two, this will be 2L will be equals to 400. So L is equals to 200 millihenry. Okay, and M is equals to 50 millihenry. Okay, so yeah, so what is the coefficient of coupling? Coefficient of coupling, if you know, it is M upon under root L1 L2. So in our case L is equal, so it will be M upon L basically. So 50 upon 200, that is 0.25. Okay, so 0.25 would be your answer for this particular question. Coefficient of coupling would be 0.25. That's all. So yeah, let's solve the next question. This is the next question here, right? So now they are asking me, consider two coupled circuits having self inductance L1 L2 that carry non-zero currents I1 I2. The mutual inductance between them is M with unity coefficient of coupling. Okay, so if the coefficient of coupling is unity, basically M will be equals to under root L1 L2. That's all, right? The stored magnetic energy of the coupled circuit is minimum at which of the values of I1 by I2. Okay, so we have solved a question like this, right, previously. So we know the energy stored when coils are coupled is half L1 I1 whole square plus half L2 I2 whole square plus M I1 I2. Okay, that is the energy stored. So if I want to find out the condition, right, where the energy is minimum, it is minimum when, hold on a second, just give me 1 second. Let me get the charger. With respect to some current condition, right? So if my del E by del I1 is equals to 0, and if my del E by del I2 is equals to 0, then of course either I will get a maximum or minimum, right? Either I will get a maximum or minimum. So let's do it. Let's make del E by del I1 equal to 0, and if nothing is mentioned, you will assume both the coils are series aiding with each other, right? They're aiding with each other. So yep. So if I do del E del I1, this will be L1 into I1 plus, this will be 0, this will be plus M into I2, that is equals to 0. So my M, what have they asked? They have asked me the I1 by 2, right? So in this case, my, so they have asked me I1 by 2. So I1 by I2 will be equals to minus M divided by L1. Okay, that is the first condition. That is the first condition. Okay. So I1 by is equals to minus M by L1, that is present in option A. Option A will certainly be correct, right? It is a MSQ, so multiple options can be correct. So another condition is del E by del I2 will be, now remember there is no global maxima here, right? Because all these are positive numbers, so we can only get a minimum. That's all. So del E by del I2 will be equals to 0 plus L2 I2 plus M I1. Okay. So yeah, this will be equals to 0. So again, I need to find out the value of I1 by I2. So I1 by I2 this time would be equals to minus of L2 by M. Minus of L2 by M is present in option D. So option A and D will be the correct answer for this question. Let's now solve the last question, right? Final question. I guess this is the final question on magnetic circuits. So the circuit is represented here and its equivalent T model is represented, right? L1, L2, L3, and remember these are the dots. So now what are they asking me? They are asking me, just give me 1 second. They are asking me they are asking me, this is the equivalent T model, then the values of the inductance L1, L2 and L3 would be. Okay. So uh, what will be the equivalent values, right? So here current is entering the dot and here current is leaving the dot, right? So if in the both sides current enters the dot, then what happens? This becomes like, here it is entering, here it is entering. So what happens actually is, if I see a connection like this, so if from the both for the both coils, right, if current enters into the dot, basically their mutual inductance will be added. How? So basically the voltage equation for this coil 1 will be V1, that is L1 plus M into di1 by dt, and for the voltage of the second coil it will be L2 plus M into di2 by dt. But for this to happen, both the coils should have same orientation, that is current should enter in both the dots of the coil, correct? But in this case, if you see, one current is entering the dot, other current is leaving the dot, right? So they are not additive in nature, they are actually subtractive in nature. Okay, so this is the voltage equation of coil 1 and this is the voltage equation of coil 2. So coil 1 will have the voltage equation equals to L1 is L1 is 3, right? That is the winding inductance. M is 4, so this will be 3 minus 4, that is minus di1 by dt, and L2 is 2, and 2 minus 4 di by dt, right? That is minus 2 di2 by dt. Okay, so these are the voltage equations. So let us try to write the voltage equations here. So what will be v1? Basically v1 will be equals to v1. Okay, hold on, I forgot to write that. It will be basically L1 into, sorry, the current, right? This will be uh, v1 will be equals to L1 di1 by dt into minus m di2 by dt. I forgot this, sorry. So yeah, the voltage equation would be, this would be equals to L1 is what? L1 is 7, L1 is 3 di1 by dt minus m is 4 di2 by dt. Okay, and what about this case? What about the second case? So it will be L2 into di2 by dt into m1 into di1 by dt. So this will be so L2 is 2 into di2 by dt and minus 4 di1 by dt. Okay, these are the voltage equations. Now let us try to write the voltage equations here. So voltage equations here, if I write, this will be v1 will be equals to so here, right, what is this current? This is actually the T model conversion. So this is I1 plus I2, that's all. So I1 plus I2, so this will be L1 into di1 by dt plus L3 into I1 plus I, so this will be d of I1 plus I2 upon dt. Okay, if I replace this, this will become L1 plus L3 into di1 by dt plus L3 into, just give me 1 second. Hello, I'm just checking the voice. Yeah, into d I2 by dt. Now from this I can directly compare that my L3 will certainly be minus 4, right? If I compare from the first equation, L3 will certainly be minus 4. That is certain. So L3 is minus 4 in this option, in this option. What about L1? So L1 plus L3 has to again be equals to 3. So L1 plus L3 has to be 3, right? So L3 is minus 4, so L1 has to be 7. So that is present in option A. So certainly option A is correct. You can verify this with the second option as well, right? I mean second equation as well. If I write the equation here, second KVL. So V2 will be equals to, again you see the direction of the current. So V2 will be equals to this L2 into di2 by dt plus this will be L3 into d of I1 plus I2 by dt, correct? So yeah, we are done with this almost. So this will be equals to L2 plus L3 di2 by dt plus L3 into di1 by dt. Again if we compare, right, L3 will be equals to, again here if you see, it is equals to minus 4, right? di1 by dt, the coefficient of di1 by dt is minus 4. So L3 will be minus 4 again. So if L3 is minus 4, L2 plus L3 must be equals to 2. So if it must be equals to 2, right? So your L2 must be equals to 6 Henry, right? and 6 Henry is present in option A only. So option A is definitely certainly correct. So this is another way to prove basically the T model. How can I prove the T model, right? So yeah, that's all basically. For the magnetic circuits, we'll start off with the transformers. Let's start with transformers. This is the first question. A single phase 100 kVA 1000 volt 100 volt 50 Hz transformer has a voltage drop of 5% across its series impedance, right? So what is its series impedance? This is my series impedance. If you remember, the transformer, essentially it is the winding impedance, which includes both the primary and the secondary windings, resistance and the inductance or the inductive reactance. Okay, they're telling me this drop is 5% at full load. What do they mean 5%? 5%, like it is not a volt in the units of voltage, right? So 5% of the full load voltage, that's all. So 5% means it is 5% of the full load voltage, right? That's how we define the voltage regulation, right? So there was a formula which I will come to. So what is this drop actually? This drop is actually I into R plus J I into X, correct? If you remember correctly, this there was an approximation of this. The voltage drop was IR. So this is the voltage drop actually. Then there was an approximation. This is IR cos phi plus IX sin phi. Okay, and after doing the approximation, after dividing this by full load voltage, this is the full load voltage, right? Now this formula becomes X R cos phi, where X is basically the okay. So let me explain you this. So what I can do is I have to divide by full load voltage because I want to calculate the percentage. I want to calculate the voltage drop in terms of full load voltage. That's why it is a percentage. So in multiplied by 100 will give me the percentage basically, right? This is the percentage voltage regulation, right? All the voltage drop is essentially the voltage regulation. Basically voltage regulation is V no load minus V full load by B full load, right? And this V no load minus V full load is basically the voltage drop. That's all. Okay, I'm just deriving the formula where this formula came from. Now what we can do, this is the actual current that is currently flowing, right? This will be always same. This thing will depend on the power factor. Now what I can do is I can multiply and divide by full load current. Okay, I can multiply and divide by full load current. How will that help me? So what I can do is, hold on a second. If I so this, right, this should be Z base. This should be Z base. XPU RPU cos theta. This is the actual current by full load. So 50. So what I will do is, this is I can take I common, right? I can take VFL common, and rest things will be same. R cos phi plus X sin phi into 100%. This thing will be same. Now what I will do, I will multiply and divide by IFL. So I'll multiply and divide by I full load. How will it help me? This is I full load upon B full load R cos phi plus X sin phi. Now something interesting will happen here. So the purpose of this videos, right, are not to just solve questions. The purpose of this is to install some sort of intuition in your brain so that you can solve the questions in the exam hall, not me watching the solution. So what is this? This is called as a loading factor, right? If it is if the current is equals to full load current, then it will be X equal to will be 1, right? This is the loading factor basically. Now this is essentially X, and this is what? This is basically the Z base, right? So your formula, so this is what? R actual upon Z base, that is nothing but RPU. This X, right? So your voltage regulation percentage formula is X RPU cos phi plus X XPU sine phi. That was the point, to explain this, like to come to this formula. Basically I could have written this formula directly, but I wanted to derive a bit so that you get the basic idea. Of course, don't forget there is into 100 percentage as well, don't forget that. Okay, now the thing is they are telling me that it is 5% of the full load voltage drop. Now what is the actual full load voltage drop? So this is my voltage drop, right? So if I take the magnitude of my voltage drop, it will be this whole square plus this whole square, that is equals to 5%, correct? That is equals to 0.05. This is what they mean by voltage drop at full load. Why full load? Because I is equals to I full load, where x is 1. This x is 1, right? I equals to I full load. Okay, that's why it can be written in terms of this value. So yeah, I hope you can understand how is it 5%. How is it 5%? It is again given in per unit. Again, what you can do, this is voltage drop, right? So if you have to communicate your voltage drop in terms of percentage, what you'll do, you'll divide the voltage drop by the full load voltage, right? And this will be the magnitude basically divided by the full load voltage. And again you will do the same thing, right? You will do the same thing, multiply and divide by I full load, and you will see that this will come in per unit. Okay, I'm not doing it, but this will come in per unit. This is the magnitude of the voltage drop. Now of this 3% is due to the resistance. So this magnitude of the voltage drop, 3% is due to the resistance. Basically this contributes to 3% of the voltage drop, right? That is 0.03, correct? The percentage regulation, basically they are asking me the percentage regulation of the transformer at full load, that is x equals to 1. I have to calculate VR percentage at power factor 0.8 lagging. Okay, 0.8 lagging. Okay, 0.8 lagging, right? Now so your what will be the, so I need to actually calculate this x, right? X. So I got, this is nothing but RPU actually. They given the voltage drop due to the series impedance is 5. So basically this information, right, that they have given me, this thing, right? This is what actually, this equals to I into Z divided by I into magnitude of Z divided by VFL, and in our case it is IFL, right? This is the voltage drop, right? And voltage drop in percentage will be 5%. So I have to divide by VFL. So it is in terms of 5% of what? Full load voltage. So this is the actual value, and your current is full load. So they have mentioned it is full load current. So this will be actually IFL. So what is this? IFL by VFL. What is this? It is nothing but Z base. So it is mod of Z upon Z base. That is equals to my ZPU. So actually indirectly they have given you the value of ZPU. And in that same thing I can do. Again I can divide by VFL here. This will be IFL. And indirectly they have given you the value of RPU. Okay, that is what I was trying to explain here, but this is the better way to understand it. So RPU, ZPU is given. If I somehow calculate the XPU, I am golden. So what will be XPU? Again, it is a inductive load. So it is a series inductive load. It will be mod of ZPU whole square minus RPU whole square. They will follow the simple rules, whatever series inductive and resistive circuits work on. So ZPU is equals to 0.05 whole square minus 0.03 whole square whole under root, that is 0.04. Sorry, XPU 0.04, right? And they have asked me to calculate the full load. So at full load x equal to 1, I have to calculate the voltage regulation at 0.8 power factor. So I can use this formula, right? Voltage regulation formula that we derived. This will be percentage equals to 1 into RPU. RPU is 0.03 cos phi into XPU XPU 0.04 into 0.8, okay, into 100% obviously. So this will be 2.4 plus 2.4, that is 4.8%. Okay, so 4.8% will be your answer for your question. Yeah, let's move on to the next question. So a three-phase 900 kVA 3 kilovolt. So it's a three-phase 900 kVA 3 kilovolt to root 3. So these are the line voltages, right? Always line voltages are mentioned. Make sure to remember this. This is the line voltage of the primary side. This is the line voltage of the secondary side. 50 hertz transformer has primary high voltage winding. Primary side resistance per phase is 0.3 ohm, and the low voltage side resistance per phase, right? So this is the primary side resistance per phase, this is the secondary side resistance per phase, that is 0.02 ohms. The iron loss is 10 kilowatts. So P iron is 10 kilowatts. The full load efficiency of the transformer operated at unity power factor. The full load efficiency of the transformer operated at unity power factor. So what will be the full load efficiency? It will be operated full load. So full load means, so actually the efficiency formula is S x into S rated into cos phi power delivered upon x into S rated cos phi plus x square into PCU FL, the full load copper loss, plus the iron loss. That will be constant. It does not depend on the load. Correct. This is the formula basically. And this like is not a like very difficult formula. This is very intuitive to understand. There will be the output power upon the input power. Input power will be output power plus the losses. These are my losses. So x square basically depends on the loading. Copper loss depends on the loading. So they are asking me the full load percentage efficiency at unity power factor. So x and cos phi all are 1. X is full load, that is 1. Cos phi is unity, so it is 1. So essentially your efficiency, so in percentage have they asked? In percentage, right? Full load percentage. So this will become S rated so S, what is S rated? S rated is given, right, 900 kVA. So it will be 900 kVA. I will write everything in kilo, so everything will be cancelled, upon 900 plus x square is 1 PCUFL plus PI. So PI is already given, right? PI, the iron loss is 10 kilowatts, so that is known to me. All I need to find out is the copper loss. How will I find out the copper loss? It's very simple. So either you can refer all the resistance to one side and then calculate the copper loss, or you can individually calculate the copper loss on primary and secondary and add them up, right? You can do it. You can add the powers, right? You can add the powers. You cannot add the currents, voltages. You can add the powers. So individually you calculate the power in the primary, individually you calculate the power in the secondary, and then you can add it. Okay. Yeah. Now, how do I calculate? So what is the copper loss per phase? Per phase copper loss, right? In a winding. So PCU copper loss per phase, it will be I square, I phase whole square into the phase winding whole square into the resistance, right? Per phase resistance. Now there will be two parts, like there will be primary and secondary. So I will compute both for primary and secondary. So let me write here primary and secondary. Then I will add them up. So now yeah, so what is the primary phase current? So remember, primary side is delta connected, and I know what is the rating of the transformer, 900. right? So we know that root 3 into VL into IL is my rating of the transformer, right? Three phase apparent power. So primary side, the line current would be S, that is 900 upon root 3 into VL. So VL will be in the primary and the secondary. So in the primary side, it is 3 kilovolt, right? So IL, so I can calculate IL primary, ILP, line current primary, it will be 900 divided by root 3 into the primary side voltage. Remember, the rating is apparent power is also in kVA and the voltage is also kilovolt. So kilo will be cancelled. This will be divided by 3. So this will be equals to 300 by root 3, that is 100 root 3 ampere. Okay, this is the line current. And remember, the delta side is remember the primary is delta connected. If it is delta connected, the phase current of the primary would be this divided by root 3, that is 100 amperes. That is the phase current of the primary. I need the phase current. Okay. Similarly, for the secondary, I can do the same thing. For secondary, the phase current. So these things I can put here, right? So this can come here. I phase for the secondary, right? So first of all, let me calculate the I line for the secondary. It will be again kVA upon root 3 into VL, and this time your line voltage is root 3 exactly. It is root 3. So this is root 3, and so this will be equals to 300 amperes. Okay, and what is your phase current? So because it is star connected, we know in star line and phase currents are same. So this will be 300 amperes only. Now we got our values. I will just simply need to calculate the copper loss because it is at full load only. These are all full load currents, right? So PCU FL at the primary, this will be equals to your current whole square into the winding resistance, that is 0.3. Also, don't forget this is the per phase loss, right? To get to three phase loss, because all the three phases will have loss. What will I do? Because it is a balance system, I will multiply 3. So don't forget to multiply by 3. That is the important part. Don't forget to multiply by 3. It's a 3-phase system. Right, so 100 whole square into 0.3 into 3. So this is 9000, or I can say 9 kilowatt on the primary side. Similarly, on the secondary side, same thing will be applied, just the numbers will change. This will be 3 into the current square, that is 300 whole square, and your resistance also on the secondary side is different, that is 0.02. Okay, so let me compute this. This will be 300 square into 3 into 0.02, that is 5.4 kilowatt. Okay, so yeah, what is the overall copper loss? What is the overall copper loss? Overall PCUFL, both including the primary and secondary, powers can be added, right? Powers can be added. It will be basically 14.4 kilowatt. So your overall efficiency would be, hold on a second. Overall efficiency will be 900 divided by 900 plus 14.4 plus the iron loss, that is 10 kilowatt, into 100. into 900. So this will be 97.36%. Okay, so 97.36% would be an answer for the question. Although I have solved in a very slow manner, but this will not take you much time to solve. Let's solve the next question. So a single phase 5 kVA, this transformer has a secondary terminal voltage of 95 when loaded. The regulation of the transformer is. So your regulation, right, is V no load minus V full load upon V full load. Like it's a very basic question into 100%, right? So what is the full load voltage? Now it is talking about the secondary. So I will choose the secondary terminal voltage. Secondary full load voltage is 100, right? So secondary no load voltage is 100. So 100 minus so yeah, nodal voltage is 100, then when it will be loaded, so obviously voltage will reduce, that is 95 full load voltage upon the full load voltage, that is 95, right, into 100%. Actually, one thing is they should mention properly what do they mean by regulation, because the formula for regulation sometimes is bit fraud. Okay, here they have chosen it to be no load, so sometimes we use V no load minus V full load by no load, but actually this is the proper formula, this is what we will use always, but sometimes they are dividing by 100, but they should properly mention it, in the question. That's what I take away from this, although it comes out according to me by default, if nothing is mentioned you will use this formula, okay, but yeah, you should use this formula, but if you see that answers are matching here almost, so you'll obviously pick option C, but the thing is they should mention properly what kind of voltage regulation they are mentioning about. There are two kinds of regulation. This is the regulation, and the other regulation is V no load minus V full load by V no load. You don't know which formula you will use. Mostly this is the default formula if nothing is mentioned. So according to me the answer should be this, but this one is almost matching, so I will choose this option. Let's solve the next question. A single phase transformer rating of 25 kVA, okay, supplies a 12 kilowatt load power at a power factor of 0.6 lagging. The additional load at unity power factor in kilowatt that may be added before this transformer exceeds its kVA rating. So how much like active power I can add, how much load I can add to this transformer uh, just before it exceeds its own rating. So currently if I have, so what they are asking is currently what is the apparent power that the transformer is delivering. It is P plus P1 plus, let's say S1 equals to P1 plus JQ1, right? It is a lagging power factor. Now what they're telling me that, tell me the maximum limit of my apparent power of the transformer that it is delivering. That P1 is there plus an extra Px active power load, because I am only adding active power because it is operating in unity power factor, and the reactive power remains same. This will be JQ1. Now if I calculate the magnitude of this, right, so your S2 is the maximum power limit, that is 25 kilovolt. Magnitude of this would be P1 plus Px whole square under root plus Q1 whole square. This should be equals to 25, equals to or less than 25. That is the limit, maximum limit that I can go. If I give any active power beyond this, obviously the rating I will like I will have to provide the apparent power beyond the rating of the transformer. That is not possible. Transformer will not be able to provide that. Now, so I need to calculate this P1 Q1 values, right? So what is P1 P and Q1? P1 is given to me 12 kilowatt. What is Q1? Q1 would be simply, you can use simple formula, right? Q upon P is equals to tan phi. So it's a power triangle. I will not explain all these things. I am expecting you already know all this. So Q will be equals to, or Q1 will be equals to P1 tan phi 1. So yeah, Q1 will be equals to P1 tan phi 1. So what is Q1? Q1 is 12 into tan of phi 1, tan of phi 1. So what is 0.6 cos inverse? It is 53.13 tan of this into P1. P1 is 12. So that would be 16 kVA. Okay, so Q1 is P1 1051, right? That is 16 kVAr. Now now yeah, now I know P1, I know Q1, right? So I will put the values over here. I know. So and the at the boundary condition, your 25 will be equals to under root of P1 whole square, that is 12 plus Px, that is what I have to calculate, plus Q1 whole square, that is 16 whole square. Everything is in kilo, so kilo will be sorted, no problems, units are okay. Now we can square both sides. This will be 625. I will subtract this whole square plus 625, then I will take the under root, then I will subtract 12, and that will give me 7.2 21. They have asked me to round off to 2 decimal places, so it will be your Px. If you solve this equation, it will be 7.21 kilowatt, and this will be your answer for the question. Pretty easy, pretty simple question. You don't have to take much stress in these kind of questions. Let's solve the next one. A single phase 4 kVA 200 volt 100 volt 50 hertz transformer emitted this, no load losses. So these are my no load losses. Okay, so P no load losses are mostly the iron losses, correct? So that is 450 watt. Okay, cool. When the high voltage winding is excited by, okay, these are pretty important information. When the high voltage winding is excited by, so VHB is equals to 160 volt 40 hertz, then the no load losses are found to be, basically the iron losses are found to be 320 watt. Okay, with the same high voltage. So this is the first case. In the second case, that they're telling me that my VHV same high voltage winding has been excited by a voltage of 100 and a frequency of 25 hertz. What will be the no load losses in this case? So pretty interesting question actually. So do you remember what things does my transformer no load losses depend on? So if you remember one thing, that my no load losses in the transformer is combination of two. One is the actually this is not the called as the one is called as the hysteresis loss. Another is one is called as the eddy current loss. Now, do you remember what does your hysteresis loss and your eddy current loss depend on? So if you remember it correctly, your hysteresis loss was some kh bm raised to the power of x. If nothing is mentioned, you will assume x only because it won't matter ultimately, into f. Okay, and your eddy current loss was ke, just give me 1 second, yeah, ke bm square into f square. Okay, now the thing is, what does your bm is the maximum flux density. It is proportional to v by f, right? Because it is proportional to flux and flux is proportional to v by f, right? And if you see, observe, v by f is always constant. In the first case, what is v by f, right? Where uh, so the has no load loss of 450 for this transformer. So if I consider the high voltage winding, so v by f here is 4, and if I consider here again the high voltage winding, v by f is 4, again here v by f is 4. So in all cases v by f is constant, so flux is constant, flux density is constant. So ultimately I can write this thing, that your iron loss is basically some constant a into f plus some constant b into f square. That's all. This thing you have to remember. This is a very important thing. This thing you have to remember. We got our iron losses. Now we'll just compare, right? So in the case one, what was the iron loss? 450. What was the frequency? In the case one, it was 50 hertz, right? So basically, case one 450 will be equals to a 50 into a plus 2500 into b. In the case two, the iron loss is 320 and the frequency has changed to 40 hertz, right? So 320 will be equals to 40 into a plus 1600b. Okay, so this will be subtracted, so this will be 130. 130 will be equals to 10a. Okay, let me eliminate one of the variables here. So let me just divide by 10. That will let me divide by 5. Oh, sorry, 20. Can I divide by 20? No, I cannot divide by 20. But I can divide by 10, right? Yeah, let me divide by 10. So this will be 45 equals to 5a plus 250b. Okay, I can divide by 50. Sorry, I can divide by 50, right? Yeah. So this will be 90 equals to a. If I divide by 50, this will be 50b. Correct. And in the bottom, what can I divide? I can divide by 40, right? So this will be 40. This will be 8 equals to a plus 40b. Okay, so now I can subtract these two. This will be 1, that will be equals to 10b. So b would be equals to 1 by 10. So b is 1 by 10. And what about a? So a would be, from the previous equation, a would be 4. Right? B is 1 by 10, a is 4. So yeah, we got our a and b. So now I can easily, so I have to calculate the case for, I have to calculate the iron loss for the third case. In the third case, again, v by f is constant, but frequency is 25. So it will be 25a plus 625b. So 25 into a, that is 25 into 4 plus 625 into b, that is 1 by 10. So it is basically 62.5 plus 100, that is 162.5 watts. This will be your answer for the question. Okay, that's how simple it is. Mostly questions will come simple only. Now again, something similar came in GATE 2021. In a single phase transformer, total iron loss is given at nominal voltage, that is at full load voltage and frequency, right? So the voltage and frequency, so at 440 volt and 50 hertz, the voltage, the iron loss is 2500 watt. At uh, at 220 volt and 25, again, do you see the ratio same? Yes, the ratio is same, and mostly the ratio will be same. If the ratio is not same, then the flux density also will change. Then you have to solve the question accordingly. Your iron loss is 850 watt, and now at nominal voltage and frequency, the hysteresis and eddy current losses are. So basically they're asking me what is the at nominal voltage, what is the eddy current and hysteresis loss. So again, the same thing, that my iron loss is dependent on the hysteresis loss plus eddy current loss. Again, we see that v by f is constant, so it will be basically some a into f, just like the previous question. So if you could not understand the previous question, you will not be able to understand. So you go back to the previous question, there I have discussed this about more. So if you are directly watching this solution, right, go back to the previous question. So a into f plus b into f square, that is my iron loss. So iron loss is 2500, that is equals to into f, that is 50, plus 50 square, that is 2500 b. And in the second case it is, so if I divide by 50 here, this will be 50 equals to a plus 50b. And in the second case, this will be 850 equals to f is 25, right? So 25a plus 25 whole square, that is 625b. So if I divide by 25, this will be 25 into 4 into 8, 4 into 8, 32, 32 plus another 2. So this is 34 equals to A plus 25B. So I can subtract these two, right? If I subtract these two, this will be 16 equals to 25B. So B equals to 16 by 25. Why did you do 16 by 25, right? So the A will be, A would be, so what will be A? So I can put in this equation, right? In this equation, if I put B equals to 16 by 25, this will be 16. 16 will go on that side, so it is 8, 18. So A is actually 18. Cool. So A is 18. We got A and B. So basically, they're asking me what is the hysteresis loss and the eddy current loss. So this part will be at nominal voltage and frequency. This will be the hysteresis loss, and this will be the eddy current loss, right? So my pH would be equals to 50, would be equals to 15 to A. So 15 to A would be basically 5 into this is 900. Yeah, 900. And your eddy current loss would be 16 divided by 25. So this is 100. So that is 1600. So 1600 and 900, that is, yeah, this one. So 900 is the hysteresis loss and 1600 is the eddy current loss. You could have, instead of using constant, you could have directly written here like this will be some this, and okay, it's okay, you use this method only. There is shortcut as well, you can think of shortcut, but yeah, this is the basic method that you should always solve with. Okay, let's solve the next question. So we have been given this ear core radio frequency transformer as shown in has a primary winding and a secondary winding. The mutual inductance between the winding is also shown. Okay, the mutual inductance M between the windings of the transformer is, what is the mutual inductance between the windings? That is what I have to calculate. So I'm observing that I'm getting a 7.3 voltage peak to peak here, and here I'm getting a 5 voltage peak to peak, correct? Okay, so how do I calculate this? And this voltage is not given, input voltage is not given. Okay, mutual inductance between the winding. So I'm just thinking, how do I calculate this? So I know the peak voltage, right? Yeah, what we can think of is there isn't any load connected, right? So what is happening? How am I getting this voltage? There isn't any load connected here, right? So this I2 current, let's assume this is the current I1, correct? And this is the current I2. So there is no current in the I2. So there is no voltage developed due to its own self inductance. Whatever voltage I am getting, it is only due to the mutual inductance. Okay. So again, current is entering from one of the terminals, one of the dots, and current is leaving the dot, right? Although it does not matter because here I2 is technically 0. So I can assume this. I can assume current to enter like this because I2 is 0. I can assume any direction. Right? That will be easier for me because this will be plus minus. This will also be plus minus. Then easily my voltage in the secondary becomes L di2 by dt. Now again, in one of the dots of the coil, current is entering. In the other coil as well, the current is entering the dot, right? So in both the coils, current is entering the dot. Then the effect of mutual inductance will be positive. That is M di I1 by dt. So this will be voltage developed in the secondary due to the what do you call, due to the primary current. Okay, so they have given me the voltage is 5 volt peak to peak. This voltage is 5 volt peak to peak, right? What does it mean 5 volt peak to peak? Basically, let's assume that my resistive voltage is some sinusoid voltage, right? So it is 5 volt peak to peak. So this will be 2.5 minus 2.5. So 5 volt peak to peak. The difference between the peak to peak is 2.5 minus 2.5, right? Okay. Now, what we can do, this is my voltage across the resistor. What is the current across the resistor? IR, it will be VR by 22, correct? So what is VR? This is nothing but Vm sin omega t, that is 2.5 sine. I have assumed this to be sine. It won't matter if you assume this to be cos as well. You will arrive at the same solution. Don't worry. So sine omega. Omega is dependent on this, right? 2 pi f. So I will just write omega here just for uh, clean notes. Like, but you know, omega is 2 pi f. That is 100 kilohertz. 2 into pi into 100 kilohertz. Okay. Now your current, right? IR is nothing but the I1. This is the same current, right? Again, no current is flowing from here. It is same current. So your IR is nothing but your I1. Okay. IR is nothing but your I1. So this is your I1 of t. Correct. This is my I1 of t. So that is equals to basically VR, that is 2.5 Vm sin omega t by 22 into sin omega t. I don't care about this for now. Now I'm getting a peak to peak voltage of 7.3. So let us come to what will be the V2. So this is 0, right? Because I2 itself is 0. I2 itself is 0. So di2 by dt also will be 0. But this part will not be 0. What will be this? So V2 will be equals to m into di2 upon dt. Sorry, di1 upon dt. I1 is not 0. So this will be this voltage. I have to differentiate this voltage. That will be, if I differentiate this, this will be omega into 2.5 by 22, and of course Vm. Okay, 2.5 is already there, right? 2.5 by 22 is already there. That is the constant into omega into cos of omega t. Okay, and this will be a cos function. Okay, it won't matter. Ultimately, your final answer won't matter. Trust me. So it will have some peak to peak. So they have given me this peak to peak value. What is this peak to peak value? That is 7.3. So what is the peak voltage? It will be peak to peak by 2. So this whole thing is 7.3, right? Peak to peak value they have given me as 7.3. So this thing will be what? 7.3 by 2. So 7.3 by 2 will be equals to this peak of the cosinusoid. So this is equals to m into omega. Omega is 2 pi into 100 kilohertz, 2 pi f, into 2.5 by 22. Okay, so from here we can actually calculate the value of your m, right? I'm sorry for the background noise. This divided by 22 into 10 raised to the power of 5 into 2 into pi. Okay, which is coming out to a bit higher side. Okay, they have asked in microhenry only, right? So they have asked in microhenry actually. So I can divide this 10 raised to the power of 6. Remember, they have asked in microhenry, so convert accordingly. This into 7.3 divided by 2. So it approximately, your m approximately comes out to be 51.12 microhenry. So I hope you can convert the units properly, and if you convert the units properly, you will get your answer. Although at first glance this question seems very difficult. How will I calculate m2, right? I don't know anything. They have given me no information. But still, if you know the basics well, you will be able to convert. You will be able to calculate everything, right? Because I know, although there is no current in the secondary, you will say how the voltage is getting developed. The voltage is getting developed. Of course, there is some mutual inductance. Of course, there is some flux that is flowing through the core of the transformer. That's why the voltage on the secondary, although there is no current, will be developed. Okay, so answer would be 51.12 microhenry. Yeah, let's just start with the next question. So a single phase transformer has a magnetizing inductance of 250 millihenry. So its magnetizing inductance is 250 millihenry. The core loss, this is the magnetizing inductance, right? Rm. The core loss resistance is 300. So basically they are talking about the shunt branch, right? So if I know the frequency which they have told me, so I will be able to comment about the magnetizing reactance, and the obviously resistance already they have given me, that is equals to 300 ohms. When excited with a 230 volt 50 hertz supply, 230 volt 50 hertz supply, at the primary, the power factor of the input power factor of the input current drawn with the secondary open circuited. So essentially what is happening is, let's say this is the winding resistance, right, and secondary is open circuited, right. If secondary is open circuited, that means this current is 0. So if I approximate this, right, this current also, like this resistance is very small compared to this. So these two components are essentially in series, and this is very dominating. So essentially I can simply neglect this voltage drop. So this voltage drop will be approximately equal to 0 only compared to this one. Okay. So basically I actually have to calculate the power factor. That's all. They are asking me what is the power factor of the input current drawn. So it is essentially asking me what is the power factor of this circuit. That's all. That is what they are asking. What is the power factor of this circuit? How do I compute the power factor of this circuit? So okay, so we know like this is parallel branch. So what I can say is the conductance will be on the x-axis, that is 1 by 300, and the susceptance, right? So this is actually plus j xm, right? If I take the inverse, this will be in negative side, right? So that's why it will lag basically. So susceptance, the inductive susceptance, it lags, correct? So this will be 1 by xm, and the angle that I am interested in is the angle this from the x-axis, that is the power factor angle, correct? So what will be this value? This will be, so your tan phi will be 1 by xm divided by 1 by 300, that is 1 by r. So in parallel circuit, if you remember, it was not r by z, it was z by r, something like that, right? It's just the inverse in parallel circuit if you remember it properly. So this will be hold on a second, this is 1 by 300 tan phi height upon the base, yes. So this will be 300 by xm. So I need xm. Xm is what? Xm is basically 2 pi into f. F is 50 hertz into the magnetizing inductance, that is 250 millihenry. So 250 into minus 3. So this will be 2 into 100, 100, 2500, 0. So 3 zeros are gone anyways. So okay, it is only pi into 25, that's all. So pi into 25 is 78.54. So so this into 300. 3.82, and if I do the tan inverse, that is 75 degrees. Phi is 75. So your power factor, right, is cos of phi, right? So cos of this, your cos phi would be 0.253. Okay, so 0.253, what they have asked me to round off to 2 decimal places, so it will be 0.25. This will be your answer for the question lagging. Let's solve the next question. This is the next question. A single phase transformer has a maximum efficiency of this. The core loss is 80 watt, right? So efficiency maximum, let me add a question, let me add a page. Is 98%, that is 0.98. So in IN they are asking questions from machines. So 0.98, the core loss are 80 watt. Core loss or iron loss is 80 watt. Equivalent winding resistance as seen from the primary, okay, which includes the secondary as well. So your winding resistance are equivalent, which includes both the primary and secondary, is 0.5 ohms in the primary side, right? and the rated current in the primary side is 25 ampere. The percentage of the rated input current at which the maximum efficiency occurs. So they're asking me what is the percentage of the rated input current. So my maximum efficiency will occur, let's assume that at I max, and the percentage input current, right, that is IFL full load, and I have to calculate the percentage of this, that is 100%. So I have to calculate the current at which the maximum efficiency occurs, I max upon IFL. So this is nothing but the X. If you remember this thing, right, I max upon IFL, it is nothing but X into 100%, right? You can write, it's okay if you don't want to write X, you can write this as well, no problems. But we're more comfortable. I know most of you have studied machines and you have seen this particular thing somewhere, right? So X is basically the loading with respect to the full load current. So X is basically the, now this will not be X, this will be X max, the loading where I get the maximum efficiency. Do you know when we get the maximum efficiency? When the coal loss is equals to the variable loss, correct? So our maximum efficiency is 0.98, right? And efficiency formula is what it is. Now have they told us anything regarding the power factor? So okay, they have not told us anything regarding the power factor. So your efficiency formula is XS cos phi divided by XSR cos phi plus X square into PCUFL, the full load copper loss, into X square. So I will not explain this formula because I hope you have seen this formula multiple times. In today's lecture only we have solved a question like this. So I will not explain you this formula. Plus the coal loss, that is always constant, that is independent of load, where X is the loading factor. In our case, they have not mentioned anything. So we will get the maximum efficiency when cos phi is 1. Okay, you get the maximum efficiency when the cos phi is 1, you will assume that. So because nothing is mentioned, you will assume unity power factor. So if you assume unity power factor, this will be, so the maximum efficiency occurs when your variable loss is equals to the constant loss. So variable loss will be equals to constant loss. So this will actually be X max at a certain load into SR divided by X max into SR plus 2 into P core or P iron, whatever you want to say, both are same thing. This will be equals to my maximum efficiency, that is 0.98, right? What things I know? I know what is the, do I know? Okay, I don't know what is the rating of the transformer. Okay, I don't know what is the rating of the transformer. Okay, I don't know what is the rating of the transformer. But I don't need this information actually, right? What I know that at maximum efficiency, my iron loss will be equals to my copper loss, full load copper loss, right? Now what is the full load copper loss? Full load copper loss will be full load primary current into the equivalent resistance. So PCUFL will be IP whole square into the equivalent resistance, that is 0.5. So it is 25 whole square into 0.5, that is 312.5 watts. So PCFL is 312.5 watts. PI is 80, right? So this will be 80 equals to X max whole square. So at this fraction of loading, the maximum efficiency occurs into PCFL. PCFL is 312.5 watts. So this into 80 whole under root, that is, so your X max comes out to be 0.5. So it is 0.5. So 0.506, and they have asked me at what percentage. So X max is 0.5, so it will be 50.9%. It's pretty simple, pretty straightforward. Sorry, 50.6. What I'm doing, 50.6%. Right, so you can see that is present in the option B. So although I was stuck here, right, in the exam hall, I might be using this information. Then I saw that okay, I don't know the so this SR is the rating of the transformer in kVA. I don't know this. So let me pause this. Let me see what if I can solve without this information. Then I checked here. Yes, I can. So what I need to equate these two, and I already know the iron loss. I need to calculate this. So if I need to calculate this, I need to find out what is PCUFL. That is the full load copper loss, and I can easily calculate the full load copper loss from the information given here. Okay, so that's how you solve this question. Let's solve the next question, right? So the next question, when the winding CD of the single phase 50 hertz two winding transformer is supplied from a AC source, okay, current source. So CD is supplied. The rated voltage developed here is this 200 volt and 50 hertz is obtained in the open circuited terminals. The cross sectional area of the core, so AC, is 5000 mm square. The average core length traversed by the mutual flux. So the length, right, mean length L is 500 millimeters, the average length. That is basically the mean length of the core. That's all. The maximum allowable flux density B max equals to 1 Weber per meter square, that is 1 Tesla. The relative permeability of the core mu r is equals to 5000. The leakage impedance of the winding AB, the leakage impedance of the winding AB and winding CD at 50 hertz is this. So leakage impedance, basically it is basically the series resistance and the inductance. So at 50 hertz, the winding AB, ZAB, right, equals to 5 plus J 16 pi, and your ZCD equals to 11.25 plus J 36 pi. Now, how do I calculate the self-inductance? Now, one thing you have to keep in mind here, what is my self-inductance? Self-inductance, right? Actually, this should be defined properly. It is actually equals to the inductance of the winding at the primary plus the mutual inductance referred to the primary. So, this M is referred to the primary. Now, what is the leakage reactance or leakage inductance referred to the primary? So, this will be equals to, so I know the impedance of the ZAB winding, right? So from this I can easily calculate the leakage inductance. So this will be 2 pi into F. F is 50. Actually, I don't even need to calculate. They have directly given me. It is 0.16. It is 0.16 Henry. Okay, that is what my leakage inductance is, and in millihenry it will be 160 millihenry. Now, what about your mutual inductance? Your mutual inductance, right, will be equals to, so whatever is the mutual flux, okay, what is, how do I calculate the mutual inductance? So hold on a second. Mutual inductance will be the leakage. So this, right, this will be equals to, if you remember the formula for inductance, it was N square by reluctance. So mutual inductance will be N1 square, because I am calculating the, at the primary side it will be N1 square by reluctance of the whole core, because the flux, right, this is the mutual flux due to the reluctance, due to the mutual flux. So that is the whole core, the flux is traveling throughout the core. So I need to calculate N1 square and the reluctance. Do I know N1 square? No, I don't know N1 square. I don't know the N1 square, correct? How do I calculate N1? What I can do is, I know this formula, the voltage developed VAB will be equals to, this is RMS, so it will be root 2 into pi into F into phi m into root 2 pi into F into phi m into N1. So there are 5 terms, these are the 5 terms that I require. So I know everything, I know VAB, RMS, that is 200, I know root 2, I know pi, I know F, do I know phi m? I will see. I don't know N1, that is what I have to calculate. So phi m will be Bm into A. Phi m, the peak flux will be Bm into A. Now they have already given me the B max, maximum flux, that is 1 Weber per meter. I just need to multiply by area. So area is 5000 millimeter whole square, or I can say in meter square it is 5 into 10 raised to power minus 6. So I can replace all the variables here. Just give me 1 second. Into 5m. 5m is Bm into A, that is 1 into A. A is 5 into 5000. 5000 into 10 raised to power of minus 6, and you have to calculate N1, and VAB is 200. So let me solve this particular thing. So from this I can actually calculate my N1. So N1 would be 200 divided by 5 into 10,000 or 1000, sorry, hold on a second. 200 divided by 5 into 1000 divided by 50 divided by pi divided by root 2. So your N1 comes out to be around 180. You will obviously choose the integer value. N1 cannot be in like a fraction. So N1 will be 180. Okay, we got our N1. I also need the reluctance value of the core. So reluctance value of the core will be LC, length, mean length of the core upon mu into AC, area of the core. Correct. So mean length of the core is given to me in millimeters, that is 500. So in meters it will be 500 into 10 raised to the power minus 3 upon mu naught mu A. So mu naught is 4 pi into 10 raised to the power minus 7, and mu R is 5000. The reluctance of the core, relative permeability of the core is 5000 into area. Area is basically your what area is this, right? This is my area. This is my area. 5000 into 10 raised to the power minus 6. 5000 into 10 raised to the power minus 6. So yeah, this will anyways be cancelled. This will be cancelled. This will be 25. So let me just rearrange few things. This will be 0.5 upon 4 pi into 10 raised to the power 7 upon 25. Correct. So 0.5 upon 4 okay into 1000 okay, this is 1.5 into 10 raised to the power 4. So your mutual inductance, right, will be equals to 180 whole square, right, divided by the this value 1.59 into 10 raised to the power 4. Okay, let me calculate this into 10 raised to the power 4 into 180 whole square. So that is equals to 2.03, approximately 2.0357. Now this is in Henry, right? Everything is in Henry, but they want me to compute this in millihenry. So this will be multiplied by 1000, that is 2035.75 millihenry. And so your overall self inductance will be this mutual inductance plus the leakage I guess was 160. So your overall self inductance will be 2195.75 Millenary. This is a pretty good question, but not that simple. You have to understand a few things. So yeah, this was a good question. Okay, this is your answer. Let's solve the next question. So here we have given the short circuit test is conducted on a single phase transformer by shorting its secondary. The frequency of the input is 1 kilohertz. The corresponding wattmeter reading of the primary current and primary voltage are this 8 watt, 2 watt. So the SC test is performed in the uh, high voltage. So shorting its secondary. So secondary, okay, they have not discussed exactly. So they are shorting the secondary. The power consumed in the short circuit test is 8 watt. The current, short circuit current is 2 ampere. The short circuit voltage is 6 volt across the whole winding. Assume that no load losses and no load currents are negligible. The core has linear magnetic characteristics. So core has linear magnetic characteristics. That basically means that the flux. So actually what we do, we have this BH curve, right? So your H is proportional to current and its B is proportional to flux. So as I increase my current, the flux also will increase linearly. That is what they mean by linear BH curve. Keeping the secondary shorted, the primary is connected to 2 volt RMS now. Primary is connected now, the voltage that is giving, it is 2 volt RMS. Frequency is same. So here also frequency was 1 kilohertz. Here also frequency is 1 kilohertz only. The source in series with a capacitor, that is 1 by 2 pi under root 5 millifarad. The primary current RMS will be, what is the primary current? So from this I can easily calculate. If it has linear characteristics, right, what will happen? The inductance will remain constant, will remain same, does not matter whatever the current is. So from this information, right, short circuit test, what happens? We basically model the winding. So we have the equivalent winding. So this will be R equivalent and I will have a X equivalent, and we simply model the winding. So we got the short circuit current, right, and I know the power. So power will be consumed by the winding resistance. So it will be ISC. So your power will be equals to ISC whole square into the R equivalent. Okay, so PSC will be equals to 8 into ISC whole square, that is 2 square, into R equivalent. R equivalent is I that is what I have to calculate, right? R equivalent. So your R equivalent would be equals to 2 ohms. That is what your R equivalent is equals to. What about your X equivalent? So I know I have given VSC and ISC. So this is the voltage drop across the whole winding, that is 6 volt, and the current is simply 2 amperes, right? So I can easily calculate what is Z equivalent. Z equivalent is equals to VSC upon ISC, that is 6 upon 2, that is 3 ohms. So I can easily calculate what is my X equivalent. X equivalent will be Z equivalent whole square minus R equivalent whole square. So this will be equals to, so 3 square 9 minus 4 under root. So this is actually under root 5. Something interesting will happen, I feel like some resonance or something will happen. This is my X equivalent, right? Now what they are doing with the winding itself, they are connecting a capacitance. Now what is the reactance of this capacitance? So reactance of this capacitance, Xc would be, now remember this is plus J, right? There will be plus J. Xc would be equals to 2 pi into F. F is 1 kilohertz. So it will be 2 pi into F, 1 by 2 pi F, right? So 1 by 2 pi F. So 1 divided by 2 pi F. 2 pi into F is 1 kilo and milli is there. Kilo milli will be cancelled. 2 pi Fc. So I will have 1 by under root 5. Here, right? That's all. 2 pi will be multiplied. F will be 1 kilohertz. 1 milli will be cancelled. So ultimately your capacitive reactance is also under root 5. But they are opposite in nature. So now how the circuit will look? I'll have this resistor. I'll have this equivalent leakage reactance of the winding, and then I will have the capacitive load, which will provide a reactance, capacitive reactance of same value, but opposite in nature. But R equivalent will still be 2 ohms. What are they asking now? Now they are asking me what is the primary RMS current. It is very simple, right? Whatever is the voltage, because ultimately this will add up to 0. This will add up to 0. So whatever is the voltage, it divided by the 2 ohm resistor. So RMS current primary will be voltage, that is 2 volt upon the 2 ohm resistor, that is 1 volt RMS, because 1 ampere RMS. Because your voltage was RMS, so this current also will be RMS, because this, right, this is 2 volt. 2 volt is in RMS, so whatever derived current also will be in RMS, that is 1 ampere. So 1 will be your answer for the question. Okay, let's solve the next question. So which one of the following, so this actually was wrong because here the dot polarities were not proper actually. Okay, so they're asking which one of the following represents the possible polarities in a single phase 2 winding transformer, where Vp is the applied voltage, E is the induced voltage in the primary, Vs is the open circuit voltage in the secondary, and Es is the induced voltage in the secondary. So it cannot happen that if the dot is with negative sign here, right, for the induced voltage, here also it will be with negative sign. No, that was the meaning of dot, right? Dot was supposed to tell me that if I have negative here with dot, this also will be negative. So this is anyways wrong. Okay, see, if you have positive here with dot, I should have positive here with dot. That was the like, if you don't understand in machines full course, we have already taught everything, so you can go into the machines full course and learn from that. So here as well, if I see dot here, this is correct, this is fine. Okay, but what is the problem? What is the problem here? This is again incorrect, so with plus dot should be there, this is again incorrect, right? So if Vp is the applied voltage, so Ep will oppose it, yeah, that is correct. So this is plus, that is fine, right? And this is also dot. So now let us see the flux direction here. So although the like dot should be plus, that is fine, but let's see the flux direction. Okay, so if I see that if I am placing the dots here, right, that basically means what? Let me check the flux direction. So this shortcut I have already taught in my full course. So if I place a dot here, so if I see that the current, right, current will be flowing from here, it will come back here, here. So flux direction would be somewhat this, like this. This will be the flux direction, correct? Just right hand rule. So flux will go like this, and if flux goes like this, then the current direction will be somewhat like this, right? So what will happen is, and if current direction is this, and this, so now what will happen is, like, yeah, this flux will try to develop a current here, but due to its own inductance, this will oppose the change. So the opposition will come and it will develop a flux in the opposite direction, in this direction. So right, in the bottom direction basically, correct? If it develops a flux in the opposite direction, so current direction would be something like this, right? Because it is trying to develop a flux in the opposite direction. So right, so current direction is this. So actually this should be plus, this should be the dot, not this. How can I identify? So you can see the winding orientation, right? If the winding is behind the transformer and here I have placed the dot, here also the dot should be behind the transformer, right? It should not be in front. So this is a shortcut that I have taught in my full course. If you are not able to understand the dot polarity, please go into the full course and there check. I've like explained for like 30 minutes there, so you can watch that video and you can understand the dot polarity. Okay, okay, so here also again the dots, like the dots and plus are placed mistakenly, so they are incorrect. So all the 4 diagrams are actually incorrect, and in 2024 this was an empty. Let's solve the next question. A 50 kilovolt 50 kilo kVA transformer has full load efficiency of 95%. Now at full load, and power, unity power factor, right? So x is equals to 1. So I hope you understand what is x and unity power factor. You can go back to the previous questions, there I've explained this particular part. So coal losses are negligible, so basically your iron loss is 0. Okay, we get an efficiency at full load. This the efficiency of the transformer at 75% of the load and 0.8 power factor. So what is efficiency equals to? Efficiency is equals to, so efficiency is equals to x SR rated kVA into cos phi upon x SR cos phi plus x square into PCUFL plus iron loss, but in this case iron loss is 0, so it won't matter, right? So in the first case, I already know the efficiency, that is 0.95. I already know that it is operating in rated load. I already know the kVA, that is 50 kVA, divided by cos phi, it is unity power factor, divided by 1 into 50, this is also 1, right? This is also 1, plus x square, again it is 1 square into PCUFL, correct? So if it is PCUFL, now I can easily calculate the PCUFL. Why? Because I will need PCUFL while calculating the efficiency at 75% of the full load. So that is what I'll do. So from this, if I calculate PCUFL will be equals to 50 by minus 50 minus 50. So it is 2.63. 2.63 kilowatts. Remember, everything is in kilo, right? This is in kVA, this is in kVA, so this also will be in kilowatts. So 2.63 kilowatts. Now I will calculate the efficiency at 75% of the load, that is when my x is equals to 0.75. So this will be 0.75 x into kVA, that is 50, upon 0.75 into 50 plus whole square into PCUFL, that is 2.63. This plus 15 to 0.75, this into 0.75 into 50. So efficiency comes out to be 0.96, and I think they have asked in percentage, right? Yeah, percentage. Okay, one small mistake. Don't forget, they have asked in power factor 0.8. So don't be in a hurry. So you have to calculate in 0.8 power factor, right? So don't forget, you have to include the power factor as well. Okay, just a small mistake. So this will be 0.75 into 50 into 0.8 plus 0.75 whole square into 2.63. So this is 95.3. 95.3 percentage. Okay, 95.3 percentage. That is your answer for the question. Let's now move on to the next question. So here we have been given the transformer connections are given here. It's a 3-phase transformer, and the primary to secondary turns ratio is 2/1. Okay, so if this coil has 2 turns, this will have 1 turn, right? Coil to coil, not the voltage to voltage. If the IA plus IB plus IC is 0, they're talking about this current, it is 0, and the relationship between IA and IAD. Okay, so this is, they're telling this is a balanced three-phase system. So this is star, right? This is star. So in star, line current is equals to phase current. So if so these are the coil ratios, right? So if, okay, IO plus IB plus this IC is this current. So they are asking me this current and this current relation. So IA plus IC plus IB is 0. Basically, it is a balanced system, right? Now, how do I find out the, so I know the ratio. So what is the coil current here? So the coil current is IAP. Let's assume this is the coil current of the primary side. And what is the coil current here? It is IA, right? So the ratio between IAP and IA will be according to the coil turns ratio. Okay, this thing I have taught in the full course. You have to go and watch the videos. So inverse ratio, it will be inverse. The current is the inverse relation. So it will be 1/2. Okay. Okay, I got this. So IAP is nothing but capital IA. I got this value, but I don't want IA. What do I want? I want IAD, right? I want IAD. How can I calculate IAD, right? So the phase sequence is ABC. The phase sequence is ABC, correct? So what will be IAD? So this is delta system, right? This is delta system. So certainly if I just compare the magnitudes, your IAD will be basically √3 times IA. Certainly this will be the case. Okay, in the secondary side. So your IA will be equals to, I'm only considering the magnitude, I'm not considering about the phase for now. So magnitude of IA will be IAD by √3. So I can just compare the magnitudes right now. So magnitude of IA by magnitude of IA, that is, so magnitude of capital IA is on the primary side, okay, and magnitude of I small a is on the secondary side. This will be small ed by √3, that is equals to 1/2. So what do I have to calculate? Capital IA by IAD. So this will be equals to basically, so your magnitude of IA by magnitude of IAD will be equals to 1/2 √3. Okay, so we got this value. Now this is certain. So either this will be true, this will be true, this will not be true, right? But what about this lag lead? How will I calculate this? So there is a way to remember it, but if you don't want to remember, you can directly solve in the exam hall as well. So it follows the phase sequence of ABC. So A will come first, then B will come. So ABC, right? So ABC basically means A will come first, then B will come, then C will come in 120-degree sense in clockwise fashion, right? So first A will come. Sorry, hold on. Sorry. So if I have A equals to IA is equals to IA 0 degree, then your B will be IB will be equals to same value but 120-degree leading. It will lead 120, right? So your IB actually will be here. It will lead here. This is your IB, this is your I small a, and this is your IC. Correct? Now what do you have to calculate? You have to calculate IAD. IAD is nothing but, so this is the incoming current, this is the outgoing current. So it will be IA minus IC. So IC will be somewhere here, minus IC will be somewhere here, correct? So this is 120, correct? This whole thing is 180. So this thing will be 60, correct? This thing will be 60. Okay. Now remember these two currents, right? IAP primary and IA, this will have no phase difference. This will have no phase difference, okay? But the phase difference between IA and IAD is different. So the addition of these two, right? This is what minus IC. These two will give me IAD, and this is a shortcut that if two vectors have equal magnitudes of length and their phase difference is 60 degrees, then the resultant will be in the middle, that is at 30 degrees, and it will lead from the reference value, that is IA. So basically your IAD its magnitude will be multiplied by √3 and it will lead by 30 degrees. Okay, or what can I say? Your IA will be equals to IAD upon √3 minus 30. So actually I can now directly replace my IA phasor. This is the phasor, right? Phasor, everything is phasor. I can directly replace my, so previously I only discussed about the magnitude just to eliminate the options, but you can directly replace this, your IA vector. So this will always be valid. So this vector format is also valid. there will not be any phase difference. So capital IA vector upon small ia vector will always be equals to 1 by 2. This will always be valid, right? Now you replace your ia with this, correct? So your ia vector upon small iad vector, you have replaced your small ia vector with this upon root 3, so that will go on the other side. So if it goes on the other side, this will be 1 by 2 root 3 minus 30. Okay, so what have they asked actually? Okay, now what do I see? So I can write ia vector is equals to iad vector by 2 root 3 angle minus 30. What does it mean basically? It basically means if IAD has angle 0, IAD will be at angle minus 30. Basically means IA lags IAD by 30 degrees. So IA lags IAD by 30 degrees, or in other way I can say IAD leads IA by 30 degrees. Correct? IAD, how can I say this? IAD leads IA by 30 degrees. Okay, so this thing you have to keep in mind, right? Hold on a second. IAD, hold on. IAD is here. IA is here, right? I hope I am doing everything correct. So this is divided by IA. Okay, okay. Well, let me do this. Let me do this thing. This is plus, right? IAD is, hold on a second. So IAD will be 30 plus IA, right? This is minus 60. So ABC phase sequence. So this will be plus 30. It will lead IA. Now this is my IA. My IAD will be minus 30. Yes. IA, so minus 30 will come here. So if I am minus 30, right? This vector is minus 30. Plus minus 30. I'm just thinking something. Just give me 1 second. Root 3 will go that side. This also will go that side. This will be minus 30 only. So IA lags, because it is minus 30, IA lags IAD by 30 degrees. Yeah. So I can say IA lags IAD by 30 degrees, or I can say the opposite thing, that if I take this IAD on the other side, right, this will be 2 root 3 IA vector plus 30 degrees, right? So that means IAD leads IA by 30 degrees, because I can take this on the other side as well. Yeah, this will be the answer. Just one small mistake that we have made here. I forgot that actually the phase shift, right? This is wrong. This is wrong, right? So IB will be minus 120, not plus 120, right? So there is phase shift of 120, but initially this will be minus. Like basically it will rotate. The vector will rotate in clockwise direction by default. So IC will be I minus 240. That becomes plus 120. Okay. So actually this will be changed. This will be IB. This will be IC. Okay, this should be this should have been properly mentioned. I forgot. Yeah, so this will follow a clockwise rule. I forgot this. So if this is IC right now, things will change a bit. Like everything will be same, just the angle will change, right? So this angle will be here, right? So this whole thing is 180 and this thing is 120. So this much will be 60 degrees, right? So this is minus IC. Now I can write what is my resultant. So resultant here would be root 3 into IA, and the angle would be minus 30, not plus. That was the mistake that I was making. I know that I just solved it right previously, and I saw that answers is not matching. That's why. So what will happen? This will actually be minus, not plus. This will be minus. So this will become plus. So just the angle will change. Everything else will remain same. Whatever discussion we have done is okay. So this will become plus. This will become plus, and this will become minus. So essentially, what is happening? My current IA leads IAD by 30 degrees, right? That is what is happening. It is opposite. So IA leads IA leads IAD by 30 degrees, or I can say IAD lags IA by 30 degrees because it is minus 30 with respect to IA. So IAD lags IA by 30 degrees. So option A will be correct. That's what I was thinking because I had solved this previously. And it will not lead, it will lag. So option A will be correct, not option B. Okay, this is the correct answer. Okay, let's solve the final question of transformers. This is the final question. So like pretty simple question, they have just given you a very basic multi-winding transformer, and all they want is the circuit diagram is drawn. They want the average power dissipated throughout. So this is pretty simple actually. I can refer everything to the primary, right? So let me first refer this particular impedance here. So I hope you remember to the site. So what is the referred formula? So Z referred, right, will be equals to N, the number of turns to the referred site, upon the number of turns from where I am referring, or N S secondary whole square, or whatever N you want, right, into the actual impedance on the other side. Let's ZS, right? So this, right, will be 50, this is N reference is 1 and NS is 10. So this is 1 by 10 whole square into ZS. ZS is 50 kilo ohms. Ten cube. So this will be equals to 50 by 100. So 500 ohms. That is a referred value. So this 400 plus 500 will become 900. And now what I will do is I will refer the 900 ohms. So this 50 kilo ohm has been referred here, and it become how much? 500. And this 500 plus 400, they are in series. I will add them. It will become 900, and I will refer the 900 to this side. So again, this will be 900 into 1 by 10 whole square. That will be the referred impedance on the first transformer. So this will be equals to 9 ohms. So basically, what is the overall resistance here? 1 ohm plus 9 ohm, right? This is 9 ohms. This is 500 ohms, right? So this two things, if I add these two, this will be 10 ohms, and the voltage Vs is already given, RMS value. This is the RMS only, nothing is mentioned. This is the RMS. So Vs is 25 root 2. So your overall impedance or resistance in the input is 1 plus 9, that is equals to 10 ohm, right? And your they have asked me the power dissipated. So your power dissipated will be Vrms whole square by R. Okay. So Vrms would be 25 root 2 whole square divided by R. So 625 into 2, that is 1250, that is 125 watts. So 125 watts is the answer. Am I correct here? V square by R. Okay, sorry. Okay, they are not asking the overall power dissipated. They are asking the power dissipated in the 50 kilo ohm. Okay, this becomes now interesting. They are only asking me the power dissipated in the 50 kilo ohm. Okay, not that simple. This is the overall power dissipated, right? Okay. So what you can do, right? We don't need this. So this is the, if I replace this whole thing, right, with a single resistor, it will be 9 ohm. So what is the voltage drop, or what is the current in the primary side? So current in the primary will be Vs upon the overall resistance, that is 10. So it will be 2.5. 2.5 root 2. I don't care about the phase difference because I have to calculate the power. This is the current in the primary. So what will be the current here? So they will follow the inverse relation. So if it is 2.5, this will be 2.5 root 2 by 10. That is the current in this side. Now if the current here is 2.5 root 2 by 10, what is the current here? Again, inverse relation, you know the current relation, right? I1 by I2 by I1 equals to N2 by I2 by I1 is equals to N1 by N2. You know this. So this will be 2.5 root 2 by 100. Okay, this is in amperes. Let me convert this in milliamperes. Should I convert this in milliamperes? No, let us keep it in amperes only. Okay, so this is the current. So now can I calculate the power dissipated in the 50 ohm resistor, 50 kilo ohm resistor? Yes, I can. So this will be I square into R. IRMS is given to me, that is this, right? IRMS square into R. So 2.5 root 2 by 100 whole square into R. This divided by 100 whole square into R, that is 50 into 10 raised to power 3. So this is coming out to be 62.5. I'm just thinking whether I'm making any mistake or not. Circuit. Okay. I think they have made a mistake. So what has happened here, the average power dissipated. So they have assumed this to be the peak voltage. They should provide whether this is peak or RMS. That is the problem. So they should mention, right? They have nowhere mentioned it. Nowhere I can see voltage source is this. Nowhere I have seen that this is the peak or RMS. So in the answer key, they have given 31.25 what as the answer. But my answer is coming out to be 62.5. Why? What is the problem? The problem is they have assumed this to be the peak value. If this is the peak value, then your current will be divided by root 2, right? If current is divided by root 2, then like that is a problem. So if you assume whatever they have given to be RMS, then this will be answer. But if you assume whatever they have given to be peak, so Vs peak is 25 root 2, so your Is RMS, right, on that side, on the 50 kilo ohm side, will be 2.5 by 100. There will not be a root 2 factor because you will have to divide by root 2 for coming to RMS from the peak value. So this will be equals to so now the power dissipated will be 2.5 divided by 100 whole square into 50 kilo ohm, and if you calculate this, I guess you will get the value as, let me just check it just to be sure. The 50 into 10 raised to power 3, yeah, it comes out to be 31.25. So that is a problem basically. So this is not correct actually. Although they have provided this as the correct answer, this is not correct. The problem is they have not defined what is this. You need to define it, right? And because this was an IN paper, no one put more focus on this. Okay, so this should be empty actually. They should mention whether this is peak or RMS. They should not make this kind of mistake. So with this, we are done with the first chapter. Now we will start with DC machines. Let's begin with DC machines. Okay, so this is the first question where we have a separately excited DC motor. So the DC motor is separately excited. Uh, so its field winding will be excited separately, and it has an armature winding whose RA is given as 0.05 ohms, and the field excitation is kept constant. Basically your field current is constant, that means your phi is constant. At an armature voltage is, it is a motor, right? So it will produce a back EMF. EB is equals to 100 volt. The motor produces a torque of 500 Newton meter at 0 speed. Okay, that's interesting. How will the motor produce any torque? Okay, at 0 speed. Basically, it is a stalling torque, right? Motor produces a torque at 0 speed, that is 500 Newton meter. I will explain how it is producing the torque. I will explain. Just give me 1 second. Neglecting all the mechanical losses, the no load speed of the motor for an armature voltage EB2 of 150, this is EB1, right? 150 volt, what will be the speed? That is what they are asking me, right? Okay, so what is the, so it is a separately excited motor, right? So it will be connected to the supply. So there will be some VT connected, terminal voltage, that will give some current I. Okay, now what is IA? So they have not told me what is the supply. I don't know what is the supply, right? Certainly I don't know what is the supply. Do I know the supply? Separately motion, excited motion. Okay, it operates at So there is no zero speed. It is separately excited. If it is separately excited, right? If it is separately excited, its flux is there, but it is operating at zero speed. It is operating at zero speed basically. That means there is some load connected. Okay. Hold on a second. There's 150. No load, the speed of the motor would be. Okay. So at this point of time, right, it has some load connected, that is equals to TL. You might have the question, sir, if the motor is not rotating, so this is the shaft of the motor. Sir, this is the shaft of the motor, and the torque, let's say, is produced on this clockwise direction. There is a developed torque from the motor, correct? If the torque is produced, how is the motor not rotating? How is it possible? Because the condition that they mentioned, they should have mentioned in the question, certain load is connected, like any bag or anything, a load is connected. So if a load is connected, it will oppose the developed torque, TL. So in this case, TD will be equals to TL, and this TL is equals to my 500 Newton meter. This is the uh, like load torque. Because the load torque and the developed torque are the same, that's why motor is not rotating. Or sometimes what happens is the load torque is greater than, okay, this will never happen, the load torque will be greater than motor torque, because then it will rotate in the other direction. That will not happen. Basically, the load torque, right, always produces that much amount of opposing effect so that it is equal to the developed torque. Yeah, sometimes it happens that when these two are equal, then the motor rotates at a constant speed. That is a separate topic itself. But this time the load torque is high enough that it will never let the developed torque to exceed it, and hence the motor will never rotate. There will not be any acceleration. At no point TD, the developed torque will be greater than load torque. It will be always equal to it or less than it. Okay. So that is the case. So this only tells me about the developed torque. That is it, right? Now from here, what I can say is it is connected to some load, right? It is connected to some load. Now what is the value of the load? That is what they are asking me. Okay, one thing I am wrong. Actually, armature voltage, by armature voltage, right, they mean it includes the resistor, armature resistance as well. I was wrong here, sorry. Armature voltage basically means this VA1, right? So this is not the back EMF, this is the armature voltage. They should have properly mentioned this, but yeah, armature voltage is the voltage across the resistor including the armature as well. So properly should be mentioned. Sometimes there is some confusion. So yeah, now it is proper. So if this is the armature voltage and if it is not rotating at all, right? So EB is what? EB would be 0. So that's why it was not making sense, because how can there be non-zero EB, right? So EB is proportional to flux into speed, right? So K phi n basically, correct? EB is phi ZNP by 60A, and as the speed is 0, so of course your EB also will be 0. There will not be any back EMF developed. Now if there is no back EMF developed, of course, what will happen? There will be huge current flowing through the armature. Now what is the current? Current in this case, IA will be your armature, this voltage, this is nothing but the terminal voltage only, that is 100 minus EB, that is 0, upon RA, that is 0.05. So it is 1 by 20, 1 by 2, 1 by 20. So 1 by 20 into 100, that is equals to 2000. Okay, that is equals to 2000. So this is equals to 2000 ampere, right? This is the current. Now I can relate this with the torque. So what is torque? Torque is proportional to phi into IA. I hope you remember this thing, right, for a DC machine. Now it is proportional to phi into IA. Now as your flux is constant, so it is actually proportional to IA only. Okay, it is only proportional to IA only. Okay, Now what are they telling me? That neglecting all the mechanical losses in the no load, the speed of the motor when the armature voltage is 150. So what will be the speed of the motor when the armature voltage is 150? No load. No load basically means your armature current is zero. If your armature current is zero, then your back EMF will be equals to armature voltage, correct? And that is equals to 150. So your back EMF is 150 volts. Okay, your back EMF is 150 volts, right? Back EMF is 150 volts. Okay, and we have to find out the speed, no load speed. How do I calculate the speed? So back EMF is 150, that is equals to my k into phi into n, correct? So from this, if I know the value of k into phi, I will be able to comment about my EV. So there is actually one more thing. So this, right, torque is equals to, this is the same k phi ia. This is the same k phi. How? So I can prove it to you. So you know this thing, right? You know this EB into IA. There is no mechanical losses. If there is no mechanical losses, this is the mechanical power developed, EB into IA. That is equals to omega into T. I hope you know this thing, right? So now what can I do? Now in this case, EB is also 0, omega is also 0, that is fine. But in this case, what will happen? In this case, torque will be 0, right? So we will not be able to comment on omega. What do I want? What do I want? I want to find out this value, k into phi. Okay. Okay. So do you know what is this k? So I can write this k in terms of this. So basically, right, what I want to come to is, I know this equation, right? EB into IA is equals to omega into T. So this is the mechanical power developed, and this is the actual mechanical power that we calculate. Omega T is the actual mechanical power, correct? Am I correct? Power. Huh. So what I want to prove is, what is EB? EB is phi ZNP by 60A into IA, that is equals to, like, I'm just thinking what can I do about this. That is equals to 2 pi n T by 60, right? So your torque actually is equals to 2 pi, 60 will be cancelled, this will be n will be cancelled, Z P divided by 2 pi by A into IA, right? So your torque is this, and of course phi is also there. Okay, and we say EB is equals to k into phi n. Now if I expand, what is my EB actually? So we say EB is equals to k into phi n. This is actually a very good question. So EB is equals to k into phi n. So EB is what? EB is phi ZNP, phi ZNP by 60, that is equals to k into phi. I just want to calculate what is k, what is the parameter k. So if I see here, this k parameter, phi and n will be cancelled, this will be Z into n divided by Z into, okay, Z into P divided by 60A. Okay, phi ZNP by 60A. Yeah, now if I replace my n to omega, so I know omega is 2 pi n by 60A, 60, right? So what will be n in terms of omega? That will be 60 omega by 2 pi, because I want to compare in terms of okay, I don't want to, because n will be cancelled, right? Otherwise they will not be cancelled. That is interesting. Okay, phi. Okay, let me keep omega here. So essentially, like, okay, let me not do this. So we can say, like, your back EMF is proportional to k into phi into omega, not not E, otherwise the units will not be same. Okay, that is very important part. So yeah, this is true, this is true, but I will not write here K here. This is also true, no problems. Like your back EMF is proportional to flux and it is proportional to omega, that is proportional to N, that is true, right? But what I want to come to, I'll come to the conclusion, then I will explain what happened here really, because I want to match the units. So I will use this equation, right? This is also true because ultimately your omega is proportional to N, so both are same, right? Both are same. If I write here, that is same, but this constant will change. Why I am doing like this, I will explain. So this is K phi omega, right? So phi will be cancelled. Let me replace. So I know omega is equals to 2 pi n by 60, right? So I will replace omega with 2 pi n by 60. So if I replace omega with 2 pi n by 60, that is equals to 60, 2 pi n by 60. So what will happen? 60 will be cancelled, 5 will be cancelled, n will be cancelled, 2 pi will be there. So ultimately this K, right, becomes Zp by 2 pi into A. That is the same as this one. So here I have written torque is equals to K phi Ia, and this K is same. I wanted to prove it to you. Okay, this is the important part. Why? Because I will use it. I will again, don't worry, I will summarize the question again. Don't worry. So this is the thing that I will use. So torque is equals to K phi into Ia. So from this I will be able to calculate what is K into phi. Because in the first case, I know my current is non-zero, that is this. My torque is non-zero, that is this. From this I will be able to compute the value K into phi. And remember, this K into phi will only be utilized in this equation, not in this, will only be used in this equation. Then only if I write phi into omega, where omega is in radian per second, like this is the mechanical radian per second, remember this is the mechanical speed, right? Then only you can say this K and this K are same. Equations are different, but the K's will be same. Why? Because you can see the derivation here, right? And this I hope you have covered in full course as well. But if I would have just written that EB is equals to, let's say, K into phi into N, then this K and this K, right, will be different. Because of course the units will be different, because this is N, not omega. So if I write here omega, then the constants will be same. If I write here N, then the constants will be different. But this equation is totally valid and this equation is also totally valid. But the difference is just the constant will change. You are changing omega, and omega and N are related by a constant multiple, right? That's why if I am replacing omega with N, then the constant also will be replaced with some factor. That's all. The purpose of this question was to tell you that this K can be same with this K. But if you write the equations properly, then only they will be same. Otherwise, they will be different. Okay. So with that, I can calculate my K into phi. K into phi will be torque. So K into phi, case 1, K into phi will be equals to torque divided by current. Torque is 500 divided by current. Current is 2000. One by 4. Okay. 1 by 4. That is my K into phi. So we got my K into phi, that is 1 by 4. I don't care about the units for now, but I will use this in the second equation, because in the second equation, so this will not be N, this will be omega. Okay. So I know my EB, I know my K into phi. I will be able to comment about my omega. So K into phi is 1 by 4. So omega would be 150 into 4. So that would be 600 radian per second. Now, have they asked in radian per second or in yeah, they have asked in radian per second. So you are very lucky. So if they would have asked in revolutions per minute, then you would have had to make this conversion. You would have had to write n is equals to, sorry, I know omega is equals to 2 pi n by 60, right? And then from here you could have written what is n. N is equals to 60 into omega by 2 pi. Okay, that's how you can solve for this question. But they have asked the speed in radian per second only, so it will be 600 radian per second. So what we did, so I was stuck, right? So I was not able to figure out. So first they told me that the motor, this question is actually pretty good. So this is the armature resistance, and initially the armature voltage, the voltage across the armature, actually they should properly mention that it is included with the, it should be inclusive of the armature resistance, drop across the armature resistance, that is equals to 100 volt, because it does not make sense that if the motor is at like motor has 0 speed and it is developing some back EMF, that is not possible, right? Because flux is also non-zero, right? Flux is constant flux, it is non-zero, and EB is proportional to flux and speed, right? If speed is 0, EB has to be 0, flux is non-zero, that we know. Then certainly this is the armature voltage across the resistance. Now from that I got this relation, I got the armature current is 2000 ampere, that is the armature current. We got the armature current. In the first case there is no torque because it does not produce any torque, that is what they have told me. Sorry, in the first case there is some torque, it develops some torque, but actually the load torque is much higher, so it will never rotate. So the torque developed in the first case is 500 Newton meter. From this I have written two equations, EB equals to K phi into omega m and T equals to K phi into I. And I have just proven it to you that this K and this K will be same if the equations are properly written, then only the K's will be same. Okay, you can either go into the full course or you can directly start here, like study from here, right? So yeah, that's how you see it. So you found out the K into phi value in this case. In the second case, what you do, because in the second case they are telling me it is operating in no load. If it is operating in no load, the armature current is 0, so there is no drop. So whatever voltage I get, that is exactly my EB. So then again I know my EB, I have to calculate my omega, right? So I know K phi is 1 by 4, I know EB, that is 150, so I will use that to calculate omega, the speed of the machine, rotating speed of the machine. That's how you solve this question. Let's now move on to the next question, right? So this is the next question. This question, previous question was pretty good, so I think a lot of things will be cleared in the previous question. So this is the next question, a DC series motor. So we have a series motor, right? 200 volt series motor. So let me draw a few stuff. So I will have a RAC, it is a series motor, right? So it will have a series field winding, and of course it has a armature resistance as well. When operating at rated voltage while driving a certain load. When operating for rated voltage while driving a certain load, right? So when operating for rated voltage while driving a certain load, so it is operating at rated voltage and it is driving a certain load. So the load current is not 0. The total series resistance is 1 ohm. So basically it includes the series field winding resistance plus the armature resistance. So total resistance, that is RAC plus RA, is the magnetic circuit is assumed to be linear. At the same supply voltage, the load torque is increased by 44%. Okay, the magnetic circuit is assumed to be linear. While driving a certain load, it takes 10 ampere and runs at 1000. Okay, so in the case 1, what happens in certain load, right? It draws 10 ampere, current IL is 10 ampere, and the speed is 1000 rpm. IL is 10 ampere, speed is 1000 rpm. Now what they're telling me that uh, the magnetic circuit is assumed to be linear. At the same supply voltage, the load torque is increased by 44%, right? In the case 2, this is my load torque, TL. In the case 2, what I'm doing, the load torque is increased by 44%. Okay, load torque is increased by 44%. That basically means your new load torque, TL dash, is equals to 1.44 TL. Okay. The speed of the motor in RPM is, so in this case what will be the speed of the motor, that is what they are asking, right? N dash. So again we have to equate with back EMF. Okay, back EMF and stuff. So in this case what is the back EMF? So what is the supply voltage? VT is, supply voltage is kept constant, that is 200, that is not changing, right? So in this case EB1 or EB I can write is 200 minus I into total resistance, that is 1 ohm, that is 190 volts. And in this case what is the back EMF? So actually do you know what happens to the current? uh, okay, so in this case this is my TL, right? And the current actually, so what happens is that developed torque is proportional to flux into IA, and in this case our flux is proportional to the current itself, because they are told me assume the magnetic circuit to be linear, so it will linearly vary with the current, and current is the armature current only. The current through the series field winding is the armature current only. So this will be IA square. Okay, so this is the developed torque, right? And a steady state load torque will be equal to developed torque. It will rotate with the constant speed that we know, right? Initially obviously the developed torque will be greater, that's why there will be some acceleration. Now here what is the, again here what is the torque? Torque is 1.44 of load torque. So previously this was equals to TL, this was the previous torque, right? So I can take the ratio to calculate the new current. So TL dash upon TL will be equals to IA dash whole square upon I square. Okay, so this will be 1.44, because TL dash is 1.44 of TL and this is TL only. So this will be 1.44 into IA square, right? So basically it will be IA whole under root equals to IA dash. So that is 1 point, this will be I think 1.2, 1.2 into IA. So basically the armature current has increased by 20%. So previously the armature current or the load current, line current was, so this IA dash, IA and IL are same. Okay, don't worry. Previously it was 10 ampere, now it will be 12 ampere. So if this is 12 ampere, this will change the back EMF. So what will be the back EMF now? The supply voltage is still same, that is 200 minus IA, that is 12 into RA, that is 1, right? So this will be equals to, this will be equals to 188 volt. Okay, that is what my back EMF is. Now I can take the ratio of the back EMF, because I know what is my back EMF proportional to. Back EMF, again in a series motor, back EMF EB is proportional to flux into speed. Now my flux itself also is dependent on the current, right? In a series machine, so it is current into speed. Okay, so again I can take the ratio of the back EMFs. So it will be EB1 by EB2, correct? So this will be phi 1, that is current, IA1 by IA2, that is like IA dash only. Okay, I'm using different nomenclatures, otherwise you will be confused. So let me just use EB dash upon EB, IA dash upon IA into your N dash, that is the new speed upon the old speed, right? So EB dash upon EB, I all know EB dash is 188, EB is 190. So this will be 188 into divided by 190, that is equals to I dash. I dash is the new current, that is increased by 20%, that is 12 by 10. Obviously the thing that I have to calculate, N dash new speed upon the old speed was 1000. So if I solve this equation, I think we will be able to solve this. Let's solve this basically, right? Just give me 1 second. This will be 188 divided by 190 into 10 divided by 12 into 1000. 824.56. 824.56. Okay. So n dash equals to 824.56 RPM. So all these are just manipulation just to uh, like take some ratios and calculate, right? That's all. So they have asked in to round off to nearest integer. So nearest integer will round it off. So this will be equals to 825 RPM. Let's solve the next question. So this is the next question, where we have been given a DC shunt motor takes a 3 ampere current at no load. So when it is operated, so it is a shunt motor, right? So I have this winding resistor and I have this armature, and at no load it takes 3 amperes of current. So if it is taking 3 amperes of current at no load, right, armature is not taking any current, the current is simply going to the field winding. So basically field winding current is 3 ampere, that's all, right? Now it draws a 25 ampere. So it draws a 25 ampere, that basically means it draws current from the supply, that's all it is telling us. Okay, so it is drawing 25 ampere at full load at 1500 rpm. So NFL is 1500 rpm, and if it draws 25 amperes, out of that obviously 3 amperes will go to the field winding, because we know the field winding current is constant, it is mainly dependent on the supply voltage and which will not change. So this will be constant. So armature current at full load is 22 amperes. The armature and shunt resistance are the following. So RA is hold on a second, 220 volt DC. Okay. I think they don't, okay, this 3 ampere, right? They don't mean this 3 ampere to be the, sorry, they don't mean this 3 ampere to be the field winding current. They actually mean the 3 ampere to be something else. It is a loss current. So I will explain. So okay, so I was wrong there, sorry, because as I read the question now I understood. So at no load it is taking 3 amperes of current, right? So what will the field winding current take? So I know this supply voltage is 220 volt, correct? And the field winding resistance is given to us, that is 220 ohms. So this current is always fixed, that is 1, right? 220 upon 220 is 1 ampere. So this will be 1 ampere, that is always fixed. Now what about the other currents, right? So for the other currents it draws 25, so it draws 3 amperes at no load. So 1 ampere will go to the field winding and 2 ampere will go into the armature at no load. Now you might say, sir, how is it drawing some current at no load? How is it possible? It is possible because there will be some losses due to the magnetizing component of the armature. Due to that it is taking in some current, that's all. So no load current is this. So okay, and full load is this, the no load speed. So if no load if it is taking some no load current, right, if it is taking some no load current, then so actually in no load the current should be 0, that is certain. Okay, but here that would have happened if the shaft and everything, right, was ideal. So there is no opposing force, but we know in practical life the shaft, everything which tries to rotate, it has some opposing load torque, like the air and any other thing, right? So that's why it will take some small amount of no load current. It will be small, but it will take some of it to overcome that torque, like the air friction and everything. Okay, ideally it should be 0. Okay, but of course air and everything has friction. To oppose that, it will take some no load amount of current. So it has to develop some torque to rotate. No load means that no load is connected. It's not like it will not rotate. No, that is not the case. So we have seen the machine to rotate in no load, right? That we have seen. So no load rotation is a separate thing. No load basically means it should not absorb any current because it is not developing any torque. That is what no load means, because there is no load connected, so it does not have to develop any torque. But even if there is no load connected, there will be some mechanical losses, friction. Due to that, it has to develop that amount of torque to overcome that. I hope that is clear. So if the no load current is 2 ampere, what is the no load back EMF? EBNL. It will be Armature resistance I know that is given as 0.5 ohms. So EB&L will be 220 volt minus IA. IA is 2 into RA. RA is 0.5 ohm. So this will be 219 volts. This is very important. Why? Because they have asked me the no load speed in RPM. What is the no load speed? So to calculate the no load speed, I need to get the information about the back EMF, no load back EMF. Okay. So I got the information about the no load back EMF. Now, what about the hold on a second now. Now, what about the full load? So in full load, it is taking 25 amperes of current, right? So in full load, if it is taking 25 amperes of current, and of course we know that 1 ampere will always go to the shunt, right? So the remaining 24 amperes will go into the armature. Okay. So yeah, what about what is the EB now? EB full load, it will be supply voltage 220 minus the 24 into 0.5. So this is 208 volts. Okay, this 208 volts. Right. So yeah, so this is 208 volt, this is 219 volts. Now we know the speed here, right? We know the full load speed. So simply like flux is constant because shunt machine this current is constant, so flux will not change. So essentially your EB, so EB is actually proportional to flux into N, right? So but flux is constant, so I can do EB, I have to calculate the no load speed. So EB no load upon EB full load will be equals to N no load upon N full load. That's it. So this is N no load equals to EB no load. EB no load is 219, EB full load is 208 into N full load. N full load is 1500 RPM. Okay, so yeah, 1500 into 219. Hold on a second. Oh, and no load speed will be greater than full load. Yeah, that is certain. So this is 1579.32. 1579.333 actually RPM. Now what have they asked? Yeah, they have asked in no load speed in RPM only. This is the answer basically. Let's move on to the next question. So a 250 volt DC shunt motor has an armature resistance of this. Okay. Uh, Hold on a second now. Yeah, a 250 volt DC, a 250 volt DC shunt motor has an armature resistance this, field resistance this. Okay, so let me draw it. Armature resistance is 0.2 ohms and field resistance is 100 ohms, right? So RF is 100 ohms and its field resistance is, this is 0.2 ohms. Okay, and it draws a current, armature current at, so it is operating in when it is operated at no load at rated condition, it draws an armature current of 5 ampere. So armature current at no load, it draws 5 ampere. Okay, have they given us the supply as well? So it is a 250 volt DC shunt motor, right? So 250 volt DC shunt motor, so this field winding will always take 2.5 amperes of current. Okay, and no load current is this, and runs at 1200 rpm. So n no load equals to 1200 rpm. Okay, now when a load is coupled to the motor, it draws a line current. Now very important, it draws a line current of 50 ampere, not the armature, right? Line current. So now they're telling me when a load is connected, it is drawing a line current of 50 amperes. So what will be the armature current? So shunt current is constant, that is 2.5. So your show your uh, armature current, right? Armature current will be 47.5 ampere. Okay, 47.5 ampere with a 5% reduction in the air gap flux due to armature reaction. So actually this field current, it is taking the same amount of current, but there is a reduction in the flux. Why? Due to armature reaction. So now the new flux is 0.95 of the old flux. I hope you know what is armature reaction. The voltage drop across the brushes can be taken as 1 volt per brush under all operating condition. So V drop, VB, right, is 1 volt per brush. There are two brushes in a DC motor, there are two brushes, right? So it will be 2 volts. Make sure, okay, because per brush, they have told us per brush it is 1 volt. The speed of the motor in rpm under this loaded condition will be, what is the speed? Again similar like question you have to solve, like just like the previous question, right? So first, the first case, I know what is my no load armature current. I have to calculate the back EMF. Back EMF will be the supply voltage in the first case minus the armature current, no load armature current, into the resistance, that is a drop, minus the brush drop, that is 2 volt. So you will have to consider the brush because there will be some drops that will happen across the brush. So this will be equals to 1 minus 2, that is 247 volt. Okay, am I correct? 240, this 5 into this 2.5. What have they told us? Hold on a second now. It draws an armature current of 5 ampere. This correct. Yeah, this will be 247 247 volts. Okay, now what is the, I'm sorry, it's like I've not had sleep in a while. So what is the back EMF in the second case, in the loaded case? So it takes a armature current of 47.5 ampere, right? And of course you have to subtract the brush drop. So your EB dash in the second case would be, this is 1 by 5, so this will be actually 47, just give me 1 second now. 0.2 plus 2 plus 250, so it is 238.5. Okay, this is the back EMF in the second case. Now what is your so what is the speed in the first case? 1200 rpm. So what is your back EMF dependent on? It is flux into speed. Now in the first case the flux was 5, in the second case they have told me the flux reduces by 5%, so it is 0.95. So I can simply, not equal to, it is proportional to, right? I can simply take the ratio. So EB dash by B equals to EB dash by EB equals to phi dash into n dash by phi into n. So your EB dash I already know, that is 238.5. EB is like the old voltage, no load voltage, no load back EMF, that is 247. Okay, and equals to phi dash, that is 0.95 phi, and new speed, that is what I have to calculate. It is the old flux into the old speed, that is 1200 rpm. Okay, so yeah, so this will be equals to 238.5 into 1200 divided by 247 divided by 0.95. So it approximately comes out to be 1 2. So your new speed would be 1219.69 rpm. Okay, I think they have given the options as well. Yeah, 1219.19.19.6769, that is obviously close to option C. So option C will be your correct answer for this question. So yeah, let's now start this question. So a a belt driven DC shunt generator running at 300 rpm delivers 100 kilowatt to a 200 volt DC grid. It continues to run as a motor when belt breaks. Okay, so a lot of stuff here. So a belt driven DC shunt generator running at, so initially the speed was 300 rpm and it was delivering 100 kilowatt. So the generator was delivering 100 kilowatt of power to a 200 volt DC grid. So I will have a shunt generator, right? It is delivering power to a 200 volt DC grid. That basically means the terminal voltages are 200 volts. So this is what they mean. It continues to run as a motor when the belt breaks. So basically what happens, there is a belt, right, and that belt rotates, and that's why this DC motor also rotates. So if the belt breaks, right, so because it is operating in a grid and grid always have some supply, so this grid can at the same time absorb power, also deliver power. So because the belt has broken, so no one is rotating this machine, so now this machine will rotate, so will work as a motor because it is not able to generate voltage. The belt has gone, right, belt is broken, so now it will, because there is a supply connected, so it will work as a motor now. The armature resistance Ra is 0.025 ohms, right? Field resistance RSH is 50 ohms, and brush drop is 2 volt. Ignoring armature reaction, the speed of the motor is, so they're basically asking me what is the speed of the motor in this case. Okay, uh pretty interesting question actually. So what will happen, so it is delivering this much amount of power. So what is the back EMF? So if it is absorbing some power at the, so what is the speed of the motor? If it is working as a motor, what will be the speed of the motor? That is what they are asking me. That is interesting. Okay, because the flux is same. So what is happening, this 200 volt, right, due to this some current will flow through the shunt winding, some IF field current, I don't know, but that current will be same because this grid is always present, that is connected, so the flux is same. So if the flux is same, what is happening, your phi is same, in the case 1 and case 2, flux is same, right? What about speed? What about the so your EB, right, back EMF is dependent on two parameters. It is dependent on the flux, it is dependent on the speed. So because flux is same, so EB is only dependent on speed. So if the back EMF changes, then the speed will change, otherwise speed will remain same. Now what will happen to the back EMF? That is pretty interesting part, right? What will happen to the back EMF? So how do I calculate the back EMF? That is what I'm trying to think of here. So it delivers 100 kilowatt. Okay. Now, okay, they have told us, right? Okay, they have told us that when it was delivering 100 kilowatt to the grid, and when the belt has broken, it is taking 10 kilowatt from the DC grid. So it is absorbing power. The armature is absorbing power. So what is the current in that case, right? So this is V, and it is, so in the first case, case 1, it is delivering 100 kilowatt to the grid. So the grid is receiving 100 kilowatt of power. This will be equal to what? This will be equal to the terminal voltage into the line current. So this line current IL, because it was working as a motor, so it was delivering. So what is IL now? So VT is 200 and power given was 100 kilowatt. So your IL will be equals to 100 into 1000 divided by 100 into 1000 divided by 200. Okay, that is equals to 500 ampere. So IL in the case 1 is equals to 500 ampere. Okay, now is this the uh, armature current? No, this is not the armature current, because they have given me the field winding resistance, right? So what is the field current? Field current will be this voltage upon the field winding resistance, that is 50. So 200 upon 50 would be 4 ampere. This will always be constant. So what is the armature current while working as a generator? It will be this current, line current, that is 500, plus the field current, that is 4 amperes. So it will be 504 amperes, correct? So it is equals to 504 amperes. Now what will happen? What about the generator current, right? What about when it is working as a motor? So when it is working as a motor, it is actually consuming 10 kilowatt from the grid. So of course some of it will be gone to the shunt field winding, right? So actually what is the line current now? Now things will change. So as it is working as a motor, so it will absorb current, it will take current, it will not deliver current, right? So current will be inwards. So it will be working as a motor, this current will not be same, and it is absorbing, line current will come here, it is absorbing 10 kilowatt of power. So what is the line current? So again your, this is N, right? Your V, so your P M is equals to 10 kilowatt. Vm is equals to 10 kilowatt. So your line current in this case will be equals to Pm, so 10 kilowatt upon the voltage, that is 200. So this two zeros will go, so this will be 150 ampere, right? So field current is still 4 ampere, so line current is 50 ampere. Out of this 4 ampere will be gone to the field, and remaining 46 ampere will go into the motor. So now what is the back EMF in the case 2? Back EMF when it is working as a motor, it is basically Vt. Okay, I forgot one thing, right? Okay, I have not even calculated the back EMF. So what is the back EMF in the case 1? Right, back EMF in the case 1 would be Vt, that is 200, minus Ia into Ra, that is 504 into Ra, 0.025 minus the brush drop. So this will be equals to 0.025 into 504 plus 2 minus plus 200. So it is 185.4 volt. Okay, and EV2 will be equals to VT, that is 200 minus I into RA, that is 46 into RA. RA is 0.025 minus VV, that is 2. So this will be 0.025 into 46. Okay, 1.15 plus 2 plus 200, that is 196.85. Now we can directly, because the flux is same, flux is not changing, we can directly comment about the speed. So they are asking me in this case what is the speed. So it will be N2 upon N1 will be equals to EB2 upon EB1, right? So that is EB2 upon EB1, that is equals to, so I can directly solve. So N2 would be EB2 is how much? 196.85 upon EB1. EB1 is something. Okay, one small mistake. Was it working as a motor here? No, right? So this is not the back EMF, right? This is a generated EMF. I'm extremely sorry, right? Because look at the direction of the current. These are the silly mistakes that can make. The direction of the current is in opposite. So actually this will be added, not subtracted. These things will be added, right? I hope you remember don't even remember, it is basic concept, the generated voltage equation. Okay. So EG 200 plus this, so it will be actually 200 plus mass of charge into 0.025 plus 2, so it is 214.6 volts. Okay, so yeah, so this will be 214.6 volts into N1. N1 is 300. So N2 would be equals to this into 196.85 into 300. So N2 would be 275.186 RPM. Okay, so yeah, this will be the answer for your question. 275 and 186, they have told us to round off to 2 decimal places, so you can round this off to 275.19 RPM. Okay, this will be an answer for the question. Let's now move on to the next question. So a 280 volt separately excited DC motor with a armature resistance of 1 ohm. So it is a separately excited DC motor. So the field winding is separately excited. It is a DC motor with basically a armature resistance of 1 ohm and 280 volt, right? So the terminal voltage is 280 volt. Constant field excitation drives a load. The load torque is proportional to the speed. Okay, they have told me that the load torque, right? is proportional to the speed of the motor. Okay, that basically means load torque is developed torque at steady state. So the torque is proportional to the speed, which is proportional to the flux into Ia. In our case, because it is separately excited, so your flux is constant, so your speed will be proportional to the current. This is a very, very important point that they wanted to convey here. The motor draws a current of 30 ampere. So it is drawing a current of 30 ampere when running at a speed of 1000 rpm. So when the speed was 1000 rpm, it took a current of 30 ampere. Neglect all the friction losses. So the speed in armature at which the motor will run if an additional resistance of 10 ohm is connected. So now the new resistance, right, is 11 ohm. If this is connected, then the speed at which the motor will run. That is what they are asking, right? Okay. So what will happen? So in this case, this is the in this case, what is the back EMF? Because we know our back EMF depends on the speed. So back EMF is proportional to the speed and the flux, because flux is constant. So back EMF will be proportional to speed. Correct? Okay. Back EMF is proportional to speed. Right? So, yep. So, what is the back EMF in the first case? So, EB1. So, EB1 would be 280. They have not discussed about burst drop or anything. So, it will be 280 minus Ia into R, that is 1, that is equals to 250 volts. Okay. 250 volts. Right. So it is 250 volts. That is the case 1 EV1, right? And this will be proportional to the field. This will be proportional to the speed basically. Okay. So in the second case, what is EB2? So I have to compute EB2. How do I compute EB2? EB2 will be equals to VT, that is 280 minus IA2 into RA, that is 11, because this has changed now. But what will be IA2? How do I compute the IA2? So what do I know? That the speed is proportional to the load, right? And our torque, yeah, so basically our speed is proportional to the load current. Correct? Speed is proportional to the load current. Okay, things are heating up here. So I will do few things. I will do certain things. So speed is proportional to the load current, right? And I know speed is proportional to the back EMF. So I can say back EMF is proportional to the load current. So not load current, armature current basically. Is that fine? So what I can do is EB2 upon EB1 will be equals to IA2 upon IA1, right? And that is equals to what? So I know what is EB2 equals to. EB2 is equals to this, correct? And what is my EB1 equals to? EB1 is equals to what? EB1 is equals to this 250. What is my IA1? I1 is equals to 30, right? So I will be able to calculate for IA2. So that was the trick in this question. This question, a lot of relations are there. You have to identify which relations to take. So IA2 will be equals to 30 by 250. So that is 3 by 25 into 280 minus 11 IA2, correct? So if I solve for this, right? So 11 into 3 divided by 25 plus 1, that is 2.32 I2, that is equals to 3 divided by 25 into 280. So it is equals to 33.6. So this divided by 2.22. So IA2 comes out to be 14.482 amperes, correct? So yeah, IA2 is this. Now it is pretty simple. We got our IA2, right? So I can actually calculate what I can actually directly say what is my speed. So speed is directly proportional to IA by IA2. So I can say N2 by N1 will be equals to IA2 by IA1. So N2 will be equals to N1 is 1000. N1 is 1000 into IA2. IA2 is 14.482 upon IA1. IA1 is 30 amperes. So this divided by 30 into 1000. So your new speed, if a resistance of 10 ohms is connected in series, is 482.76 RPM. Okay. So yeah, have they asked us? So round up to the nearest integer. So if you round up to the nearest integer, it will be 483 RPM. Let's solve this question. So we have four conductors, stator conductors, right? These are the stator conductors that are shown: capital A dash, then capital B dash, in a rotating machine. So the rotor is rotating. The direction as shown. The rotor coils A dash and B dash are formed by connecting the back ends of the conductors A and A dash, right? So these two are connected back ends, and B dash are connected, and a voltage is developed, EAA dash and EBB dash, if the rotor is rotated at uniform angular speed with omega radian per second in the clockwise direction. It is rotated with uniform angular speed in the clockwise direction. Then which of the following describes EAA dash and EB dash properly? Okay, so they want the values of EAB dash and obviously the whether which one is leading, which one is lagging. So first thing is, what are the location of the poles, right? So what will be the location of the pole? So this will develop like a what, a rotating magnetic field. So a field like this, because it is inwards, if I curl my fingers, so it will be clockwise, right? And this is coming towards me, right? This, for the stator conductor, it is coming towards me. If I curl my fingers in the anti-clockwise direction, this will be the direction of the field, correct? And if I curl my fingers here, this will be in the clockwise direction. If I curl my fingers here, this will be in the anti-clockwise direction, right? Okay, so one thing to notice here, so magnetic field, right? We assume this to be the inner side. So magnetic field is coming in here, magnetic field is coming in here. So if it is coming in, then we'll assume like in a south, what happens? So from north pole to south pole, right? So outside, what happens? From north it goes to the south pole in the outside. Inside also something like this happens, although we don't never show it. Inside something like this happens, north pole to south pole, right? So what will happen is, as the magnetic field is coming in, right? So this will be my south pole, okay, and this will be my north pole. Although it does not matter, you can assume anything to be north and south, because it will also keep on rotating, because the rotor itself is rotating, right? So this will be my north pole and this will be my south pole. So I got my 4 poles. Of course it makes sense, I have a 4 pole machine, that is okay. Now what happens? What I am concerned about is the geometrical neutral axis. Why am I concerned about the geometrical neutral axis? Because I know if my conductors, right, if my rotor conductors lie on the GNA, geometrical neutral axis, then there will not be any EMF developed at this particular instant. So we know that the GNAs are always 90 degrees electrical from pole, right? So what is 90 degree electrical? So everything is mechanical here, right? Nothing is electrical. So let me understand what is the mechanical angle. So I know my electrical angle theta E is equals to P by 2 of theta M. That is my mechanical angle. So mechanical angle would be 2 by P into theta. So number of poles is 4 and theta is 90 degree. So mechanically, if I go 45 degrees from either of my poles, I will exactly be at the geometrical neutral axis. So if I go 45, so this is exactly the bisector, right? And this is this 45 degrees. So I hope you can do bits of geometry. You can understand these are 45 degrees. So basically all my coils, right? These two coils are lying in the geometrically neutral axis, and if they are lying in the GNA, so A dash, B dash, all the coils are lying in GNA. Okay, all the coils are lying in GNA. So that's why this will be basically what will happen here. They will not develop any EMF. So option D will be the correct answer for this question. Okay, if they would have lied in some other axis, then there would have been some non-zero finite magnitudes. Okay, and if that was the case, then what would have happened is, if it is rotating, right? So which one will lead, which one will lag, that we'll have to think about it. Okay, but they will not be in the, certainly we'll have to think about it. But for this question, the option will be D. So you can think, if I just rotate this by 45 degrees, right? If I rotate this coils by 45 degrees, what will happen? Okay, let me know in the comments below. So yeah, let's solve the next question. So this is the next question. A separately excited DC motor rated at 400 volts. So the terminal voltage, it is a separately excited DC motor. So terminal voltage of the DC motor is 400 volts, and it takes a rated current of 15 ampere and 1500 rpm, drives a constant low torque at rated, operating from 400 volt DC supply. So it is operating at rated speed. Okay, so it is operating at rated speed and drawing also rated current. So basically the current is 15 ampere, operating at rated speed, and it is operating at constant shunt resistance. So okay, this is the condition basically. So not, so it is separately excited, right? What I'm doing, it is separately excited, sorry. Okay, so this is the condition here. So in this condition, do I know the armature resistance? Yes, the armature resistance is 1.2. Okay, so now they're telling me that if the supply voltage drops by 10% with the field current unaltered, so the flux is unaltered, then the resultant speed of the motor will be. So basically what has happened, only the supply voltage has dropped. So let us write the values in the condition when the supply voltage was not dropped. So what was my back EMF when there was no drop in supply voltage? It is the terminal voltage minus IA, armature current, into the RA 1.2. So this will be 15 into 0.2, that is 1 by 5, that is 3, right? 15 plus 3, that is 18. So 18 would be basically 3 8 2 382 volts. Okay, so EB 1 is 382 volts. Now this will help me calculate the speed actually, because for the second case, now what is happening, the field current is unaltered. Okay, so what is my torque proportional to? Torque is proportional to flux into IA, correct? And the load is not changed, right? And field current is unaltered, so IA also will be constant, because there is a load connected which drives a constant load torque, which drives a constant torque load. So torque is constant. If torque is constant, because, and also the flux is constant, right, then the load current has to be constant. So IA will not change, only the supply voltage has been reduced, so speed will be reduced. So if the supply voltage has been reduced, so what will be the back EMF in the second case? Supply voltage has been reduced by 10%, right? So if it was 40, Now it will be 10% drop, that is 0.9 into 400, that is equals to 360 volts, right? So this will be 360 minus IRA. IA has not changed, RA has not changed, so this is still 18. So now the back EMF is 342 volts, and of course what is my back EMF proportional to? It is flux into speed, and of course flux is not varying, so I can directly say EB2 upon EB1 would be equals to N2 upon N1. So my N2 would be equals to EB2 by EB1, that is 382 into N2 by N1, N2 by N1, that is 1500 RPM, okay, 1500 RPM. One three four two. 1343 RPM. Okay, so this is the basically resultant speed of the motor in the new case. Okay, let's solve the next question. So the no load steady state output voltage of a DC shunt generator is 200 volts. Okay, no load steady state output voltage of a DC shunt generator is 200 volts. Okay, when it is driven in the clockwise direction. Okay, so this is my DC shunt generator, and when it is driven in the clockwise direction, it generates a EG voltage, and it's a shunt generator, right? So it is operating in no load. So in no load, do you remember what used to happen? So there is this field flux, which also there is the residual flux, right? Due to the residual flux and due to the rotation of the motor, like due to the there is already a field flux, right? Sorry, there is already residual flux, and due to the rotation of the motor, what happens? A field flux is generated, which is added with the residual flux, and slowly it increases, and slowly the voltage is built up. If you remember, this was the build up voltage curve, right? Okay, just give me 1 second. Okay, this is the voltage build up, right? So yeah, this is EG, and I think this is the IA plot. Yeah, this is the IA plot, and this is the critical resistance field line, right? Something like this. So what happens is, as soon as the motor is rotating in the clockwise direction due to some residual flux and due to the generated uh, uh, flux, right, the both will be additive in nature, and slowly the voltage will increase, because if this flux, if this field flux is generated, this will add, and overall flux will increase, and I know my EMF is proportional to flux, so EMF will increase, and again if EMF increases, this in turn increases the flux. So this is a feedback kind of system, but of course it will stop at certain point when it will meet the load curve. Basically, this is the concept of DC machines. Okay, now here what happens is, what they are asking is, now what they're telling me, that if the same machine is driven at rated speed but in opposite direction, if it is driven in rated speed but in opposite direction, the steady state output voltage will be dash volts. Okay, if the same machine now is rotating in the opposite direction, so you will assume if the same machine is rotating in the opposite direction, so what will happen? Simply it will generate 200 volt only, right? Because it doesn't matter, right, whether I generate in the clockwise or anti-clockwise. No, it does matter actually. So what happens if you generate? So if I was generating in the clockwise direction, it was it was producing or generating a flux such that it was additive in nature. But if I rotate in the opposite direction, it will produce a flux, right? It will certainly produce a flux, but that will be subtractive in nature. It will not be additive. And if it is subtractive in nature, right, it works as a negative feedback. So if I rotate the machine, overall flux, because the newly generated field flux is subtractive in nature, the overall flux will reduce. And if the overall flux reduces, it will try to reduce the generated EMF. So actually, generator will fail to build up voltage. So there will not be any voltage built up. This is actually a very beautiful question. So if there is no voltage built up, right, the voltage will be simply 0. This will be the answer. Now what is the other way to understand it? If you are rotating in the clockwise direction, this was the polarity of the generated EMF. If you rotate in the anti-clockwise direction, so your Eg is proportional to flux into speed, right? If you are rotating in the anti-clockwise direction, right, so your N is becoming negative, so your Eg also will become negative, right? Or if you want to keep the Eg in the same term, so if you want to keep Eg as the same, right, so what do you want? So you want the Eg to be positive, because it will deliver from here only. You want the Eg to be positive. So what will happen to the flux? So basically, let's take a very basic example, right? So let's say if Eg was some 1 volt, okay, or some 100 volt, and there is some K into flux into speed. So let's say speed was positive 100 ampere. So what will be your flux? Flux will be K is some positive constant. Flux will be 100 upon 100 divided by K. Okay. So this will be 1 by K. Okay. This will be 1 by K, right? Now this is 1 by K. Now what do we need to do? Okay. Yeah. So this is positive, right? So if your speed becomes negative, and if you want your EMF Eg to be still at 100 volt only, and your speed is in the anti-clockwise, right? It was clockwise plus 100, anti-clockwise minus 100. So it will be K phi into minus 100. Like mathematically, like technically, visually I have already told you, but mathematically I am doing it. So what will happen is your phi will be minus 1 by K. That's all. Okay, so it will be negative. Mathematically, I'm proving it will be negative. The generated flux will be negative. If it is negative, it will be opposing in nature. So there will be no voltage built up. That's all. So 0 will be your answer for the question. So I hope that part is clear by you. Okay, so yeah. Now let's solve the next question. This is the next question. So a 5 kilowatt 220 volt DC shunt motor has 0.5 ohm armature resistance, including brushes. The motor draws a no load current of 3 ampere. A 5 kilowatt 220 DC volt. Okay, it is a DC motor, DC shunt motor, right? So 5 kilowatt 0.5 ohms, and it draws so we have a 5 kilowatt DC shunt motor 220 volt. So 220 volt is the terminal voltage, right? It is a motor. It takes the motor draws a no load current of 3 ampere. Sorry, motor draws a no load current of 3 ampere. Basically it will draw the current here, right? The field current is constant, that is 1 ampere. So obviously the armature takes a current of 2 amperes. Okay, the field current is constant 1 ampere. Assuming the core and rotational losses are constant and independent of the load, the current drawn by the motor while delivering a rated load for the best possible efficiency. Okay. Okay. The current drawn by the motor while delivering the rated load. Okay. So one thing is interesting over here. What do they mean by 5 kilowatt? So when it delivers the rated load, what is the current drawn? Okay. If the rotational losses are constant and independent of the load. I exactly don't understand what they mean by the. Okay, that this is good. Okay, I got it. So they want me to find out the current drawn by the motor. Current drawn by the motor actually is the overall current drawn by the motor, including the field winding. Okay, including the field winding. So basically, they want me to calculate the line current at full load. Okay, line current at full load. They want me to identify the line current at full load. Okay, so yeah, now how do I calculate this? So you might think that already they have given me this 5 kilowatt. So if I just simply divide 5 kilowatt by 220, I will get the line current, right? And you're wrong. This 5 kilowatt is the output of the motor. Okay, this is the output of the motor. So the motor delivers 5 kilowatt of the power as the output. So this is just the P out. The rated P out of the motor is 5 kilowatt. But what is the input to the motor? The input to the motor, right? Or the power developed by the motor, P developed by the motor, what will be it? It will be the P out plus the no load losses, no load rotational losses. And do you know what is the no load rotational losses? Okay, or the constant losses. So I know in no load, this thing is absorbing how much amount of current? If you see in no load, the armature is absorbing 2 amperes of amount of current, right? So basically, this 2 amperes of current is what? This 2 amperes of current is nothing but the rotational losses, friction and windage loss. All these are losses. Okay. Now, here for me to calculate these losses, right? Also, there is this armature loss. So what I will do? I will calculate. So what is this loss? I will calculate the EB in no load. Okay. If I calculate the EB in no load. So if I calculate the EB in no load, right? And the no load rotational losses will be EB no load into IA no load. That's all. These are the no load losses, because the motor no load is connected. Still, it is consuming some power, and that power actually is utilized to provide to the losses. That power is actually utilized for the losses. Okay. So I got my no load losses. So this will be. So I have to calculate EB no load. How do I calculate EB no load? So EB no load will be 220 minus IA no load, that is 2 into 0.5, right? So this is my EB no load. That is equals to 219 watts. Okay. So that is 219 watts. So this is 219 watts. So yeah. Now what will I do? What will I do? Okay. Sorry, this is the power, this EB, and your no load. Sorry, this is 209, not 19 volts. This is 219 volts, right? So your power will be 219 into 2, so it will be 438 watts. Okay. So this is the no load power basically. Now these are fine. What about the power consumed by the field winding, right? That is also a power that the supply has to deliver. So power consumed by the field winding will be the voltage across it into the DC current, right? That's very simple. So it will be 220 into 1. So it is basically 2 220 watts. Okay, that is the power consumed by the uh, field winding. Now, like there is one more power. So when it will operate under rated condition, if it operates at rated condition, right? So at rated condition, what is the current? Okay, how do I calculate the current at rated condition? The current drawn by the supply. Uh, so at rated condition, it delivers 5 kilowatt of power. Okay, so it delivers 5 kilowatt of power, right, at rated condition. So can you tell me what is the power developed by the motor at rated condition? It will be EB rated condition, EBR into IAR. Okay, but I don't know what is EBR. I don't know this value. Also, I don't know what is P developed. P developed actually is not just the 5 kilowatt power. It also has to develop this no load power, right? This also has to provide the no load losses, because at the output the user will see that I am getting 5 kilowatt of power, but internally the motor has to also provide the power for the losses as well, right? So you are observing 5 kilowatt, but motor has to provide that extra losses, correct? Okay, so yeah, motor has to provide this extra losses. So the P developed, right, will be 438 plus the uh, obviously the rated power, that is 5 kilowatt, that is 5000, right? 5000. And what is EBR? Rated back EMF. It is actually equals to VT minus IAR RA. VT is 220, so 220 minus IAR. IAR is uh, IAR is what? IR into RA. RA is 0.5, right? RA is 0.5. So it is IR by 2, and this is equals to into IR. Now this gets converted into a quadratic equation, and from this actually I will be able to calculate what is my uh, rated armature current. Okay. So yeah, I hope that this part is clear. I can easily calculate what is my rated armature current. So let me calculate the rated armature current. So this will be 538, sorry, 5438 220 IR minus IA square by 2. So if I solve this quadratic equation, IAR whole square (440 IR) (800) 10,000 874, sorry, 76, yeah, equal to 0. Right now I will solve this quadratic equation. I will calculate the value of IA basically, right? So let me calculate the value of IA. So this will give me the value of IA. So yeah, IA square 440 minus B plus minus B square 440 minus B square minus 4 AC b square minus 4. Okay, something is happening. This is coming out to a negative. Minus b plus minus b square minus 4 is, I'm just thinking of something. This is coming out to a too low value. Oh, no, this is fine. This is fine. 4 into 10876 divided by 2a. So this will be 440 whole square minus 4 into 10,876 under root. Obviously I will, okay, there are two options here. So this is actually, this under root value is 387.42. So either I can choose the negative value or positive. Let's choose the negative value. So plus 440 by 2, which is, so your, if I choose the negative value, your IA rated comes out to be 26.28 amperes. Or if I choose the higher value, right? If I choose the higher value, okay. So let's say if I choose the positive value, 387.42 plus 440 upon 2. So it comes out to be 413.71 amperes. This will be very high. And anyways, if you put this value, right, if you put this IA value in the EB, what will be the EB value? EB value will be almost very low value. EB, like if you put this IA value, right, in EB equation, it will be very low. Okay, it will be almost around 10 volts. So of course you will not choose that value, otherwise E will come out to be negative. E will almost come out to be negative, which of course you will not choose. So you will choose the lower value, otherwise E, the back EMF will be almost zero, negligible. So this is the actual current, this is the rated current. Now this is just the armature rated current, right? But they have asked me how much current the supply will, how much current the motor will draw, that is this current, line current. So line current will be equals to, line rated current will be equals to 26.28 armature rated current plus obviously the constant field current, that is 1 ampere. So it will be 27.28 amperes. So 27.28 amperes will be the answer of your question. Very good question, very elegant question. Okay, bit lengthy but bit conceptual, and you will have to solve this kind of questions, right? So let's solve this question. So a DC series motor with negligible series resistance is running at a certain speed. A DC series motor with negligible series resistance, so RASE is 0, at certain speed, is running at certain speed, driving load where the load torque varies as the cube of the speed. The motor is fed from a 400 volt DC source. The motor is fed from a 400 volt DC source. Okay, so the motor is fed from a 400 volt DC source. So the VT, terminal voltage, is 400 volt. And draws 40 ampere armature current. Okay, it draws a armature current of 40 ampere. Okay, assume linear magnetic circuit. Uh, what external resistance must be connected in series for the armature speed to reduce by half? Okay, so this is the condition, this is the scenario. So I have this armature, and they're telling me it does not have a armature resistance, right? The series resistance is almost negligible, and it draws a current of 40 ampere. Okay, and it does not have a resistance, so whatever is the voltage, 400 volt applied, that will be my back EMF basically. Correct. So in this case, the speed, I don't know, speed is n. So in this case the speed is n. Now what they want to connect a resistor so that the speed becomes n by 2. And I know that they told me that the load torque also TL varies with n cube. Okay, you have to keep in mind, because what are the things here? So in a machine, DC machine, the torque varies with flux into Ia, and the back EMF varies with flux into speed. Okay, I know flux is dependent on the current because they have told me that we can assume linear magnetic circuit. So my back EMF will be proportional to Ia into speed, and my torque will be proportional to Ia square because flux is proportional to Ia, or I can say it is proportional to N cube because your torque is proportional to load torque is proportional to N cube, and at steady state load torque will be equals to developed torque. So your torque is proportional to N cube, your EB is proportional to Ia into N. Okay, these equations I will use, all these equations I will use. Okay. So if the speed is reduced by half, right, the load torque also will be reduced. So these things are there, I have to consider. So I have to calculate the current basically. So if the, so what is the current here? 40 amperes, right? So for 40 amperes, what is that? So I can do, so what I can say is Ia square is proportional to N cube, right? So what is the first case current? 40, right? What is the current in the second case? I don't know, that is Ia2 whole square, and this will be equals to, so Ia square is proportional to N cube, right? So what is the speed in the first case? N, right? So it will be N cube. What is the speed in the second case? It is N by 2 whole cube. So Ia2 will be equals to, this will be 2 cube, right? 2 cube will be divided, so 1600 divided by 8, that is 200 amperes. Okay, hold on. N cube, this will be 2 cube will be divided there, yeah, this Ia square, sorry, this Ia square equals to 200, right? So Ia2 will be 10 root 2, that is what my Ia2 is. Okay, so we got our Ia2. Now all I need to do is find out the R. So how do I compute R? So what will happen to the back EMF? So you know back EMF is proportional to current into the speed, right? So EB1 by EB2 will be equals to Ia1 by Ia2 into N1 by N2, right? So I know what is my EB1. EB1 is simply the voltage directly connected across it. So this will be 400. EB2 will be the voltage minus Ia2 minus Ia2, that is 10 root 2 into R that is connected, right? That is what you have to calculate, equals to Ia1 upon Ia2, that is 40 upon 10 root 2 into N1 by N2. N1 by N2, right? So N1 by N2, right? So it is half basically. So N1 is N, N2 is N by 2. So this is half. Sorry, this is 1 by 1. So this is N by N by 2 basically, right? Speed has been halved. So from this I can easily calculate what is my R. So this will be, let me just compute few values here. So 400 into 10 into root 2 upon 40 divided by 2. Yeah, so this will go on that side, plus 400 upon 10 upon root 2. So your R comes out to be, so you can solve this equation simply. R will come out to be 23.28 ohms. Okay, and 23.28 ohms is present in option A. So option A will be your answer. Very good question, very beautiful question. Just a bit lengthy, okay, because like it was varying with speed cube. So DC machines have been covered completely now. Now we will move on to your induction machines. Let's begin with induction motors. So this is the first question. A 3-phase 50 hertz 4 pole. So whenever induction motor is given, always write down the information. It's a 50 hertz 4-pole machine, and at no load with a slip. So slip at no load is 1%, that is 0.01. With full load, the slip increases to 5%. The speed regulation of the motor is. So for this again you have to remember that what is the formula for speed regulation. What is the standard formula? Standard formula for speed regulation is, or it is sometimes called as regulation, percentage regulation, right? That is equals to no load speed minus full load speed upon full load. That is the default formula. Okay, into 100%. They have asked percentage regulation, so upon full load will be there. So what is the no load speed? So we know that in induction motor, your rotor speed is the speed of the rotor, right? That is equals to 1 minus s into ns, right? Ns is the synchronous speed and ns is equals to 120 f by p, that is 50 by 4. So this shall be equals to 3 into 50, that is 1500 rpm. Okay, so in the first case, what is my n no load? That is the rotor speed and no load. So ns is 1500, that will be remaining as constant. S is 0.01, so this will be 1 minus 0.01, so this will be equals to 1485. And what about your n full load? N full load will be 1500 into 1 minus 0.05, that is equals to 1425 rpm. Okay, so that is equals to 1425 rpm. That's my speed in full load. So yeah, that is equals to 1485 minus 1425 1425 into 100%. So this will be this into 60, right? Just give me 1 second. 60 upon 1425 into 100, so it is 4.21%. This will be your answer, 4.21, because I have to round off. So 4.21 will be your answer for the question. Pretty simple and easy to understand. Let's solve the next question. So the constructional features of a induction motor are given, and the machine type is given, where they are used basically, right? And what is the mitigation, like why is this used, for what reason, like what does it help to mitigate? So the correct relation between the features. So I know damper bars are used in induction motors, right? Certainly. And skewed rotor bars are also used. Sorry, damper bars are not used in induction motor. Damper bars are used in synchronous machines. Okay, this is actually not a topic of induction machine, but okay, it's fine. Damper bars are used in synchronous machines. Why? For like for hunting and starting, right? I hope you remember, they are used in synchronous machine. One reason is for starting, and hunting is for eliminating the noise, right? The high frequency noises, correct? So they are used in synchronous machines for eliminating the noise. Like hunting basically means the synchronous machine rotates like this, okay, sometimes, so it does not properly rotate. To fix that, we use damper windings, and of course to provide the starting. Skewed rotor bars are again used in induction motors. So rotor bars are skewed for proper magnetic locking of the induction motor. I hope you remember, like these are theoretical points that you need to remember. So properly, for the stator magnetic field and the rotor magnetic field to lock, we skew the rotor slots of the induction machine. Compensating winding, again it is used in DC machine, right? For what reason? Armature reaction, because it reduces the effect of armature reaction. So my P will be pointing towards U, P will be pointing towards U, and U will be pointing towards X. Okay, PUX, PUX, option B and D and my Q will be pointing towards S. Q is pointing towards S. Here Q is pointing towards V. So this is gone, this is gone, this is gone. This is the only option. We can verify it as well. S is pointing towards Y. S, if you see, S is pointing towards Y, and your R is pointing towards V, and your V is pointing towards Z. So whatever we have discussed, that is exactly correct, and that is in the solution as well. Okay, that's how you solve this question. It's just a theoretical question. Let's now solve the next question. So this is the next one, where a power input to a 500 volt 50 hertz. Okay, so the voltage is 500 volt, stator voltage, and frequency is 50 hertz. It's a 6-pole machine, and 3-phase induction motor running at 975 RPM. Three-phase induction motor running at 975 RPM, right? So it is running at 975 RPM. Basically, its rotor speed is 975 RPM, is 40 kilowatt. So input power in this condition is 40 kilowatt. The total stator losses, STL, right, are 1 kilowatt. If the total friction and windage loss is equals to 2.025 kilowatt, the efficiency would be. Okay, so actually so what is efficiency? Basically, what is efficiency for a motor? What have this in percentage? They are asked in percentage, right? If you see, they are asked in percentage. So efficiency in percentage would be your P out, P in into 100%. Okay, so yeah, that is P out, P in over 100%, and I know what is P in. I need to calculate P out. What will be P out? P out will be basically P in minus the losses, because few of it will be gone in the losses. Now a few things if you remember. So if I just draw the equivalent circuit of the induction motor. So here I have the magnetizing part which develops the magnetizing energy. Then I have the rotor part, right? If you remember, I had the rotor and there was this load. This was R2 dash, this was X2, and here I had R2 dash. I'm just drawing the rough rough equivalent circuit into 1 minus S divided by S. Okay, so what used to happen was, this is my load basically, right? So this is the power that is developed after considering the stator copper loss. So what happens? So this part here I get a loss in the, sorry, not stator, sorry, I will mention, I will explain. So this part is the stator winding resistance, right? So this part contributes to the stator copper loss, SCL. Then this part, right, after subtracting that, we develop a air gap power, the power in the air gap due to the magnetic field. Then that magnetic field, and also there are core losses, but have they discussed about core losses? Okay, they have not discussed, so we will assume the core losses to be almost negligible. Okay, and then what happens? No, sorry, the core losses is not negligible. Actually, the core is responsible for generating this. Ignore that statement. So yeah, we develop the air gap power, and after the air gap power, we reach here, right? And some of it will be lost in the rotor copper loss. So this part will be responsible for losses in the rotor copper loss. And then what will happen? Then finally, after subtracting the rotor copper loss, I will get a developed mechanical power. So this power is called as developed mechanical power, that is present at the shaft, and this is also not observed by us. What is observed by us? After subtracting the friction and windage losses that is occurring in the nature mechanically, right? After subtracting this losses, this is the shaft power, or this is the output power that we observe. So we will have to subtract all these losses. Okay, this is not a loss, this is just the generated power. We'll have to subtract the stator copper loss, we'll have to subtract the rotor copper loss, we'll have to subtract the friction and windage loss. Then only we'll get our P out. Now there is a derivation. We will not go into the derivation, but this was a very, very important relation that you must remember, that the ratio of air gap power upon the rotor copper loss upon the mechanical power. Like this will be, trust me, this will come in your examination 99.9% chance. If a question is coming from induction motor, not 99 actually, 90% possibility is there that this thing will be used, this relation will be used. This is equal to 1 S and 1 minus S. The ratio are proportional like this. Okay, this thing you have to anyhow remember. Okay, like there is a derivation, not going into that. Now, what do we know? So I need to get PG, because I know slip. What is slip? Slip, I already know the rotor speed, I know the NS. What will be NS from this information? NS would be equals to 120 F by P, 120 F by P. So that is 20 into 50. 20 into 50, that is 1000 RPM. Okay, that is what my NS is equals to. Okay, that is my 1000 RPM. Right now, what is the slip in this case? I can calculate the slip. Slip will be NS minus NR by NS, that is 1000 minus 975 by 100, sorry 1000. So this will be my slip basically, right? So my slip would be equals to 1000 minus 975 divided by 1000. So that is 0.025. Okay, that is my slip basically. So I got my slip. Now, yeah, we got a slip, right? What is my air gap power? So air gap power will be equals to your input power minus the stator copper loss. Stator copper loss. So what is the stator copper loss? They've given me, right? This is actually S, not STL, SCL. So what is the stator copper loss? 1 kilowatt. What is the input power? 40. So your air gap power is equals to 40 minus 1, that is 39 kilowatt. So air gap power is 39 kilowatt. So this is 39 kilowatt. Now I know everything, right? Because I know what is slip. Slip is 0.025. Correct? So yeah, if I compare 39 upon rotor copper loss, that will be my 1 upon the slip. Slip is 0.025. Correct? So I will get my rotor copper loss. Or directly, I don't even need to calculate all this. Actually, if I just compare this, right, that will be helpful, because I ultimately your mechanical power developed is nothing but the PG minus P RCL. It is the same only. So that's how this thing comes. This relation, that is how this 1 minus S comes. Ultimately, you'll have to remember this. Okay, this thing anyways you can derive, right? So I can directly use it. So your 39 upon mechanical power developed will be equals to 1 by 1 minus 0.025. So your mechanical power developed will be equals to 0.05 plus 1 into 39. So this will be 38.025 kilowatt. Okay, that is my mechanical power developed. Now the output power, right, will be equals to this power minus the friction and windage losses, right? That is my shaft power. Friction and windage losses is this, right? So my output power would be Pmech, so 38.025 minus 2.025, so this is 36. So they've given some round number, okay? So 36 divided by the input power, that is 40. So efficiency is 90%, correct? Your efficiency would be P in upon P out, right? So it will be 90%. So efficiency would be P in, that is 36 upon P out, that is sorry, P out upon P in into 100%. So this will be 90%. This will be your answer for the question. Let's solve the next one. A 8 pole 50 Hz 3-phase slip ring induction motor. So it's a 8 pole 50 Hz. Of course, it will be 3-phase induction motor, has an effective rotor resistance. So basically R2 dash is equal to 0.08 ohm per phase. Its speed at maximum torque. So N R at max torque is 650 RPM. So whenever these kind of things are written, right, maximum torque, you know you will need the maximum slip. Anyhow, you will need the information regarding the maximum slip. So let us calculate it now itself, right? I will read, of course, the next statements, but let's calculate it now itself because maximum slip will be required. Sorry, the slip at maximum torque will be required. So that is actually called as S max. That will be equals to NS. So what is the NS here? NS will be 120 F by P. So 120 into 50 by P. So this is 30 by 2, 50 into 5, that is 750. So this is 750 RPM. So 750 minus 650 divided by 750. 750 minus 650 divided by 750. So that is 0.133, right? So that is my maximum slip. Okay, got it. Cool. And you know what is the condition? So we'll discuss about that. Let's read the next phase. The additional resistance per phase that must be inserted in the rotor to achieve a maximum torque at starting. So we want to achieve a maximum torque at the starting itself. And do you know what happens at the starting? At starting, my rotor speed is 0 because it is just starting. So my starting slip is 1. Okay, so we want this S max and this S starting has to be same. I will discuss about that. Hold on. Neglect the magnetizing current, stator leakage impedance. So there is no stator leakage impedance. So the condition of the slip at which maximum torque occurs is my S max will be equals to R2 dash upon under root of R1 dash R1 whole square plus X1 whole square plus X2 dash whole square. Okay, this is the condition. This comes after the derivative of the torque equation, and after differentiating it, right, we get this condition at what slip maximum torque will occur. Okay, there is a derivation, you can look it up. In our case, they have told me that neglect the stator leakage impedance and the magnetizing current, obviously. So my R1 is 0, my X1 is 0 because stator leakage impedance is 0. So ultimately this S max formula is converted into this value. R2 dash upon X2. Okay, and currently, do I know anything? Yeah, I have been given R2 dash. So from this information, I can actually calculate my X2. Why is it important? I will explain. So my X2, right, will be equals to S max, that is 0.133, that the slip that is currently present, divided by the R2 dash. R2 dash is 0.08. So this will be divided by 0.08. So it will be 1.67 ohms. Hold on a second. Sorry, I'm doing it opposite. Sorry. I'm doing it opposite, right? So it will be 0.08 upon 0.133. Just the opposite. So it is actually 0.6 ohms. This is your X2. Now next what they're telling me, that what resistance must be added so I achieve the maximum torque at starting. So to achieve maximum torque at starting, my S max must be 1, right? Because at starting the slip is 1. So to make this S max 1, what do I need to do? I need to increase the numerator, because the denominator is fixed. If I increase the numerator, then this S max also will increase. I want this S max to be equals to 1. So now what I want my S max to be equals to 1, that is equals to my R2 dash. So R2, or let me write as Rx divided by X2, where Rx is equals to, obviously the rotor resistance is there, plus another additional resistance that I am providing, let's say small r, so that I can increase the overall rotor resistance to achieve maximum torque as starting. So this will be equals to, Rx will be equals to X2. So Rx is equals to X2, that is 0.6, and R2 dash is 0.08 plus R. So your R will come out to be 0.52 ohms. That is what your R will be. So your answer will be 0.52 ohms. This will be your answer for the question. Pretty simple, pretty straightforward, very standard question. And you can expect something like this in the upcoming examination as well. Let's solve the next question. A slip ring induction motor is expected to be started by adding extra resistance in the rotor circuit. So simply we are adding the extra resistance. The benefit that is derived by adding extra resistance in the rotor circuit in comparison to the rotor being shorted is the starting torque will be higher. Yes, right, because we just saw if I add a rotor resistance with the rotor, right, in the rotor circuit, what will happen? The previously there was some other starting torque, right? Now I'm getting the maximum torque as starting itself, so the starting torque will be higher. That's it. This will be the answer. The power factor will be lower. No, power factor actually will improve, but that's not the point. Starting current will be higher. No, starting current won't be higher. Okay, if I'm adding resistance, how can the current increase? The losses at the starting would be lower. No, because I'm adding a resistor, right? Losses on the resistor will be higher. Okay, so you cannot directly comment that losses will be lower, but certainly the starting torque will be higher due to the previous question we directly saw, right? If I'm increasing the rotor side resistance by adding an extra resistance, you see that I am observing that I'm getting a maximum torque at starting itself, right? So that's it basically. So let's solve the next question now. The type of single phase induction motor expected to have the maximum power factor during steady state running condition is, okay. So the type of single phase induction motor expected to have maximum power factor during steady state running condition, maximum power factor. Okay, I think it's the capacitor start and capacitor run, right? So because in capacitor start, what we do, power factor is really bad, because single phase induction motor does not have inherently starting capacity, self starting capacity, right, capability. So what we do, we change the phase shift. Initially it is like we make the phase shift between the main winding and auxiliary winding 90 degrees, so that we get a starting torque, and after it starts, then we change the connections to reduce the capacitance value, so that it runs with good power factor, right? Good, like highest power factor, almost unity power factor. So the reason for that is, like, most of the power that we generate will be gone to the load. Otherwise most of it will be lost in the winding, in the magnetic circuit. That is what we don't want. That's why we want to have maximum power factor, and that is achieved with the capacitor start, capacitor run. With capacitor start, what happens? Yes, we get the starting torque. Here we get the starting torque, but the problem is, while running also, the high capacitance is present, and a lot of magnetic energy is wasted. All of it is not converted to the mechanical energy. So to do that, we introduce an additional circuit known as capacitor run. So during running, the capacitance value will be lower, and basically we don't need the phase shift 90 during running point of view. Only during starting we need the phase shift between the auxiliary and the main winding as 90 degrees. This you will learn obviously once you study the single phase induction motors. Let's move on to the next question. The frequencies of the stator and the rotor current flowing in 3-phase 8-pole induction motor are 40 Hz and 1 Hz. The motor speed is, what is the motor speed? We know that in normal operation of induction motor, the frequency of the rotor will be slip times the frequency of the stator supply. So they have given me the stator frequency and the rotor current frequency. So rotor current frequency is 1 and stator current frequency is 40. So your slip becomes 1 by 40 and it's a 8-pole induction machine. So what is your NS? Synchronous speed, it is 120 into F. Now what is the stator current frequency? 40. 120 into 40 divided by the number of poles, that is 8. Right? So this will be 3 by 2, 20. So this will be actually 30, right? 30, Mr. 0, 600. So your NS comes out to be 600. So yeah, your NS comes out to be 600, right? So if your NS comes out to be 600, now what is my NR? NR will be simply because they have asked what is the rotor speed. So rotor speed will be NR will be NS into 1 minus S. So NS would be, sorry, this will be 600 into 1 minus S, that is 1 minus 1 by 40. So it is simply 39 by 40. So 39 by 40 into 600, which comes out to be 585. So your answer of the question would be 585. This will be the speed of the rotor basically. Right. So yeah, let's solve this question. This question is pretty good. So we have a 4-pole induction motor. Okay, the number of poles of the induction motor is 4. With the inertia constant, let's write this as inertia constant as I, that is 0.1 kg per meter square, which is all in SI units, so I don't need to worry about it. Drives a constant load torque of 2 Newton meters. So the load, it drives a constant load torque of 2 Newton meter. The speed of the motor is increased linearly. So you see the speed is increased linearly from 1000 to 1500 RPM in 4 seconds. Okay. So can you say what is the, so this is the speed, right, in RPM. What is the angular acceleration alpha? Because this thing will be used. So we will actually calculate it. We will actually calculate it later. Let's read the question. Neglect the losses in the motor. The energy in joules consumed by the motor during the speed change. What is energy? So energy consumed, right, would be equals to, okay, they want me to find the energy consumed by the motor during the speed change. Okay. It is increased linearly, so I'm just thinking what shall be the energy consumed by the motor during this phase. So I'm just thinking something. Your angular acceleration is constant. Load torque is constant load torque, right? Like I'm thinking like your energy consumed would be, let me think of it. So what is the power? What is power? Power in linear dimension is force into velocity, correct? And power in curvilinear motion, force becomes your torque and your velocity becomes your omega. So power in curvilinear motion is T dot omega. Okay. And what is my energy? Energy is equals to P dot dt integration from whatever time t1 to t2, whatever I want to do, right? Time t1 to time t2, correct? So so what is the torque? Torque actually is equals to your moment of inertia. So actually what is force equals to? Force is equals to mass into acceleration. Similarly in curvilinear motion, torque is equals to moment of inertia into angular acceleration alpha, right? And here alpha is constant for us. alpha is constant, the angular acceleration is constant. Why? Because the slope of my uh, rotor speed is constant, right? This is the slope is basically the acceleration, not exactly because units are different. This is in rpm. I will have to compute this in radians per second and then only comment, but that is fine. This part is fine. There will be just a multiplication of constant. That part is fine. Okay, so I can just replace my variables over here. That will be much easier because I know I also know alpha. Alpha also you know, right? I know omega is changing basically. That is fine. So my energy will be equals to integration of T1 to T2. What is power? Power is T into omega and T is I into alpha into omega into dt. Now what is alpha? Alpha is actually d omega by dt. Correct? Alpha is actually d omega by dt. So this right can be changed actually. I is constant. I into alpha into omega. Sorry, alpha I into omega into d omega by dt. So dt will be cancelled. So I can say this will be omega 1 to omega 2. That is equals to my E. Correct? This I can only do. Okay, let us not do it. Okay, no. Let us keep. What is alpha? Alpha is d omega by dt. So in our case d omega by dt is just a constant. Correct? D omega by dt is just a constant. So let's not replace it here. So in our case d omega by dt is just a constant. It is just, let's say, some slope of the graph m, but m is just constant, right? Slope of this graph is constant. So this will be actually m into omega into dt, right? If I am not wrong, this is constant. Okay, and okay, your speed is changing. So your speed is function of time, right? Yes, your speed is function of time. Or a easier way what we can do is we can replace this d omega. That is the easier way. That is what I was thinking. But this also will work, I guess. Okay, let's keep it on this one only. So I have basically, right, I into alpha is constant, alpha is constant. So this will be t1 to t2, I into alpha. Alpha is constant, right? Alpha is constant, some m value, omega dt. So I just have to compute the integration from here to here, area under the graph from here to here. But remember, this is in rpm and this omega is in radian per second. Is in radian per second. So how do I, because I have been given the graph of speed in rpm, not in radian per second. So let me convert this omega into its speed equivalent. That is revolutions per minute equivalent. So we know that omega is equals to 2 pi n by 60. Right? So I can replace here omega with 2 pi n by 60. It will not make any difference. Only a constant term will come outside. So I alpha 2 into pi by 60 integration from t1 to t2 n dt. That's all. Now it is much simpler. So everything is in SI units. So I can slowly replace stuff now. So what is alpha? Remember now this alpha also is d omega by dt. Correct? Alpha also is d omega by dt. The problem is we have a, if I find out the slope, this slope will be not equals to d omega by dt. This slope will be dn by dt, right? So if I replace my omega here also, right, with 2 pi n by 60, this will be d of dt into 2 pi n by 60. Ultimately n is changing, other things are constant. So this can be at the outside, this is just a constant, this will be dn by dt, right? So what is dn by dt? It's very simple, right? Change in speed is 500 and change in time is 4. So 500 by 4. So it is 125. So 125 dn by dt is 125 revolutions per minute per second. Okay, so 2 pi by 60 into 125. That is my constant number. Be very careful. This is in revolutions per minute, but d omega by dt is separate. So be very careful here. So now it becomes very simple actually. So this will be I know I is 0.1 kg per meter square, right? Load torque, actually the information regarding the load torque is irrelevant. I don't need the information regarding the load torque. Okay, so 0.1 into 2 pi by 60 whole square, because there 2 pi by 60 is coming twice, here once, into 125 integration of, like, basically the area of this graph, like area of the graph from T1 to T2. What is the area here? So the area, I can calculate the area. So there is a triangle, that is half into base into height is 500, base is 4, plus there is this rectangle, that is height into 4. So this is 1000 plus 4000, that is 5000. Okay, that is 5000. So this is 5000. Now let's ultimately solve this. This will be coming in joules. So 2 into pi upon 60 whole square into 0.1 into 125 into 5000, that is 685.5 joules. Okay, the energy consumed by the motor during the speed change, this will be 685.5 joules. I hope I am correct. Now, is this the only thing that is changing? That is what I am thinking. So this is torque. Okay, torque I have changed. It already has some stored energy. That stored energy is there, right? All it needs is just to increase the speed. I'm just thinking something, because it has a mass connected as well, right? Okay. So what is your torque basically? Actually, one thing I might have missed here. So your torque, right? Your torque is equals to your load torque plus your developed torque. Okay. So your load torque will always oppose your developed torque. So sorry. Your developed torque is equals to load torque plus acceleration torque, right? So whenever the acceleration torque is 0, that means your developed torque is equal to load torque, so it is in steady state, so it is always rotating at a constant speed. But what happens if I want some acceleration, correct? So I have to give additional torque, addition to load torque. I have to give this additional torque, addition to load torque, right? So if I have to give this additional torque, so this is the additional torque basically, this TA, all this whatever I have derived, I into alpha is the additional torque for acceleration, otherwise alpha will be 0. But actually my torque is, this load torque is always there actually. So you're here, right? I should have replaced T with T plus TL, correct? So this will be actually there will be two things here. So this thing will be there, certainly this thing will be there, plus TL into omega integration of dt, okay, from 2 to 4, from T1 to T2. This also will be there. I forgot to include this stuff, and TL is just a constant number, right? And this will be again converted. So I forgot to include this. So your T developed is TL plus TA. Whatever I have done here, right, that was for TA, the acceleration torque. I forgot to include the load torque. Okay, that's my fault. I forgot to include the load torque, because whenever the speed will increase, it has to provide an additional torque for the load as well, right? For the load as well. So this also will consume some energy. So I replace my T with TL plus TA, where TA is this term that is expanded, and I am just including this additional term, but TL is just a constant number, load torque is just a constant number, that is 2 Newton meter. Omega into dt, I will convert this into N dt, right? That is easier for me. So it will be TL into 2 pi upon 60 N dt. Okay. So this part comes out to be 685.39 joules. What about this term, the second term, right? I forgot to derive for the second term. That's my bad. Correct. So if I replace my stuff, TL load torque is 2 Newton meter. So this will be plus 2 Newton meter into 2 pi upon 60. Now what is the area? Area is same, right? Area under the graph, NDT, time duration is also same, right? This is going from T1 to T2. Time duration is same. So we have to consider the load as well, right? Because the speed is increasing. Now previously, if it had to provide 2 Newton meter of torque, now it may have to provide a little bit higher torque because the speed has increased, right? Speed has increased. If the speed has increased, the input power will increase. So all these things you will have to account for. So yeah, this will be, the area will be same. This will be 5000 only. So let me compute this. This will be 2 into pi into 5000 upon 60 into 2. So this comes out to be 1047.19 joules plus 685.39. So which is 1732.58 joules. Okay. Yeah. So it is 1732.58 joules. This is the answer for your question. Just be careful. This question was actually pretty good, and it's actually very conceptual because things are changing here. Let's solve the next question. A three-phase 415 volt 4-pole 50 hertz induction motor draws 5 times rated current at rated voltage at starting. It draws 5 times the rated current. So my starting current is 5 times the rated current, that is a full load current at starting. It is required to bring down the static current from the supply to 2 times of the rated current. So basically my starting current should be reduced to 2 times of the full load current, correct? Using 3-phase auto transformer. So we will use 3-phase auto transformer. If the magnetizing inductance impedance and no load current is neglected, the transformation ratio of the auto transformer is given by. So do you remember what needs to be happening here? So the line current of a auto transformer, how is it changed? So for auto transformer, the line current, right, like the starting current is x square times the starting current at direct online starting. This is the ratio that you must know, like this is a relation, right? So the starting current with auto transformer will be x square times the starting current of the direct online starting, where x is the turns ratio, correct? This was the relation. Now we already know this, right? The starting current is 2 times the full load current for in case of auto transformer, and starting current in case of direct online is 5 times the full load current. So from this will be 2 times the full load current, that is equals to x square into 5 times the full load current, right? From this my x would be equals to 2 by 5 whole under root, correct? So this will be 2 by 5 whole under root, that is 0.632, and this will be the turns ratio for your auto transformer. Let's solve the next question. So this is the next question. A 440 volt 8 kilowatt 4-pole 50 hertz star connected induction motor has full load slip of this. So full load slip is 0.04. The rotor speed at full load. It's very simple. Simply what you have to do is you have to find out NR, that will be 1 minus S into NS, right? So it is 1 minus 0.04 into NS, that is 120 into F by P. So this will be equals to 120 into 50 divided by 4 into 0.96, that is 1440 40 rpm will be your answer for the question. Let's move on to the next question. So the next question is, following columns represent the mode of operation, the range of slip. If it is running in generator mode, what do you know? The slip will be negative, right? Basically, if you remember the torque speed graph, so this was the torque developed and this was the speed graph, right? Speed, there is n. So your torque speed graph would have been something like this. Hold on a second, right? So beyond, so this is the point where my slip is simply 0, where my speed is equals to ns is equals to, sorry, nr equals to ns, where the slip is 0. After this, what happens? The nr is higher than the synchronous speed, so my slip becomes negative. In this region, my slip is negative. In this region, right? In this region, the slip is equals to 1, and here the slip will be greater than 1. Okay. So if it is running in generator mode basically means what? Your rotor has higher speed than the synchronous speed. That is, slip will be negative, and slip is negative in R. So your R will be matched with A. Running in motor mode, if it is running in motor mode, then my slip range will be between 0 to 1. If it is just motoring, so your speed will be greater than 0, rotor speed will be greater than 0 and less than the synchronous speed. So I will be lying between 0 to 1. And if it is operating in plugging, that is the braking region, so braking region, my slip is greater than 1 because I swap the supplies. If the supplies are swapped, then your relative speed becomes nr plus ns. All this has been taught in the full course, so I am not explaining. So your slip will lie between 1 to 2. So here the slip will be greater than 1 and of course it will be less than 2. So this will be the connection. Okay, so A will move to R, B will move to P, and C will move to Q. So A, R, B, P, C, Q. So option A is the correct answer for this question. Let's move on to the next question. So this is the next question. A 10 pole 240 Hz single phase runs at this while driving rated load. The frequency of the induced rotor currents due to the backward field. Okay, this question is interesting, right? Because it's a single phase induction motor. Now in single phase induction motor there are two fields. One is the forward field, one is the backward field. So do you remember what is the relative speed? So if it is a forward field, the field will rotate with the speed of ns and rotor rotates with the speed of nr in the same direction. So the relative speed between the forward field and the rotor is ns minus nr, and this is the frequency at which the induced EMF is generated on the rotor, right, for the forward field. So frequency for the forward field, right, will be equals to so from here I can calculate the slip will be ns minus nr divided by ns. This will be slip of the forward field, that is slip of the forward field into the frequency of the supply. Now similarly there is a backward field. In single phase motors, two fields are generated. One is the forward, another one is the backward. So during starting, both of them cancel each other out. But as soon as the motor is started, the forward field is more stronger than the backward field, so it dominates. So the rotor rotates in the forward direction. But they are not asking that. They are asking me what is the frequency of the EMF generated due to the backward field. So backward field rotates with a speed of minus ns. Because why minus? Because it is rotating in the opposite direction. So minus ns, right? So what is the relative speed between the rotor and the backward field? Because your field is rotating in the backward direction by ns and your rotor is rotating in the forward direction by nr. So what is the relative speed? It is ns plus nr. All these has been taught in the machine's full course, so I will not explain the things here. So this is the relative speed. What is the slip of the backward field? It will be ns minus, sorry, it will be ns plus nr. Hold on a second. Now, okay. So actually your slip is what? Slip is relative speed upon the synchronous speed, right? So it is ns. So what is the relative speed? it is ns plus nr divided by ns, correct? So that is my slip now. That is the slip of the backward field. So this will be equals to 1 plus s slip of the forward field. That's all. So your backward field slip is 1 plus slip of the forward field, right? So what is the slip of the forward field? That I can calculate from here, because I know the rotor speed. I can calculate ns. So what will be my ns? Or you don't even need to calculate the this, right? You can directly put values here. So what is my ns? Ns will be 120 f by t. So 120 into 50 by p, that is 600, right? So your backward slip will be 600 plus 540, because the rotor itself is rotating at 540 rpm divided by 600. So this will be equals to 540 divided by 600. So this will be 1.9. This is the slip of the backward field. So what will be the rotor induced EMF due to the backward field? It will be SB into the supply frequency. So 1.9 into 50 into 50, this will be 95. Although you might see the frequency is very high, but the magnitude is much lower, so it will not affect much. So 95 hertz will be your answer for the question that is present in option B. Let's solve the next question. So this is the next question. A three-phase 415 volts, 50 hertz, 6 pole. This squirrel cage motor drives a constant load torque at rated frequency, rated supply. If the supply voltage and frequency both are reduced by 20%, right? So V by F is constant, right? But both are reduced by 20%. Now what are they telling me? The resultant speed of the motor in RPM, neglecting the stator impedance. So if both voltage and frequency are reduced by 20%, do you know what happens to the resultant field if the load torque is constant? So there is this derivation, right? Your torque, right, developed torque is proportional. So your developed torque is equals to 3. So it is basically your power, three-phase power, developed three-phase power upon omega s, right? And what is the developed three-phase power? It is 3 into 3 by omega s into I2 dash whole square into R2 dash divided by S. I will not say how this came and all those things. You can derive it from the basic diagram, circuit diagram, equivalent diagram, and you will get this value. Okay. Now, if I say my developed torque is nothing but equals to load torque at steady state, right? So my torque, load torque is proportional to 3 is a constant number. Omega s is dependent on frequency, so it will be 1 by f. I2 is just I2. Okay, it will also, will it change? So I2 dash is what? I2 dash is V2, V1, the stator voltage, upon the under root of R1 plus R2 dash by S whole square plus X1 plus X2 dash. Now nothing is mentioned, and also they have told me to neglect the stator leakage impedance, right? If the stator leakage impedance is neglected, so this is gone, this is gone. So approximately like this, right, can be approximated as V1 divided by V1 into S divided by R2 dash, approximately, if I neglect the magnetizing reactance of the rotor as well, right? So approximately this thing, right, your I2 is proportional to this. So your I2 will be proportional to V1 square into S square, right? R2 dash is just a constant number, and don't forget there is a R2 dash divided by S as well. So okay, I can write the R2 dash here, no problems, and I can multiply R2 dash divided by S. So ultimately this comes out, your torque is proportional to S into so V1 square. So I know my V by F, V1 is the stator voltage, V by F is constant. So if I multiply and divide by F on both sides, right, this will be V1 square by F square, which is constant. So F will be there. So I just want to keep it as simplified as possible. So it comes out to be S into F. So basically your S into F will be constant. Because why? Because your load torque is constant. So if your frequency has been reduced by 20%, voltage has been reduced, that is fine. That effect is taken care of. If your frequency has been reduced by 20%, what will happen to your slip? So previously it was S into F. Now I have a new slip S2 into new frequency f2, which is 80%, because the frequency has been reduced by 20%. So your new frequency will be 0.8 into the old frequency. So your s2 would be 1 by 0.8, that is 1.25 of times of the old slip. So that's how we can actually calculate the speed. Now I will calculate what was the slip previously. It was operating at full load. So at full load its speed is 960 rpm. And what is the synchronous speed? Ns, that is 120 into f divided by p. So this will be 20 into 50, that is 1000 rpm. So what is the slip in this case? Slip at full load, that is in the initial condition, it is 1000 minus 960, that is 40 divided by ns, right? That will be 0.04. So 40 divided by 1000, 0.04. So slip is 0.04 in the old case. So in the new case, what will be the slip? 0.04 into 1.25, that is 0.05. So if the slip is 0.05, what is the speed of the rotor? So speed of the rotor would be nr will be equals to 1 minus new slip s2 into, obviously synchronous speed will not change. So this will be minus into 1000, right? So this comes out to be 950 rpm. So your speed will be reduced by 10 rpm. That will be your, this should be your answer for the question. If you have done this, then you are wrong. Okay, so till this point everything was good, correct, but here you are wrong. Why? Because your synchronous speed also has changed to ns2. Why? Because your frequency has changed, right? It has changed to f2. So be very careful here. So while applying this, be very careful. Actually, what is the proper formula? Because your s into f is constant, right? Generally they say basically your ns1 minus nr1 equals to ns2 minus nr2. So from this you can directly actually calculate. Like there is a derivation, you can derive it, it will come like nothing, right? You just replace your slip with the ns minus nr value, it will come. I will prove it in both ways. So in this way, what was my synchronous speed? 1000. What was my rotor speed? 960. What is the synchronous speed in the second case? It is 120 into f. F is now 40 hertz because it is 80%. 80% means 1 by 5, yeah, 40 hertz upon p. Pole is 10, number of poles is 10. How many poles? Sorry, number of poles is 6, right? Sorry, number of poles is 6. New frequency is 40 hertz because we have reduced the frequency, right? So this will be 20 into 40, that is 800 rpm, right? So this will be 800 rpm minus nr2. So from this you will directly calculate what is your nr2. nr2 would be, this will be 4760 rpm. If you are not convinced with this answer, you can put it here, right? So your nr2 will be equals to 1 minus s2, 1 minus 0.05 into ns2. What is the new synchronous speed? 800, because the frequency has reduced, so the synchronous speed also will reduce. So this will be 800. So this will be equals to 0.095, sorry, 0.95 into 800, that is 760. So in both the cases you will get the same answer, right? So this is just a derivation, extension of the formula, that's all. So be careful while solving these kind of questions. Let's move on to the next question. A 3-phase 50 Hz 6-pole motor runs at 960. The stator copper loss, rotor copper loss, sorry, stator copper loss, coal loss, rotational losses, everything is neglected. The efficiency of the motor is, it's very simple. So basically, like one of the questions I have done previously explaining all the losses, so I will not explain stuff here. So that has already been covered previously in this video itself. So basically we have to find out the efficiency, that will be your P out upon P in into 100%. Okay, P out upon P in into 100%, right? So what is your, I don't know what is my P in, right? I don't know what is my P in, but what is my P out? P out will be P in minus losses. In losses there will be multiple kind of stuff, right? One will be the stator copper loss, that they have told me to neglect. Then there will be the coal loss, that also they have told me to neglect. Then there will be rotational loss, that also they have told me to neglect. there will be some rotor copper loss, right? Only loss that I have to consider now is the rotor copper loss. Everything else they have told me to neglect, and I know the relation between rotor copper loss and the air gap power, because then my input power will be equals to my air gap power. PG will be P in only, because stator loss, coal loss are not there, correct? So yeah, my input power is this, that is my PG, air gap power, and I know the relation between PG and rotor copper loss, that is basically your 1:s, and basically this is the mechanical power output to the shaft, that is 1 minus s. So essentially, right, this value is nothing but 1 minus s of the air gap power, that is input power. This is my P out. So basically we got the ratio of P out over P in. I'm going a bit fast because all these things have been explained in one of the questions earlier. So P out by P in is equals to 1 minus s into 100%. That ultimately I will have to calculate the slip. What is the slip? You see, your frequency is 50 Hz, pole is 60, so your ns is 1000 rpm. You can calculate that. Ns will be 120 f by p, and your slip will come out to be 0.04, correct? So we'll put it 0.04 here, so this will be actually 96%. Okay, I'm doing it a bit fast because these things you already know, how to calculate the slip, how to calculate the synchronous speed. These things you like, this is the first thing that you study in induction motor. So 96% will be the answer for this question. Let's solve the next question. This question is pretty interesting, where a three-phase star connected slip ring induction motor has these specifications. These are the stator impedance, and this is the rotor impedance. The per phase stator to rotor effective turns ratio is 3:1. Okay, so they have given me the effective turns ratio, right? That is interesting. And what are these? So XR dash and RR dash all are referred resistance and referred reactance on the stator side. I hope they have mentioned this, right? They have not mentioned. They should have mentioned, actually. They should have mentioned. Okay, no worries. These are all referred. Okay, yeah, they have mentioned, right? So these are all the parameters that are referred to the stator side. Very important. These are all parameters referred to the stator side. So why? I will explain. The per phase this turns ratio is given. The rotor winding is also star connected. Rotor winding is also star connected, and stator winding is also star connected. The magnetizing reactance and coal loss of the motor can be neglected. To have maximum torque as starting, what is the value of the extra resistance connected on the rotor side in series in each phase of the rotor winding? So first, let's calculate what is the extra resistance connected with the rotors referred to the stator side, and then I will refer it to the rotor side. Okay, so we know this thing, that the maximum slip condition is basically my R2 dash, the rotor resistance referred to the stator, upon the R1 dash whole square plus x1 plus x2 dash whole square. Basically x2, these are all like stator and rotor resistance, stator and rotor whole square. This is the condition, right, for maximum slip. And they want the maximum torque. Sorry, this is the condition for maximum torque, and they want this to happen at starting. At starting, the slip is 1, so this needs to be equals to 1. If you put the values, if you put all these values over here, you will see that this will not yield you 1. That's why we add an additional resistance to increase this numerator, so that I get a maximum torque at starting. So ultimately what you have to calculate, your slip SM will be 1, your RR dash is 2.5 plus some resistance R X upon this value 3 square plus XS square. XS is, sorry, XS plus XR square, 2 plus 2 whole square. So this will be 3 square plus 4 square under root, that is 5. So your Rx will be equals to 5 ohm. Rs will be equals to 5 ohm, right? That is the amount of external resistance. So not 5 ohm, sorry, 2.5, right? Because 2.5 has been subtracted, it will be 2.5. But this is referred to the stator, correct? Whatever I have done, all these values are referred to stator. I will have to compute, because they have asked me refer to the rotor side. Refer to the rotor side. So I will have to refer this resistance to the rotor side. How will I refer it? So I hope you remember the referring formula of transformer, right? So we do, if I have a resistance and I want to refer it to the other side, so I will have to write the turns ratio of the other side on the numerator first. So it will be NR, and then in the denominator, the turn number of turns on the side which I am in currently, that is NS whole square. That is how referring works. So NX Rx on the rotor side. So this will be 2.5 and turns ratio on the rotor side. So they have given me stator to rotor ratio, but I want rotor to stator. So it will be inverse. So this will be 1 by 3 whole square. So just give me 1 second. Divided by 9. That is 0.278 ohms. This is the value of the external resistance that needs to be connected on the rotor side. So I hope these things are clear. If you could not understand how this maximum torque and all these things have been calculated, I have already done a similar question just before this. You can go and check that question. There I have explained this in a broader manner, because I have already done that question. That's why I am not again explaining the same thing. I am just doing something else here. Okay. So 0.278 will be your answer. They have told you to round off to 2 decimal places. So this will be 0.28 ohms. This will be your answer for the question. Okay. So a 3-phase squirrel cage induction motor has a starting torque of this and full load, and a maximum torque of this much percentage of full load torque. See, starting torque is 100% of the full load torque and maximum torque is 300% of the full load torque. Neglecting the stator impedance, the slip at maximum torque would be. What is the slip at maximum torque? So we know this one formula, the ratio of the maximum torque to full load torque. This will be equals to 2 upon SF upon SM plus SM upon SF. Okay, this formula you will have to remember. This is a very handy formula, and they have told me that your starting torque is same as your full load torque. Okay, and your maximum torque is 300% of the full load torque. So basically your TM is 3 times the full load torque, correct? So this will be 3 will be equals to 2 upon SF by SM. So, but this is not useful to us, right? Because I don't know my SM and SF, both of these I don't know. So actually what we can do, we can compare the maximum torque and the starting torque. Then this formula will be replaced with basically, right, this is one relation. Another relation is between the maximum torque and the starting torque. So basically you will have to replace your SF with 1, because the slip at starting is 1. So that's why you will replace your SF with 1, right? So this will become TM. So this will be 3 times the full load torque. So this will be 3 TF upon TF, because your starting torque is same as full load torque. This will be 1, right? This will be SM square plus 1 into SM. So SM square plus 1, that is 2 by 3 into SM. SM square minus 2 by 3 SM plus 1 equals to 0. Okay. So yeah, if I solve for this, this will be minus B, SM will be equals to minus b plus minus b square minus 4ac. B square, hold on a second, this will go on that side. B square minus 4ac upon 2a. Okay, something wrong is happening. I'm doing some sort of silly mistake, right? Yeah, just I have just made a one small mistake here. I also sometimes tend to forget the formula. This will be actually, here I will have, this will be TF by TM. I'm sorry, right? How can you remember it? So not a straightforward way, but one thing you can think is SF is generally very small. The full load slip is generally very small. Now if the full load slip is generally very small, then what will happen? Then this value will be almost negligible, right? Then this ratio will be 2 into SF by SM. 2 into SF by SM, right? And SF is very small, so 2 into that also will be very small, and we know our full load torque will be less than the maximum torque, so that's why the numerator is smaller value, denominator is larger value. That's how you can confirm and verify whether whatever you have done is correct or not. Okay, you write the formula, then you verify according to your intuition. So I did not do it, so I was wrong. So here also things will interchange, so this will be actually, that's why I was getting a wrong answer, T starting upon TM, so this will interchange here. Things will interchange, so basically this 3 will come down, so the equation will change now, so this will become 6 SM, right? 6, so this will be minus 6, so here I will have 36, this will be 6, so minus 32 under root. So of course I will not choose the plus 1 because that will make the slip greater than 1, that is not possible. So I will choose a negative number, negative root, so this divided by 2, so ultimately your slip, maximum slip, comes out to be 0.171, correct? And what have they asked? They have asked the maximum slip at, you will put 0.171 and you will be wrong because they have asked in percentage. So be very careful here. They are also very smart. So as they have asked in percentage, this will be 17.1 percentage. This will be your answer for the question. Okay, this was an iron question actually, and I'm not sure, are they supposed to ask this difficult, like not difficult, but this depth of the concept in iron, because in induction motor, in iron, this is not the core subject for iron, right? So I'm not sure about this. Okay, just give me 1 second. Yeah, so that was one thing. So yeah, let's move on to the next question. The operating time of developed torque TEM, okay, this is the developed torque, and speed is given. Operating region of an induction motor drive is given in the shaded region. Okay, this is the shaded region that is given. The operating developed torque and the, sorry, this is the developed torque TEM and the speed, and this is the load torque. Load torque varies like this. Okay, now they are asking me the motor drive moves from initial operating point O. Okay, so initially it does not develop any torque, right, and it moves to the final operating point S, because at steady state, of course, the developed torque and the load torque will be same. The motor drive moves from initial operating point to O and to S. Which one of the following trajectories will take it to the shortest path? So it will go from O to then Q, then it will go to R, then it will go to S. O, then P, then S. O, then E, okay, and then it will go to S, and O, then F, and then it will go to S. Which one will take you to the shortest possible time? That is what they are asking. So what takes the shortest possible time? So what is the time dependent on? So I want my speed, right? I want to reach this steady state. From I am at initial operating point, it is at rest, so my omega is 0, and I want to get to some omega f, right? What is dependent on it? So if I want to increase my speed, I have to increase my acceleration, right? If my car accelerates at 10 meters per second, then my speed will be 10 meter in 1 second, 10 meter per second. Sorry, if my car accelerates in 10 meter per second square, then my speed after, or velocity after 1 second, will be 10 meter per second, right? If my car accelerates at 5 meter per second square, then my speed or velocity would be 5 meter per second after 1 second, and my speed will be 10 meter per second after 2 seconds. Right? These things are the basic things. So here we see that it is dependent on acceleration. So wherever my acceleration is the highest, I will reach my desired speed. And who is responsible for acceleration? Basically, in case of a car, right, force. The more force I will give, because force is equals to mass into acceleration, right? More force, more acceleration. Similarly, in case of curvilinear motion, your torque is responsible. Your torque is equals to I into alpha. So if I increase more torque, I will get more acceleration. Correct? More torque, more acceleration, more angular acceleration. So I got more angular acceleration. So that is what I need. I need more torque. And what is torque dependent on? Basically, if torque is what? Torque is developed torque minus the load torque, the difference, right? Higher the difference, higher will be the acceleration. At steady state, developed torque and load torque will be same, hence acceleration will be 0, hence velocity will be constant. So we want our difference of the torque to be maximum. So this is my load torque, right? And this is my developed torque. So I want the difference to be maximum, and I see if I go from 0 to Q, right, O to Q, then I see this difference is always high, right? If I go from O to P, this difference is low. So I get the highest acceleration if I directly go from 0 to Q and then Q to R, and then from R to S. So that's why the acceleration will be highest in the first option. Otherwise, you see, if I go from 0 to P, this acceleration will be low, right? This difference is lower compared to this difference. And if you go from 0 to F, this difference is always low, right? So this will not be that much. So option A will be your correct answer for this question. So let's now move on to the next question, right? So let me read this. I think, yeah, we have two more questions. A 3-phase 400 volt 4 pole 50 hertz star connected induction motor has the following parameters. Neglect these things. Okay. The motor is run with constant VYF control. For maximum starting torque, the motor and the frequency output respectively would be what? Okay. For runs at constant VYF control. So what is the for maximum starting torque? So I want the torque to be maximum at starting. So what should be the voltage and corresponding voltage and frequency values? That is what they want. Okay. So when do we get the in constant VYF control? What happens in constant VYF control? I want the torque to be at maximum, right? I want the torque to be maximum. If I want the torque to be maximum, there are two things. Either I can add a rotor resistance. So I hope you remember the formula for condition for maximum torque. The slip at maximum torque is R2 dash upon R1 whole square under root plus X1 whole square plus X2 dash, sorry, not X1 whole square, X1 plus X2 dash whole square. This is the condition, right? And they have not given me any R2, right? R1, sorry. They have not given me any stator resistance. So they are asking me to neglect the stator resistance, right? So essentially your condition is converted into R2 dash upon X1 plus X2 dash. Now we never actually discussed that we can change the frequency. If I change the frequency, what will happen? Your reactance will change. There are two ways, right? So I want my maximum torque to occur at starting. If I want my maximum torque to occur at starting, basically my slip must be 1. If my slip is 1, that means this value must be equals to 1, correct? Now if this value is 1, there are two ways. Generally your SM will come something lower than 1. So either you can increase your numerator or we can reduce our denominator. So previously we learned that if I add my resistance, then I will get the maximum starting torque. Now if I reduce my reactance, that also will work, because what will happen? Essentially your reactance is proportional to F, right, frequency. So if I reduce my reactance, then that will help. So basically, let's say your reactance is equals to what? It is 2 pi FL. So basically, let's say if your reactance was initially X and you change your reactance to X dash, right, or X X2, let's not keep it x2. How do I change? Let's keep it to xf, or a new reactance basically. Then essentially their frequencies will be, they will be related with their frequencies only. That's all. So I know all these values. I know what is x1 plus x2. I know all this, right? So I can actually compute what will be the new reactance. So your new reactance, right, xf will be some f dash. I don't know what frequency I need to set, so I will calculate that upon the previous frequency, that is f, that is 50, into the previous reactance, that is x. So all these values I can change to this value, right? Because I can change my reactance, so that I will reduce my reactance, so that this value will come out to be 1. Because now if you put, right, if you put R2 dash, if you put xs, like R2 dash is nothing but the rotor resistance, right? If you put the rotor resistance, if you put these values, you will see that currently what I am getting, x1 equals to xs equals to xr dash equals to 2 ohm, and this is 1 ohm, right? So this will be 1 plus 1 by 4, that is 0.25, which is not equals to 1. So certainly I have to reduce this. So certainly I have to reduce my x1 plus x2 dash to 1, then only sm will be 1, right? So how can I reduce it? So previously it is 4, I want to reduce it by a factor of 4, right? I want to reduce it by a factor of 4. So basically this factor f dash upon 50, right, should be equals to 1 by 4, so that it reduces it by a factor of 4. I need to reduce my reactance by a factor of 4, hence this will be 1 by 4, or you can take the ratio, you will get the same value. So ultimately your new f dash will be 12.5 hertz. This will be your new frequency, right? If your new frequency is 12.5 hertz, and previously if your voltage was 400, right, ultimately if it is star connected, actually what we do, uh, uh, so your phase voltage is what? Phase voltage will be 400 by root 3. Okay, so we compare this ratio, phase voltage upon the frequency, that is 400 by root 3 upon 50 hertz. Previously it was this, and we are doing V by F control, so both of them are constant. So this will be like this is the previous value. Now in the new value, I don't know what is the new line to line voltage or new phase voltage, right? New V phase dash. I know the new frequency, that is 12.5 hertz. From this I will be able to get my phase voltage, that will be 100 by root 3. This will be the phase voltage, but I want to compute the line voltage. So new line voltage will be 100, because I have to multiply by root 3, correct? So yeah, so this will be 100 and 12.5, and anyways you can observe 12.5 is only present in one of the options, so this also option will only be correct, right? You know it, but still we wanted to calculate the voltage as well. Let's now solve the last question. This came in iron branch. So a 2-pole 50 hertz 3-phase induction motor supplies power to a certain load at 2970 rpm, right? So it's a 2-pole, it powers this. The linear relationship between synchronous speed and 95%, the torque speed curve of this machine follows a linear relationship uh, between synchronous speed and 95% of the synchronous speed. So basically your torque speed curve is somewhat like this, and it is telling me that when my rotor speed is 95% of synchronous speed, and at synchronous speed, right, this part is linear, and I know basically what happens in high slip region, what happens. So what is the okay, let me solve this first. Assume mechanical and stay losses to be 0 if the load torque is doubled. If I am doubling the load torque, TL dash is 2 into TL, the new operating speed of the motor will be, okay. So do you know what is my developed torque? It is equals to the developed power, 3-phase developed power upon omega s, correct? This will be equals to 3 into I2 square, I2 dash whole square into R2 dash by S by omega S, right? And I2 dash itself is voltage by the resistance whole square, correct? And if your slip is very close to 1, right? So your I2 dash is equals to voltage under root of R1 plus R2 dash by S. Okay, let me do it properly. is equals to R2 dash is equals to V by under root R1 plus R2 dash by S whole square plus X1 plus X2 dash whole square. So what happens when the slip is very near to 1, high slip region? So this will be almost, this thing will be almost constant. So it will not even vary. So this I2 will be almost constant. So roughly what I can say, this will be almost constant in high slip region. So your developed torque will be proportional to 1 by S. So that's how they say that it is kind of following a linear relation, correct? So if your at steady state your developed torque will be equals to your load torque. So previously what was the slip? So previously it was 2970, right? 2970. So what was the slip in the initial case? So what is your ns? Ns will be 120 F by P. So 120 into F by P. So it is 2 pole. So 60 into 5, that is 3000 RPM. Sorry, 3000 RPM. Ns is 3000 RPM, and your slip would be 0.01, right? 3000 minus 2970 divided by 3000, right? This is your slip in the case 1. In the case 2, what will happen is okay, in the case 2, so it will be TL upon 2 TL upon TL dash will be equals to 1 by S upon 1 by S dash, the new slip, right? So your torque has doubled. So your TL dash is 2 into TL equals to old slip, that is 1 divided by 0.01 upon 1 divided by S dash. Yeah, here, like, okay, I just thought of something. I am doing something wrong, right? So this derivation was for high slip region, because uh, it was actually around here. So when the slip is very high, right, that was the derivation. Here the slip is low actually. They're talking about when it is very close to synchronous speed. When my rotor speed is very close to synchronous speed, it is talking about the low slip region. Okay, I'm sorry. This was all of this was discussed for high slip region. Okay, if my slip is very low, so this was discussed for this, right, was for high slip region. When my slip is very close to 1, that means just at starting. So sorry, I was so sorry. I was talking about this region. I just this came into my mind. We are talking about this, right? So here it is a low slip region. S value is very small. If S value is very small, let's say 0.01, right? So this component will be very large. So then I cannot assume this to be constant. Then this will be equals to V upon, like, this will be very dominating compared to the other components. So this will be almost R2 dash by S, and I am doing here I2 dash whole squared. So this thing is wrong. If I am squaring it, so this thing is proportional to I2 is proportional to S, right? V2 by R2 dash is constant. So if I square it, it will be proportional to S square, and already another S is there. So S and S will be cancelled. So the developed torque will be proportional to slip. That is what they mean when they say that it is operating in linear region. It is related linearly. It is related linearly at near to synchronous speed. That is what they mean. That your developed torque will be proportional to slip. So I was wrong here. It is not 1 by S. 1 by S is for the high slip region, and S is for the low slip region. So this anyways you learn while studying induction motors, correct? So I was wrong here. So it is low slip region. Hence now we can do. So your new torque is 2 TL and your old torque is TL. Your new slip is S dash and your old slip is S, right? So your S dash will be 2 times the old slip, that is 0.01. That is what we have computed in the previous step. So that will be 0.02. So now I can find out the rotor speed. It will be 1 minus S dash into NS. So it will be 0.98 into NS, that is 3000. So 0.98 into 3000, it comes out to be 2940 RPM. That is the answer of our question. So with this we are done with induction motor. Now we will begin with synchronous machines. So let's begin. So this is the first question. A three-phase synchronous motor draws a 200 amperes of line current. So the line current drawn by the motor is 200 amperes from line at unity power factor. So my cos theta or cos phi is 1 at rated load. So 200 amperes is the the load is rated. Considering same line at voltage and load, the line current at power factor 0.5. So if my power factor is 0.5, what will be the new line current? That is what they are asking me, right? Same line voltage is connected and same load is connected. Now if same load is connected, it will consume the same power. What is it? Like ultimately synchronous motor is delivering a load that is consuming some power. Yeah, you are correct that it is actually a load torque to the shaft. A load is connected that is actually taking some torque. You are correct, but ultimately this torque comes from the power generated from the motor, electrical power generated from the motor, and then it gets converted into the torque, that I know. But ultimately if your load is constant, your power also will be constant. Because why it will be constant? Remember, your load is constant, that means TL is still present, and your power output of the motor is equals to omega into PL. So TL, right? Omega into TL. And in a synchronous motor, the speed is constant. So speed is always constant. It is equals to synchronous speed, and load was also not changing. They are telling me same load. That means load torque is also constant. Hence, your power also has to be constant. I hope this makes sense now. No one will explain you like this, right? Everyone will say power is constant. You're done. Solve the question. But I will explain you each and every point wherever it is required. So power is constant. Now I can use my formula. So what was the power previously? So assuming without I don't consider losses because nothing has been mentioned. What was the power previously? Previously the power was root 3 VL IL cos phi, right? That is equals to root 3 VL. I don't care whatever is the line voltage because I don't even need the information. I will tell you why. My line current is 200 amperes. Just give me 1 second. Oh no, 200 amperes. Line current is 200 amperes at unity power factor. That is equals to root 3 into line voltage is not changing. They have told me it is VL only. Line current will obviously change, IL dash, and now your new power factor is 0.5. They have mentioned. So I will replace this to 0.5. So of course what will happen? Essentially your line current will double basically. So now your line current will be 400 amperes, which is present in option D. Let's solve the next question. This is the next question. A 220 volt line. So my line voltage is 220 volt. And star connected synchronous motor has a synchronous impedance ZS of 0.25 plus J 0.2 ohm per phase. The motor draws the rated current of 10 amperes. At a power factor of 0.8 PF leading. Okay. The RMS value of the line to line internal voltage would be, what is the RMS value of the line to line internal voltage? So basically, right, we can draw the per phase model. It is a star connected load. So what will be the V per phase? So it is a synchronous motor, correct? So I have a motor. So they're asking me what is the line to line internal voltage. So here I will have the terminal voltage, right? And then I will have the ZS RA plus XS JXS, and then ultimately I will have the motor, correct? So ultimately what they are asking me is, actually I should not draw this motor. Ultimately what they are asking me is, so this is the internal power factor, internal voltage of the motor, right? EF. This is the terminal voltage where I am applying, where the user is applying, and this resistance is the armature resistance, that is 0.25, and this reactance is the synchronous reactance, that is 0.25. It is a, nothing has been mentioned, we will assume it to be cylindrical motor, correct. And I know my Vt. So this is the per phase model, correct, per phase model. Right, if it is the per phase model, then this will be 220 divided by root 3, right, because it is a star connected. So this is my voltage here, 220 divided by root 3, it is in volts only, correct. Okay, now I know the current, that is 10 amperes. I know the power factor of the current, so all I need is to calculate EF. So like there is a derivation of this, I will not derive it, I will directly solve it. Okay, so what will be the so what are they asking? They are asking me the RMS line to line internal voltage, line to line. Remember they have asked line to line. So what I will do is, first I will calculate the phase voltage, and then I will multiply by root 3 because it is a balanced system. So this will be equals to, like there is a derivation, you can, or you can simply solve it, right. Your EF will be, you can simply use KVL and you can solve it, but I am using formula because that is easier, because anyways we have to remember it if I want to solve any question in synchronous motors. So this will be actually equals to, for a motor, this was Vt cos theta minus IARA plus, this will be whole square, Vt sin theta. Now what is the load? Load is unity power factor, sorry, load is leading, cos phi is leading, okay, it is leading. So for leading, what happens is we change the sign, whatever the sign was there, we change it, okay. I hope you are watching the revision X notes, there all these things are written. So the sign will be changed, so this will be plus IA XS, okay. So this thing, how to remember all those things, you have to figure out, everything is there in revision X notes. So this will be equals to this. Now if I equate this, this will be what? So okay, let me solve it. So this will be 220 by root 3, 127. So this is actually 127 into cos theta, that is 0.8 minus IARA. IA is 10 into RA is 0.25. So it is 99.1 whole square plus this will be 220 divided by root 3 into sin theta. Sin theta is, cos theta is 0.8. What will be sin theta? Sin theta will be 0.6. So 0.6 plus IAXA. So this will be 25, that is 101.21 whole square. So this square plus 99.11 square under root, so which is 141.65 volts EF per phase. So that is the voltage right now. Now we got the per phase voltage, right. Now what we want to do is we want to compute the line voltage, because there was a line voltage. So I will multiply this by root 3, so that will be 245.35 volts. So there was to round off to 2 decimal places. So yeah, 245.35 volts will be your answer for the question. Pretty simple, straightforward, not that difficult, just some formula based problem. Let's solve the next question. A 3-phase cylindrical generator has a synchronous reactance XS and negligible armature resistance. So whenever this happens, you should feel very happy, okay. Then your formulas are very simplified. The magnitude per phase terminal voltage is VA, okay, per phase terminal voltage, so that is my Vt, and magnitude per phase induced EMF EA. Consider the statements P and Q. For any 3-phase balanced leading load connected across the terminals of the synchronous generator, Vt is always more than Ea. Okay, this part is interesting. So whenever they are talking about a balanced leading load connected to a synchronous generator, if a leading load is connected to a synchronous generator, what happens? My synchronous generator is so if a leading load is connected, right, my synchronous generator, so I will not have to provide any excitation there because the load, so if the load is leading, actually what happens, if the load is leading, the effect of armature reaction for a synchronous generator, if the load is leading, the effect of armature reaction for a synchronous generator is magnetizing. Okay, if it is magnetizing, so I will have to under excite my generator to get to the same voltage. So actually if the load is leading for a synchronous generator, okay, all these have been covered in the full course and in the revision X notes as well, all these things have been covered, right? So if the load is leading, your generator will be magnetizing and it will be under excited because we will have to under excite because we don't need to deliver that much amount of flux, that's why it will be under excited. And if it is under excited, the condition for under excitation mathematically was EF cos delta EF cos delta less than Vt plus IA RA cos theta. Okay, in our case we are very lucky that our RA is 0, right? If RA is 0, basically your EF cos delta will be less than Vt. Okay, so if RA is 0, EF cos delta is less than Vt. So in this case, what is that telling me? That Va is always more than Ea. So this statement is for a three-phase balance leading load, the terminal is Va is always more than Ea. So if my cos delta will be something equals to 1 or something less than 1, Vt will be okay. I cannot directly comment here. You cannot directly comment here. Okay, cannot comment. Why? Let's take an example. So they are telling me that your Vt is always more than Ea. Your Vt is always more than EF cos delta. That is correct. But your Vt is always more than EF. Is it correct? No, right? Let's take a very basic example. So let's assume in the first case where my delta power angle is 0. Okay, in this case, let's assume that my EF. So what will happen here? That if my delta is 0, then you will say that your EF cos delta is 1, then your EF is less than Vt, then this statement will be valid. But your power angle can be something non-zero, like your power angle can be something non-zero as well. Yeah, it can be. Let's assume that your power angle is 60 degrees. If your power angle is 60 degrees, then what will happen? Then this will be converted into EF into 1 by 2 less than Vt. So EF is less than 2 Vt now. It is not less than Vt. So let's take for numbers. Let's assume a number which satisfies this condition. Let's take that EF is 100 and Vt to be 90. Is this condition satisfied? Yes. Is my Vt greater than EF? No. Your EF was 100. So there is a problem, correct? So this will always not be true. So first statement is not always. So they are telling me always. No. It will certainly be not always true. It depends on the power angle delta. How did this came? Go and watch the short like revision X notes. There this has been derived. Unfortunately, you will have to remember it. You will have to remember it. Like you can understand it from this equation as well, from here as well, but it's very tedious. It's very lengthy. So this is the easy way out. Okay. So yeah, that was one thing. Now let's come to the, this was the for the statement P. For the statement Q. For any three-phase balanced lagging load connected across the load, VA is always less than EA. Now a balanced lagging load is connected. If a balanced lagging load is connected, then this condition will just be reversed. Okay, whatever I discussed, that will be reversed. Your generator will be demagnetizing. So then for the statement Q, your EF cos delta will be greater than VT plus IARA cos theta, where theta is the power factor angle. I hope you know. RA is 0. So you will say that my EF cos delta is greater than VT. My EF cos delta is greater than VT, right? EF cos delta is greater than VT. What they're telling me, that my VT is always, VT or terminal voltage VA is always less than EA. This is certainly true. Certainly it is true. It will always. So here, can I write this? That my EF will always be greater than VT. Can I write this statement? Yes, because your cos delta, the limit of your cos delta is between 1 to 0, right? So basically what I am doing, let's say this number is 100, right? This is 100, and then I am multiplying a number that is less than 1, that is, let's say 0.8. So 80 has to be greater than VT. Let's assume VT is, to satisfy this condition, let's assume 60. So certainly my EF will be greater than this, because I am multiplying a number less than 1 to reduce this, right? And then I am saying that reduced number is greater than VT. Certainly the greater number will be greater than VT, right? So I am reducing my EF, then I am saying that reduced number is greater than VT. Certainly the EF will be greater than VT, right? Because it is already higher than the reduced number. So certainly EF will always be greater than VT in this case. For lagging, certainly I can comment EF will always be greater than VT. Now one thing to note here is, can you comment the same here, that your EF will be always greater than VT? No, because this inequality sign has changed. So this cos delta gives me some problems. Okay, so that's why we cannot certainly say anything here. So in case of leading loads, right, you can never say. In case of leading loads, what happens is your EF can be greater than VT, it can be less than VT, it can be equal to VT. But for lagging loads, your EF will certainly be always be greater than VT, okay, if it is a generator. And trust me, in all the other institutes, they will just write this as a short note, but they will not explain you the mathematical proof. So I have explained you the mathematical derivation as well. For motor, everything whatever I said will be just opposite. Whatever I have said for generator, for motor, everything will be opposite. That's it. Okay. So yeah, so P is false, Q is certainly true. So option A is correct. Okay. Yeah, let's solve the next question. This is the next question, right? So a single phase 50 Hz synchronous generator on group control was delivering 100 megawatt power to the system. Due to increase in load, the generator power had to be increased by 10 megawatt. Okay, so generator power had to be increased by 10 megawatt. As a result of which the frequency dropped to, so previously the frequency was F naught was 50 Hz, right? Or let's assume F was 50 Hz. Now your frequency has been dropped to 49.7 Hz, 75 Hz. Further increase in load in the system resulted in frequency of 49.25 Hz. Further increase in load in the system resulted in frequency of 49. Okay, further we increase the frequency further, and the frequency got reduced to 49.25 Hz. At this condition, the powers in megawatt delivered would be, okay. So it was delivering 100 megawatt of power, right? And we know the governor group characteristics is something like this. It is something like this, right? So it was like, it is constant, even though they have not mentioned, it is like a linear relation, right? So this axis will be my frequency, and this axis will be my power. So whatever the power increases, as I increase the power, the frequency also will reduce. This is the governor group characteristics. Now initially I was at 50 Hz, for a load of 100 megawatt. Let me write, okay, sorry, this will be 100 and this is P in megawatt and this is 50, correct? And then what happens, then I suddenly increased my load to 110 megawatts and the frequency reduced. So this is 110 and this is my new frequency, that is 49.75. Then I increase my frequency further and I reduce my I increase my load further, which reduce my frequency to 49.25. So ultimately, first my task would be to calculate this, right? This value. So if I am able to identify the slope of this line, I can easily calculate this value. So how to calculate this slope? It's very easy. It is, the slope of this line would be delta F upon delta P, correct? That is the slope of this line. So what is the change in frequency? So the change in frequency is 49.75 final minus initial. So it is minus 0.25, correct? And what is the change in the load? It is 10 megawatt. So this is the delta F upon delta P. Now I got my slope of my straight line. So can you now calculate, if I'm at this point, how much power will be reduced? It's very easy, very simple. Let's say I'm at this point currently. So what is the delta F from here? Delta F is this, correct? Delta F is this 49.25 minus 50. So it is minus 0.75 divided by delta P. Now that is what I have to calculate, correct? Final load, that is Px, minus the initial load, that is 100, correct? Now the slope from here to here and here to here should be same because it's a straight line, right? So this slope will be equal to this value, that is minus 0.25 by 10. So your Px is equals to Px minus 100 is equals to, this will be 30 equals to 30. So your Px would be equals to 130. So your 130 megawatt will be your answer. Okay, I'm not using any fancy formula, nothing. All I used was graph. So that's the beauty, right? In any other coaching institute, you will see they are using some formulas like slope of group characteristics, so and so. But I use basics. I always like to use basics, as like we try to remember as little as possible. Yes, in the previous questions we have to. There is no other option. If you don't, you'll not be able to solve the question in the exam hall. But in this case, wherever I see that there is a way out to solve with basics, I try to solve it. So let's solve the next question. The figure below shows the per phase open circuit and the short circuit characteristics. Okay, and these are the ratings of the machine, and this is the speed. The field current IF is measured in amperes. The readings taken are marked as respective x and y coordinates. The ratio of the unsaturated to saturated synchronous impedance would be. Okay, that is what they are asking. The ratio of the unsaturated to saturated synchronous impedance. Do you know what do we mean by unsaturated synchronous impedance? Unsaturated synchronous impedance basically means, if I assume, so OCC line will saturate, right, due to like the property of magnetic materials, it will saturate. If I assume that it never saturates, it is linear in the same field current of the rated armature current, right? In this case, the rated IA rated, if you compute, it will be coming out to be around 20.2 amperes. You calculate from this equation, your IA rated will come out to be 20.2 amperes. That is what they have shown here. This is the current, IA current, armature current, and this is the field current. Okay. So at this same current, if I extend this straight line, right, and if I find the voltage here, whatever voltage I got, and if I take the ratio of that voltage V unsaturated over IA, like IA rated basically, right, and that will give me my ZS unsaturated. In this case, in this case we see V unsaturated, I don't know, I will have to extrapolate. So we got 2 points, right, and we have to approximate it as a straight line. So if I got 2 points, I can easily make the straight line out of it, right, I can easily make the straight line out of it. So we got 2 points, right, so we know the slope of the equation, it is 100 upon 1. The slope is basically 100, slope is 100. So every 1 unit I will move on the right hand side, it will move by 100 units on the top, on the y-axis. Yeah, so just one small change. Okay, I'm sorry, I previously told that this is related to this ACC line. No, so I'm sorry. So what I meant was, is we will extrapolate till the point of the field current. Actually my my graph is not enough, till the point where I get the field current, right. So basically, for what field current I got the rated voltage, and then I assume my graph to be linear, and then I compute the voltage from there, right. This is my V unsaturated. I'm extremely sorry, I made a mistake. I thought this is the same line. No. Okay. So we got the slope to be 100. Now what we will do is we will add. So from 2 I need to go to 8, right. So on the x axis, how much change I need? 6. So on the y axis, how much change there will be? So 6 into 100, because the slope is 100. So for every unit of x axis change, the change in y is 100, right. So it is 600. So change is 600 units. Okay. So I will have to add 210 plus 600, that is my V unsaturated. V unsaturated. So that will be equals to V unsaturated would be equals to V unsaturated would be equals to 210 plus 600, that is 810 volts. That is what my V unsaturated is equals to, right. Okay, we got our V unsaturated. I already know my IA rated, like basically the rated current at the field current IF4. So that will be 20. So basically your ZS unsaturated would be 810 by 20, that is 81 by 2. Okay. And what about your what do you call, what about your ZS saturated? So your ZS saturated would be actually equals to basically whatever was the saturated voltage, that is 400 upon the current, that is 20, right. So now they are asking me the ratio of unsaturated synchronous impedance to saturated synchronous impedance. Right. So this will be equals to 81 by 2 upon 40 by 2. So this is 81 by 40. So this is almost equals to 2.2025, that is present in option B. Okay. So certainly option B is correct, but here, right, everything is fine. But one thing we have made a mistake, very silly error. So I told you that my rated armature current is 20.2 amperes. Answer is correct. But this, right, actually is the line rated current. There was a slight mistake here. So remember, your alternator is delta connected. So if it is delta connected, your root 3 VL IL equals to my kVA base, that is 14. So you know what is your line voltage, that is 400, and if you solve, right, you will get back this value 20.2 amperes. That is your line rated current. Okay, it is your line rated current. Now what will happen, your per phase rated current, because we are doing the per phase analysis, it will be 20.2 by root 3. So technically, right, here instead of IA rated, it should be 20 by root 3, 20.2 by root 3. Actually, this should not be 20 actually. Similarly, here also, instead of being 20, it should be 20.2 by root 3, correct? But what is happening, because we are taking the ratio, both the root 3 and root 3 here are getting cancelled. So ultimately in the final answer, it is not affecting us. So I think examiner also forgot this. That is my assumption, because they only gave this 20 amperes of current and they are telling this is my rated current. But this is a line rated current. Whatever analysis we do in open circuit test and short circuit test is the per phase analysis. So per phase rated current is something else for a balanced system, right? So that's just my assumption. If you have some other thoughts, let us know in the comments below. And trust me, no one will tell you all this, right? Koi nahi bolega. I am just saying you, like whatever mistakes I can make also, I honestly say I can make these kind of mistakes. Okay, let's solve the next question. This is the next question. So a cylinder rotor synchronous generator with constant real power output. Okay, so a cylinder rotor synchronous generator, right, with constant real power output and constant terminal voltage is supplying 100 ampere. A cylinder rotor synchronous generator with constant real power output, okay, so the power is constant, that is Vt Ia cos theta is constant. Okay, supplying is supplying 100 amperes of current, and your cos theta is 0.9 power factor lagging. An ideal reactor is now connected in parallel with the load. An ideal reactor is now connected in parallel with the load, as a result of which the total lagging reactive power requirement of the load is twice. An ideal, okay, so I have a load here, right? This is my synchronous generator and I have my load connected. Now a reactor is connected across the load, which result of which the total reactive power requirement is twice. So previously what was the reactive power requirement? So I can compute that, right? So QL would be what? It will be active power. Okay, okay, I don't know, do I know the voltage? I don't know the voltage. Okay, cool. So it will be basically VTIA sin theta. I know what is theta, I know what is IA, I don't know VT, so I will not be able to exactly comment. But now they are telling me that which if I connect that reactor, then the total lagging reactive power requirement is twice the previous value. So now the reactive power requirement, that is QL dash, is 2 times VTIA sin theta. Previously it was VTIA sin theta. Now what they are asking me is, while the active power remains constant, same, so active power does not change, so VTIA cos theta is same, the armature current would be, what is the change in the armature current? This is actually pretty interesting question. Okay, so reactive power changed but the active power remained same. Okay, what can help me here? So what is my tan theta? So if I draw the power triangle, this is my active power, this is my reactive power, and this is my apparent power, right? Okay, that is my theta. So tan theta would be equals to Q upon P, right? But this Q upon P would not help me, because theta will change, right? Yeah, theta will change. This will not help me actually. This will not change. This will change. What will help me? That is what I'm trying to figure out. It has now become twice. If I connect the reactive flow. Okay, I know the okay. Okay. One thing is certainly true, that if the active power is constant, right, that means Vt is anyways constant. The terminal voltage, it is connected to a constant terminal voltage, right? So if Vt is constant, basically it is essentially telling me that my Ia cos theta has to be constant, correct? So what was the armature current in the first case? 100 amperes. So 100 into cos theta, what was the cos theta in the first case? 0.9 must be equals to, like, this is constant. In any case, this will always be constant no matter what. So it will be equals to Ia to cos theta 2. Okay, Ia to cos theta 2. So this is equals to my thing. Now I need to find out the information regarding cos theta 2. How will I calculate? So that I will calculate using this thing, right? So okay, so active power is same. Yeah, I think this will help me actually. This thing will help me. So what is tan theta 1? Tan theta 1 would be, right, because I know cos theta 1, so I can compute theta 1. Theta 1, this would be, I think, 25 point something, right? Let me compute this. Cos inverse of this, yeah, 25.84 degrees. Okay, so 25.84 degrees, tan of this is 0.484, correct? Now I don't know what is my tan theta 2, right? But what is this actually? What is this? This is equals to, this effectively tells me the relation between Q and P. So my Q effectively is equals to, actually my Q, right? Q is equals to (0.484 P). Okay, so Q is 0.484 P, right? So this is my Q value. Now what is tan theta 2? It will be again Q2 by P2, and I know my P is not changing. Active power is not changing. My Q2 is 2Q, and I know Q by P is already 0.484. So this will be, actually, your tan theta 2 will be 2 times this. So it will be 0.986, and from this I can compute my cos theta value. So cos theta 2 would be equals to 0.718. That is what my cos theta 2 is equals to. If my cos theta 2 is equals to 0.718, then I know my cos theta 2. Now I can compute my Ia2. So Ia2 would be this into 0.9 into 100. So that is 125.3 ampere. Okay, so Ia2 is 125.3 ampere. That is your answer. So we solved everything from basics, no formula, nothing. So let's solve this question. Two generating units rated at 250 megawatt and 400 megawatt have governor speed regulation of 6% and 6.4% respectively. So let me just draw the diagram. Make it. So this would be basically, so no load frequency and no load frequency, they should from no load to full load. Okay, both operating in parallel to share load, assuming free governor action, the load is shared between this. Okay, so they have not discussed what is the amount of load shared by them. So I'm assuming they're operating in parallel, so of course their no load frequencies has to be same, right? So yeah, so their no load frequencies will be same, and in no load basically they are delivering zero load. Okay, that makes sense. Yeah, now they will deliver some load and then it will reduce. Yeah, so assuming the by the 250, if assuming governor free action, both the operating in parallel to share, okay, if they share 500 megawatt, then what will happen? So I'm assuming at no load they will operate in parallel, so they are not delivering, so they will have some rated frequency. I don't know what is that frequency, I don't need to know. Okay, and this is my power axis in megawatt basically, right? And this is the full load basically. At full load, let's say this is the generating unit 1 that is delivering 250 megawatt at full load, and this is generating unit 2 that is delivering 400 megawatt. Okay, so this will be this, right? Generator 1 has a slope of 6%. So from no load to full load, its regulation is 6%. What does it mean basically? So percentage regulation is equals to, now this thing you have to remember, unfortunately it will be F no load minus F full load divided by F full load. Okay, so this thing mostly sometimes I also tend to uh, forget this actually, so don't worry that whether you will remember it or not, but this thing you will have to remember. Okay, I am guessing I'm doing it correctly, right? F no load minus F full load divided by, hold on a second, percentage F full load, right? 6% governor speed. Yes, this seems correct. Or okay, let's not, yeah, I think, no, sorry, I think this will be F no load. I think this will be F no load. Yeah, this thing you will have to remember, unfortunately, right? So this is F no load. Then, so what is essentially happening is the frequency, right? From no load to full load, this much is the reduction, and the percentage regulation is this multiplied by 100. That's all. Okay, so how can I compute the slope of this line? I want to compute the slope of this line, right? So I know this parameter. What do I know? I know this parameter, right? So F no load minus F full load would be equals to percentage regulation into F no load divided by 100. Okay, now this is the variation from F no load to full load. Now what is the variation of the power? The variation of the power is 250 megawatts. So this, if I divide this by 250 megawatts, correct, this divided by 250 megawatts, like basically this is the change in the y, this is a change in the y, right? What is the change in the x? That is 250. So change in x is 250. So if I divide both sides by 250, then I get my slope of the line. Okay, so yeah, this is the slope of the line, and nowhere they have mentioned anything regarding the no load frequency, speed. They should actually, I'm assuming they have to mention the no load frequency. I don't know if they have to mention or not. Let's see. Yeah, this is the slope of the first line. Okay, I don't think we will require it, but let's see. So what will be the slope of the first line? It will be percentage regulation divided by 100 into the power, basically into the F no load. That is constant in both cases. So let's assume that F no load is equals to F only. This is F only. Okay, so the slope in the first line will be 6 upon 100 into 250 into F, and the slope of the next line Okay, one more thing is there actually. This will be minus, right? You have to consider this negative because I'm considering f no load minus f full load, right? But actually my final position is f full load, so it will be just the opposite. So there will be a negative sign here. It will be minus of 6.4 into f no load, that is f uh, divide by 400. Okay. Now what will happen here? So they are sharing load 500. What is the load shared by 250 megawatts? So if they are sharing a load of 500, right? So basically your P1 plus P2 would be 500. Also they will be arrive at the same, they will operate in the same frequency. Let's say they are operating at fx frequency, correct? And my generator 1 is delivering P1 power, generator 2 is delivering P2 power, right? So can I use this slope somewhere? Of course I can, right? I think I can. So this will be can I write my P1 in terms of P2, anything that I can do? That is what I'm trying to think, that is what I'm trying to figure out. So what will be your P2 equals to? So your P2 sorry, what will be your this fx equals to? Fx will be equals to your f no load, that is f minus of whatever is the slope 6 point. So let me compute. So yeah, I can write in terms of P1 and P2. So fx will be equals to f, let me write it in terms of this. So all I'm doing is writing the equation of a straight line. So what will be my fx? It will be the y intercept, that is f plus mx, right? So m is minus this into x is P1. That's all I'm doing. Y equals to mx plus c. That is all I'm doing. So this is my c. Okay, this is my c. F is the no load frequency, that is my c. Don't confuse this f with this f, right? Okay, f is the no load frequency, that's all. F is just a constant number. So minus 6f by 100 into 250 into P1. Now this will be same as f minus 6.4 f divided by 400, okay, into P2. So f and f will be cancelled. So I think we don't need the no load frequency. We actually don't need the no load frequency. So there, right, directly f and f is getting cancelled. And like what will happen? These two frequencies are same, so they will be cancelled. This f also will be cancelled. I will actually effectively find out the ratio of P1 and P2 from this equation. So look, I am not using any formulas, okay? So you can trust me on that. I am not using any formulas. I think one more thing is there, even though if they don't define, okay, this thing you have to remember. Actually, this is pretty important thing. This I will recommend you to remember. You see anywhere else, you will not understand the solution. Trust me, you will not understand it. So yeah, I will focus on this equation now. So what will happen is your P1 by P2 would be equals to 100 will be cancelled. So this will be 250 by 400 into 6.4 by 6. Okay. So from this I will get the relation between P1 and P2. So 250 by 400 into 6.4 by 6. So it is, so your P1 is equals to 0.67 P2, right? So that is what your P1 is equals to, and I know this relation, right? So from this I can calculate. So P1 plus P2, so this will be equals to 1.67 P2 is equals to 500, and your P2 would come out to be into 500, that is 300. Now is it in my range? You always have to check is my whatever value I have computed, is it in my rated range, right? Rated range. So yes, it is. 400 megawatt is in the range. Like 400 megawatt is the rated power and it is delivering 300 megawatt. So it is lying in the range. We're good to go. What about P1? So P1 would be 0.67 of P2. So it will be lower. So 0.67 of P2. So that is equals to 200. Right? And it makes sense obviously because it is delivering 500. So 300 is getting delivered by the second generator and 200 is getting delivered by the first generator. Again, let's check, is it lying in my range? Yes, 200 is inside 250, it is less than 250, so yes, it is lying in the range. So P1 generator 1 will deliver 200 megawatt of power and that is what they're asking. The load shared in megawatt by the 250 megawatt generating unit, that is 200. So actually technically you don't need this no load frequency and everything, right? This question was very beautiful, and I think when this question came in my, so this was came during my year when I cracked GATE, and I think I was not able to solve it, but still I got 74.33 marks. I don't know how I got it, but this question I don't remember, but I think I was not able to solve this question because it seems very difficult at first because you don't know what to solve, what unknowns to assume, you don't know that, right? That's why. Okay, so we got to our answers. The solution was pretty elegant. Let's now move on to the next question. So you can see solutions anywhere else for this particular question, you will not find it, trust me. Let's solve this question. A star connected 3-phase 400 volt 50 kVA 50 Hz synchronous motor has a synchronous reactance of this. So XS is 1 ohm per phase, and of course it does not have any armature resistance, so we are safe on that. The shaft load of the motor is 10 kilowatt, while the power factor cos phi or cos theta is 0.8 leading. Okay, it is leading, it is a motor, correct, it is a motor. The loss in the motor is 2 kilowatt. So the loss in the motor is 2 kilowatt, right? This is a shaft power. The magnitude of per phase excitation of the motor, the magnitude of the per phase excitation EMF of the motor in volts. What is the magnitude of the per phase excitation EMF of the motor in volts? So this, right, is equals to basically, so if it's a leading load and it's a motor, right, so there is a formula for this, that is Vt cos theta minus IRA, RA is 0, so I will still write it minus IRA, and as the load is leading, right, so this thing will be changed, this will be plus in the other part, whole square is there, Vt sin theta plus IXS whole square. Okay, so that is what my EF is equals to. So yeah, this will be this, right? Now in our case, as RA is 0, so this will be simplified, Vt cos theta whole square plus Vt sin theta minus Ia XS whole square. So this will be equals to, so yeah, they want the per phase per phase EMF, right? So do I have Vt? Vt we do have, so this is the line voltage, right? So Vt per phase would be 400 divided by root 3 because it is star connected. Okay. Do I have the armature current? I don't have the armature current. Okay. So how can I calculate the armature current? So we know that the shaft power is 10 kilowatt and losses in the motor is 2 kilowatt. So what is the power input from the supply? It is 10 plus 2, that is 12 kilowatt, and this power will be equal to root 3 VL IL cos theta. Okay, and yeah, from this I can actually calculate IL because everything else is known to me. So let me compute this somewhere. So into 10 cube into VL into into cos theta is 0.8. So let me calculate this value. Okay, I forgot to multiply VL. VL is, now it is a line voltage, it is not the phase, right? So it will be 400. So this will be equals to 12,000 divided by root 3 into 0.8 into 400. So this will be equals to 21.65 ampere. So we got everything almost. IA we got, I know XS, I know sin theta, I know VT. So let's solve it, right? So your EF would be equals to this VT. VT is okay, VT is 400 by root 3. What is 400 by root 3? That is equals to 230 T.94 whole square into VT sin theta. So it is 230. Okay, hold on. So it is only VT, right? I have to multiply the cos theta as well. So cos theta is 0.8. 0.8 94 into 0.6 plus IA into XS. IA into XS. So IA is 21.65 into XS. XS is 1. So this will be into 0.6, hold on, into 0.8 whole square. Okay, this is also whole square, right? So this bracket 230.94 into 0.6 plus 21.65 whole square whole under root 244 0.54 volts. So it is 244.54 volts per phase, right? That is your answer. That is what they asked. So you have to round off to nearest integer. So you will say it is 245 volts. Okay, I think, yeah, I think that makes sense. Or yeah, it can be 245 or 244, anything makes sense. So let's solve the next question. So this is the next question. A 3-phase synchronous motor with synchronous impedance 0.1 plus j 0.3 per unit per phase has static stability limit of 2.5 per unit. What does it mean basically? Okay, the corresponding excitation voltage per unit would be. So this question is actually pretty interesting, right? So I have a motor and its armature resistance is not 0. when it is not 0, then things will become very difficult. Okay, so yeah, we will see. So we will have to consider the armature resistance and the synchronous reactance, and it is a motor, and here I have my, this is my terminal voltage Vt, right, that is equals to 1 angle 0, right, and this is my excitation voltage Ef here, and my Ra and XS are, everything is in per unit, and they tell me the per phase has a static stability limit of 2.5 per unit. So what does static stability limit means? Static stability limit basically means whatever is the electrical power developed by the synchronous motor, this will be equals to maximum for a certain delta. Okay, for what delta we'll see. We'll see for what delta. If my Ra was 0, so then this delta would have been 90 degrees. If you remember something, your PE expression, if Ra is 0, it is Ef Vt by XS sin delta, right, and this becomes maximum when delta is 90 degrees, correct. But actually here Ra is not 0. So if Ra is not 0, you cannot do this. So this formula is only valid if Ra is 0. Then you either you remember the formula or derive it. Okay, so let us derive it. Okay. Obviously you can remember it, no problems, but let us derive it. What if in the exam hall you forget it, right? So let us derive it. So this Ef will have an angle delta, this is Vt 1 angle 0, and I will have a current Ia, right? Ia will be a phasor. So basically what is the power developed by the synchronous motor, right? Whatever power it is receiving, so what is the power that it is receiving? It is this voltage into Ia conjugate, right, the current, correct. So the power developed by the synchronous motor, right, it will be Ef. Remember, we will not consider salient pole because they have only given us a synchronous reactance, so don't consider salient, consider cylindrical motor. So it will be Ef angle delta into Ia angle theta conjugate, right. So what is Ia angle theta? So Ia I can actually compute, it is Vt, that is 1 angle 0, it is basically Vt minus Ef vector divided by Zs vector, right. So this will be basically equals to Ef Vt by Zs theta. So this would be equals to Ef angle delta. Now Vt is 1 angle 0, so this does not have any problems. So this will be 1 angle 0 only if I take the conjugate inside, right, minus this will have, okay, sorry, this is the this is not the active power, right, sorry, what I am doing, this is the apparent power, right, developed in the motor. Okay, so this will be Ef is some Ef, magnitude of Ef angle delta and conjugate, so it will become minus delta, correct, upon Zs conjugate. Okay, Zs angle will be, so magnitude of Zs angle of minus theta s, correct. Now this will be equals to, I'm just deriving it, okay, I'm doing the task of teaching him, okay. So this will be magnitude of Ef angle theta into 1 angle 0, that is simply the same thing only, 1 only. So this will be divided by Zs minus theta. So minus theta can go on the top side, right? So it will become theta s plus delta. One small thing I forgot because I remember the formula. Just one small thing here, right? We will not define it as Ef delta because this is a thing that I have taught in my full course. So your active power will always flow from higher angle to lower angle. This I have taught in power system, in synchronous machines as well, I have told you. So if you assume your delta to be positive, let's say some 3 degrees or 10 degrees, right? So active power will not flow. Certainly, if this particular reactance is lagging in nature, active power will never flow. Certainly, then this has to be negative. Now to represent this as negative, right, what do? We write minus delta. Like you will see in every derivation, synchronous motor is written as minus of delta. What is the reason? You'll never know the reason. The reason is this. Just to say to you guys, delta is a positive number, minus delta is a negative number, and yes, power now can flow from higher angle to lower angle because this is 0 degree and this will be minus 10 degree. So yes, it can flow. That is the reason. So actually, I will write this minus delta. That's why you can write this delta, no problem. But you should be able to figure out when you will come to this point that your delta will be negative. That you should be able to figure out. If delta is positive, then power will not flow if only plus delta is written. That's why we assume delta to be positive. I write minus delta so that you can see, the user can see it is a negative angle. That's all. So this will be minus delta, hence this will be also minus delta. This also will be minus, this will be plus. Okay, that is the only difference. Now here this will become minus delta then, right? So just be careful, this will be minus delta and this will be Vt is 1, this will be EF square. Okay, just EF square, just give me 1 second. Yeah, that is correct. So this will be EF square upon minus delta plus delta will be cancelled upon Zs into theta s. Okay, so this is the expression for developed power of a synchronous motor, right? Minus sign will be there, sorry, negative sign will be there. Now what they are asking me, the corresponding excitation voltage per unit if the steady stability limit is 2.5 pu. If the steady stability limit is 2.5 pu. Okay, let me check this. So what is your theta s? So what is this is the apparent power, right? What is the active power? Active power would be, I will have to take the cos, right? So this will be SE will be P plus JQ, where P will be basically this thing cos of this, like basically whatever is the cos, because this also will have a real and imaginary part, this also will have a real and imaginary part. So the imaginary part, so the real part would be EF, magnitude of EF by magnitude of ZS cos of theta s minus delta minus magnitude of EF square by ZS cos of theta s. Now what they want, they are telling me that what is the steady state stability limit, right? Steady state stability limit is the static stability per phase has a static stability limit of 2.5 pu. Okay, it has a static stability limit of 2.5 pu, right? So that means the maximum value of P is 2.5 pu when my delta, like when my delta is equals to what? So for what value of delta this will be maximum? When delta equals to theta s, when this value will be maximum, because the other terms are not dependent on delta, only this term is dependent on delta. So when my delta is equals to theta s, this will be maximum, correct? So this will be equals to EF. So the steady stability limit will be EF by magnitude of Zs when my delta is equals to theta s, right? So this term will be 1 minus magnitude of EF square upon magnitude of Zs into cos of theta s, that is equals to 2.5 pu. Everything is in pu, correct? Now everything is in pu. What is cos theta s, right? It will be basically your real upon imaginary, not sorry, real upon Zs, right? So real upon Zs, that is Ra upon under root Ra square plus x s square. So this will be equals to 0.1 whole square plus 0.3 whole square whole under root into 0.1. So that is 0.316. That is my cos of theta s. So yeah, and what is magnitude of Zs? Magnitude of Zs is, okay, just hold on. Yeah, this cos of theta is, so this is 0.316227, and I will have to compute. Let me assume EF square as x square, okay, and magnitude of z is, right, let me just compute magnitude of z, 0.1 reciprocal. Magnitude of z will be 0.316. That's all. Am I correct here? Just hold on. So 0.1 square plus 0.3 square whole on root. Yeah, 0.316. Correct, the inverse into 0.1. Oh, the inverse is also same. Okay, that's interesting. So this will also be 0.31622 almost, approximately, right? Approximately magnitude of z, and this will be x upon 0.31622. So approximately this will be cancelled, and this will be 2.5. So your equation, quadratic equation, will be x square. This, if I take the inverse, this is 3.16, right? So x square minus 3.1622 x plus 2.5 equal to 0. So 3.16 22 plus minus b square. So 3.1622 whole square minus 4ac, right? That is minus 4ac is 10 basically, upon 2a. So this whole square minus 10, okay, this is almost 0. That's interesting. So it is almost a perfect square, so it does not even matter. So 3.1622 upon 2 is 1 point. So your x is equals to 1.5811, and your x is nothing but the magnitude of EF. So what they have they told? To round off to 2 decimal places. So approximately this will be equals to 1.58 pu. This will be the answer of the question. Very beautiful question actually, and people will solve it directly. They will jump onto this equation directly and they will solve it. But I wanted to give a different feel, so I derived everything so that you are doing revision as well, right? You are doing the revision as well. Okay. Okay, let's solve the next question. This one, I think 2 more questions are left. So 3-phase 11 kVA synchronous motor is connected to a inductive power factor load of root 3 by 2. So your cos theta is root 3 by 2, that is basically your theta is equals to 30 degrees. And via a lossless line with a per phase inductive reactance of, so it is connected via a lossless line, so Ra is 0 basically. Okay, it is connected via lossless line, and like, okay, I have a generator and then it is connected via lossless line, so it's like the resistance of the line is 0. Okay, it has only inductance whose reactance is J5. Okay, and here I have my infinite bus, right? Now the per phase synchronous reactance of the generator itself is 30 ohms, right? So now they are discussing about the generator also. Okay, this was the line reactance. Now they are talking about the generator as well. So generator, they are telling me that it does not have a armature resistance, but it certainly has a synchronous reactance, that is of 30 ohms. That is of 30 ohms, right? With a negligible armature resistance. If the generator is producing the rated current at rated voltage, if the generator is producing the rated current at rated voltage, so it is producing the rated current, so IA is IA rated, right, and voltage is also rated. Then the power factor at the terminal of the generator. So what is the power factor at the terminal of the generator? So they are asking me what is the power factor here. Okay, how do I calculate the power factor here? Interesting. Load power factor is this. They want me to calculate the power factor this at this point. So I know, let's assume few things, that three phase this generator. So okay, connected to an inductive load via lossless line, this right. So actually, what is the, so whatever they are telling me, right? So this, right, whenever they talk about this is always defined in terms of the terminal voltage, right? The term voltage that the user will observe when it will probe. So user can never probe here. User can probe only after the synchronous reactance. So this point is the terminal voltage that is given, that is 11 kilovolt. Remember, it is a okay, nowhere it is mentioned actually. Per phase, this nowhere mentioned, but it is a star connected load. Okay, so this will be 11. So it will be a star connected by default. So it will be 11 by root 3 kilovolt. Okay, that is the terminal generator voltage. Now they are telling me that it is operating in rated condition, right? It is taking rated current. So if it is taking rated current, what is, can you compute the rated current here? So I know the rated apparent power, right? And I know the rated voltage. I need to compute the rated line current, and in star both the line current and the phase current are same. So from this I will be able to compute the armature rated line current. So it is 10 MVA upon root 3 into 11 kilowatt. So 10 raised to power 6 upon root 3 into 11 into 10 cube, that is okay, something, okay, something I'm missing up. Hold on. So this will be 10 into 10 cube upon root 3 into 11 . 524.86 volts. Okay, yeah, so this is the current, so not volts, sorry, amperes. Okay, this is the rated current. I don't know the power factor, certainly I don't know the power factor, but I certainly know what is the load operating at, right? So what is the load operating at? So load is operating at this power factor, correct? This is the power factor, that is the load operating at, but I don't okay, from this one information I can say that. So this power factor, right, this is my load basically, right? The infinite bus is connected to a load. So in this the current is same, whatever current I have computed, this current will be same, IA. So if they say that the motor is operating at rated power, that means it is delivering rated current. So this current is okay, magnitude of the current, but the what will be the phase of the current? Phase of the current I can compute from here. So current will be magnitude of IA angle theta, and if it is leading, theta will be negative. So if it is lagging, theta will be negative, and it is a inductive load, right? So your theta is minus 60. Okay, sorry, your theta is minus, sorry, here I mentioned theta to be plus 30. No, it is negative, right? Why it is negative? Because load is lagging. That's why theta will be negative. So I got my current. So I got this current, right? IA. So IA magnitude is, because it is delivering rated power, so it will deliver rated current, that is 524.86 angle minus of theta. So minus of theta is minus 30. That is the current that it delivers, right? Now what are they asking? They are asking me rated, if the generator is producing rated current at the rated voltage. So they have already told me it is producing rated current at the rated voltage. I don't know whether it is producing rated power. I'm sorry, I don't know whether it is producing rated power, but it is certainly producing rated current, right? And from here I computed the rated current. Then the power factor at the terminal of the generator is, so they are asking me the power factor at the terminal of the generator. What will be the power factor at the terminal of the generator? So here, right, this voltage will have a phase EF angle delta, correct? This will have a phase EF angle delta. So essentially what they are asking me, and obviously what is the current from this terminal? It is IA angle theta. So basically they are asking me what is cos of delta minus theta. That is what they are asking, right? That is what power factor means. Power factor basically means cos of the angle between the voltage phasor and the current phasor, right? That is what my power factor basically means. So I will have to compute delta. To compute delta, I will use KVL. So what is KVL? KVL will be EF angle delta would be equals to this current into this reactance plus whatever is the voltage here. What is the voltage here? Do I know the voltage here? No, I don't know the voltage here. Okay. Okay. That is interesting. But what do I know? I know the voltage magnitude here, right? So basically this voltage magnitude is 11 by root 3, okay, angle delta, that is certain, plus this current, okay. Okay. Do I know the power? I know the current, I know the power factor, but I will not be able to comment on the power, right? That is what I am trying to think of. Hold on a second. Okay. We have, so we got this equals to, so everything is in kilovolts, right? So this will be Vt, sorry, this voltage, right? That let's assume that this voltage is some Vt voltage, right? So Vt angle 0, we'll assume this to be the reference, plus your Ia theta into basically your J into XS, right? That is what my equation is. Assume that this is in kilovolt, everything is in kilovolt, the units are in kilovolt. Now for this I need to compute Vt. Now do you remember another formula? So for a lagging load, for a generator, your EF was equals to, magnitude of EF basically was equals to Vt cos theta plus Ia Ra whole square plus Vt sin theta plus Ia XS. Now actually if you remember it correctly, now you will get confused here, but if you remember correctly, this formula was to calculate the potential at this point. But what we are doing, we are very smart, we are engineers, right? We are reusing this formula to calculate the voltage at this point. How can you calculate? So consider the same scenario. I know the voltage at this point, a inductance is connected, I want to compute the voltage at this point, right? So actually these two, computing the voltage between these 2 points and computing the voltage between these 2 points, are they somewhat similar? Both of them have inductive load connected, both of them has some phase difference, that's it, and I know the current to it, both of them, right? So I can reuse the formula here and here. What I will do, I know this voltage, I will compute this voltage, right? So in this case, whatever I have written is correct, I can reuse the formula, okay? So essentially, right, I know this potential, I don't know the angle, and there is an inductive link, I can always use this formula. Got it? So yeah, so your EF is I know 11 by root 3. So let me just write this in actually volt only. Let's not do it. Let's write in volt, otherwise you'll be confused. So this will be actually 11 by root 3 into 1000. So that is actually equals to 6350.85, this whole square. So this will be now VT I don't know, right? Now we are lucky that our RA is 0. Okay, if this RA is, there is no resistance, right, only inductance. So this will be VT cos theta square plus this also will be squared, right? This also will be squared, right? VT cos theta square. Okay, just give me 1 second. Do we really need to do this? Okay, I got it. Maybe we don't need to do it. Maybe without it also we can calculate. I'm just trying to think of that. I'm just trying to think of something. Okay, I think yeah, I think without this formula also we can do. So if I see this equation, right, so what will be the, let's equate the real part. If I equate the real part, so I will have to take cos. So this will be 11 by root 3 into 10 cube cos delta into VT plus, now this does not have any real part, right? It is all okay, sorry, this does have a real part. So this essentially contributes plus 90, right? So this will be cos of IAXS cos of 90 plus theta. Okay, 11 by root 3 sin delta equals to, now this is purely real, right? So this does not have any imaginary part. This will be 0 plus IAXS sine of 90 plus theta. Okay, now what are the unknowns here? I know IA, I know XS, I know 90 plus theta, I know this, I need to calculate delta. Yeah, I think we don't even need to do this. Okay, so whatever I've explained, you can use it, but here technically we don't need it. So okay, so from this actually we will be able to calculate the value of delta. So what do I need? I actually need delta only. I don't need anything else. Okay, I don't even need anything else. So I need delta. I don't even need VT. Okay, I need delta only. So your sine of delta, right, will be equals to, let me compute this. Your IA is, we have just computed IA. It was 524.86. So this is 524.86. Now your excess is equals to okay, your excess is basically, so this is not excess actually, this is x, sorry, this is not excess, this is the link between the synchronous generator terminals to the infinite bus. So sorry, this is not excess. I'm so sorry, I'm extremely sorry, this is not excess. Okay, just x, don't get confused, there is some synchronous reactance here, this is not excess. Okay, I'm sorry. So this will be IA and x is basically 5, I'm guessing, right? It is 5, yeah. And what is theta? Theta is minus 30, correct? Theta is minus 30. Theta is minus 50, right? So this will be 524.86 divided by into 5 into sine of 60 upon 11 by root 3 into 10 cube. So let me compute this. 524.86 into 5 into 0.5 into root 3 upon 11 divided by 1000. So your sine delta comes out to be 0.2. So if I take the sine inverse of this, so your delta would come out to be 11.93. So actually I don't even need VD, right? What I need is I need this value. So I don't need to do all these things. Ultimately I need to find out cos of delta minus theta, correct? Yeah, delta minus theta. So cos of delta minus theta. So it will be cos of delta, that is 11.9376 minus of minus 30, because theta is negative, right? So this will be plus 40, so plus 30 cos of this. So it comes out to be 0.744. Okay, lagging. I hope I'm doing everything correctly. Just give me 1 second now. This, what is the angle? Theta v minus theta I, right? So theta v minus theta I. So power of a triangle will increase. So previously it was root 3 by 2, that is 0.86. It has worsened. Yeah, but why is my answer not matching? Am I doing something? Am I missing something in the calculations? That is what I'm thinking. Okay. The power factor of the terminals of the generator is, what is the power factor of the terminals of the generator? Okay, the terminals of the generator. I think, okay, I missed the point here. Yeah, I think I made a mistake here. When they mean the terminals of the generator, I think they mean including at this point only. I think I may have missed a point here. That is what I'm thinking of, right? Or no, I don't think I missed. I think I've done everything correctly only. Terminals of the generator, right? This is 524.86. Okay, that is the current. This is 5 sine 60. Okay, sine of both sides. So cos and sine. So if I took the sine, cos will be there. Sine, this will be 0. Sine of 0 is 0. Sine of 90 plus theta. Theta is minus 30. It is a lagging load. Right? Theta would be negative. So it will be sine 60. So yeah, sine 60 if I do. I'm just thinking what mistake I'm making. The power factor angle essentially should be cos of theta minus. So this, right? Just thinking something. Just give me 1 second. 11.573. Cos of this comes out with this only. Where am I making the mistake? Let me check again. Let me check the calculations. So sine 60 is, oh sorry, I think sine 60 is root 3 by 2. Oh sorry, what? That's what happens, man. That's what happens. It's like 3 a.m. at night, and that is what happens. I'm writing sine 60 as half. Okay, and the same thing you will do in the exam hall. Shit, man. Okay, yeah, sine 60 is not half, man. The one place where I did not use calculator and I made a mess of it. It is root 3 by 2. So this is not 0.2. Oh my god. So this into 5 into 524.86 into root 3 divided by 11,000. Yeah, it is 0.35 actually. Oh my god. I was just scratching my head. What have I made? Like, where have I made the mistake? Now I do cos in sine inverse of this. So actually your delta comes out to be 20.97 degrees. Okay, 20.97 degrees. That is what your delta comes out to be. And yeah, your delta is 20.97. Now it makes sense. Now this will be fine. So now this plus 30 cos of this, yeah, Now we are getting closer to our answer. 629, that is almost 6.3 lag obviously. Okay, because you see that like overall this theta is coming out, this difference is coming out to positive, so current lags the voltage, right? So 0.63 lag, of course, because there are inductive load like link connected, so it has to be lagging. So 0.63 lagging, that is present in option A. Okay, so I was just thinking, where have I made the mistake, man? I was just so much stressed here. Okay, this is a good question. This is a good question. So here we have this induced EMF in a 3.3 kilovolt 4 pole 3 phase star connected synchronous motor. Okay, the induced EMF in a 3.3 kilovolt, so 3.3 kilovolt 4 pole 3 phase star connected synchronous motor, right? .3 kilovolt, okay, 4 pole star connected motor, and in phase with the terminal voltage. So at no load it is in phase with the terminal voltage, so EF and VT are both in phase. Okay, on application of a mechanical load, the induced EMF phasor is deflected by 2 degrees mechanical. Okay, it is shifted by 2 degrees mechanical, right? So how many degrees electrical? Because this is a phasor diagram, this is the electrical quantity, right? So I will have to convert this into electrical. So we know my theta E is equals to P by 2 of theta M. So basically my delta E, right, because my EF has been shifted by 2 degrees mechanical, so that's why delta I will calculate. Delta is the angle between the EF and VT. So delta E would be P by 2, that is 4 by 2 of delta M, that is 2 degrees, right? So actually electrically it has shifted by 4 degrees. So this difference would be 4 degrees. Okay, so this difference is 4 degrees. Now if the synchronous reactance XS is 2 ohms and the stator resistance is negligible, then the motor armature current magnitude in ampere during the loaded condition is closest to. So what happens is that they're telling me that the induced EMF in this 3.3 kilovolt is considered to be equal and in phase with terminal voltage. So basically my induced EMF is equals to my VT in no load, right? So this magnitude is same actually. This is equals to my VT. Okay. Now what happens? My EF is shifted by 4 degrees electrical. Okay, although this is not 4 degrees, but I am just showing you by a large quantity so that you can solve it. Okay, magnitude will be same still. Suddenly for the transient the magnitude will be same. Okay, now what are they asking me? Why is this shifted? This I have taught in my full course. Okay, I will not explain much here due to because the mechanical load is connected, there will be a synchronizing current that will make the rotor magnetic field and stator magnetic field in sync. That is called as the armature current, that is called as the synchronizing current. Okay, and what happens like and this drop, right, ISY, so the synchronizing current would be somewhere here. Actually it will not be here, synchronizing current would be somewhere in the middle. Okay, and there will be a drop synchronizing current into excess that will be on this line. Now what happens is like this I have taught in my full course, so I will not explain here much. So if you don't understand, you have to go and watch the full course. Okay, and it is completely present on YouTube for free, so you can watch it. So this will be like this, right? Now what happens is your synchronizing current actually bisects these two lines. So this will be actually 2 degrees, this will be 2 degrees. All these I have taught in my full course and it is present on YouTube. So here I will not utilize much time to explain stuff here, I will directly solve. 2 degrees, 2 degrees. Okay, this thing you will have to understand intuitively only. Now, and this drop, right, this length is called as the drop, that is I synchronizing, magnitude of I synchronizing into XS. Okay, now as it bisects, so what I can do is I can draw a right angle triangle here. So this will be 90, this triangle will be 90 degrees. Okay, so if this triangle is 90 degrees, what will happen is I can use the sine law. And okay, let me just enlarge this picture, right? Let me enlarge this picture, then you will understand it even better. So here I will have EF. Now this EF has been shifted by 4 degrees, right? And during this shift, because the mechanical load has been connected, the stator magnetic field and the rotor magnetic field for a second were out of sync, and to make it in sync, a synchronizing current will flow. Okay, that will make the two magnetic fields in sync, right? So this will be 2 degrees, this will be 2 degrees. Okay, this will just bisect the angular difference between EF and VT. So VT is still here, right? VT is still here. Okay, now what happens, this drop, right, this drop is known as magnitude of I synchronizing into XS. Okay, and as it bisects, so this length will be half of it, because what are they asking? They're essentially asking me what is the armature current magnitude, and to calculate that you will have to use these things. So it will be half, so it will be I synchronizing into XS by 2, right? So from here you can easily calculate using the right sine rule, right? So if I consider this length and the angle opposite to it, right? So it will be length I synchronizing, magnitude of I synchronizing, XS by 2 upon sine of the opposite angle, that is this, that is sine 2, that is equals to sine 2. And what about this? So this is the length. What is the length here? EF, right, upon sine of the opposite angle, that is sine 90 only. How will you remember all these things? So you will have to remember the unit of this and unit of this must be same. So that's why there will be a term XS. That's how you can remember it. Now from this I can calculate my magnitude of synchronizing current, that will be equals to 2 EF by XS into sine of 2 degree. So I know all the values. They have given me the synchronizing reactance. So this will be 2. So 2 into divided by 2 into EF. EF is basically 3.3 kilovolt per phase, right? So you will, so also they have told me that your, actually this is VT, but they told me VT and EF are same. So your EF is also 3.3 kilovolt. 3.3 kilovolt, is it per phase? No, it is not in per phase, because by default if it is given, so you will assume it to be in star. If it is star, so your phase voltage will be 3.3 kilovolt by root 3. In what unit they have asked? In amperes. So I will convert this into, I will convert kilovolt into volts, and sine 2 I will have to multiply, and sine 2 will be a very low value. Okay, sine 2, if I calculate sine 2, it's sine 2. Sine 2 would be 0.03 something, right? So 0.035 almost. So if I solve this into 1000 into 3.3 divided by root 3, so this is actually equals to 6.6 66.5 amperes. Okay, this is my synchronizing current. So yeah, this is the magnitude and this is your answer. You got your answer. 66.5 is your answer. But if they would have asked you what is the phase of the synchronizing current, so your phase, right, it will be directly in the middle. So your synchronizing current, so if this is the reference, right, it will lag because your EF has also moved, right, whatever. So if your EF will lag, so basically your synchronizing current, right, the angle of synchronizing current will be, it will be magnitude of I synchronizing angle minus delta naught, sorry, by minus delta by 2. Okay, so because your EF has lagged by 4 degrees, your ISY will lag by half of it. Okay, this thing, if you remember, maybe in future questions they might be asked, so please keep a note of it. This is important. So yeah, if your EF has lag by delta E, remember, electrical angle, then your ISY will lag by minus delta by 2. Okay, so basically EF lags by delta, that means EF angle has minus delta and ISY will be minus delta by 2. So magnitude of ISY is 66.5 ampere, that is your answer, and minus delta by 2, your delta E is basically 4 degrees, right? So minus 4 divided by 2. So that is minus 4 divided by 2, that is 2 only. So this will be minus 2 degrees. So this will be the complete expression, vector expression, phasor expression for your synchronizing current. And trust me, nowhere else you will find this solution. Nowhere else. Okay, they will use some big things. Yes, we did use this concept. This was a kind of memorizing part, but otherwise you will not be able to solve this question. If you don't understand this, or if you don't memorize this, you will not be able to solve the question. As simple as that. So with this, we have ended our electrical machines. If you have enjoyed, let us know in the comments below what stuff you have enjoyed. And trust me, this kind of analysis you will not get anywhere else. And yeah, with that, we have revised our electrical machines in a very well manner. So if you have enjoyed, please hit the like button, please comment down below and hype the video. I will see you in the next video. Until then, happy learning.